Hi, and welcome back to another video in our series on covering statistics for year one. So this will be one of the first topics that you'll learn in statistics when you study the subject. And what this topic will be data collection. So there aren't actually very many calculations you have to do in this topic, but it's quite important that you understand some of the theory behind it because a lot of this theory is the reason for a lot of what you do in statistics. So if you understand this chapter really well, it will really help you understand, why do we use statistics and what's the importance of it. So in this chapter, we'll be looking at some stuff like getting data from a population and a couple of definitions of different kinds of words that you might see every now and then. We'll look at different ways you can sample a sample from a population. So there's a few different types of those, and we'll take a look at that. And we'll also look at different types of data. So that will be stuff like continuous data, discrete data, and so on. And we'll also take a look at some kinds of questions that might come up for this. So what I really want you to understand from this chapter, some of our key takeaways are understanding what is a population, what is a sample, what is a census, as well as the advantages and the disadvantages of both. Normally in exams, they'll probably ask you, what does it make more sense to do and why should you do it and why you shouldn't. We'll look at what is random sampling, systematic sampling, stratified, quota, and opportunity sampling. And finally, we'll look at the different types of data, so qualitative, quantitative, discrete, and continuous types of data. And finally, we'll look at how this all fits together when we group the data up. So without further ado, let's carry on to one of the first areas that we should look at for this topic. So starting off with statistics, like we said before, we want to understand what is a population, what is a census, and what is a sample. So let's have a question. Let's pose a question here. So let's say we have a question of some kind. Our question might be, what is the most popular TV channel in the UK? So what is the most popular TV channel in the UK? Now, there's lots of different ways we could do this. So one of the ways we could do it is ask every single person in the UK, or we could ask like a few people, and if we've asked enough people, we might think, okay, that's enough to kind of get an accurate answer. If we want an answer which is 100% correct, we know for 100% sure we got it right, then we'd have to ask every single person that we're interested in the UK. And of course, this is not really feasible. So statistics kind of looks at the fact that normally we have a huge amount of people, or like a big kind of data set that we have to ask. But in real life, we can't really, go around and check every single data point. So statistics kind of just looks at how do we look at like a few of these data points and kind of guess something about the population that we're trying to do. So I mentioned the word population a few times. What do I actually mean by the word population? So a population, quite simply put, is basically the entire set of items that we're looking at that we're interested in. So if I had to write that, the entire set of items we are interested in. And what I mean by that is, for example, in this question, when I said the most popular TV channel in the UK, in real life, I probably wouldn't ask, kids who are under 3 or kids under 4, because probably a lot of these won't really have a favorite TV show. Or more accurate, let's say the kid is at less than 1, he won't really have a favorite TV show to be able to say it. So I probably wouldn't ask those types. So when I say this part here, which is we are interested in, I mean all the people who would be qualified to answer our statement. So in the most popular TV channel, probably kids who are 5 and upwards. So the population is every single person that we're interested in. So the population in this case would be the entire UK population who is older than 5. So that's what population is, every single person that we're interested in, or the entire set of items we're interested in. Now, continuing from this, if we have a census, and you might have heard of the UK census, what happens in the census is you actually end up asking every single person within a population. So in a census, you measure every single person, or every member, or every item in a population. So like we said, a population was the entire set of items we're interested in, and how can we, gather data about it? So before we said, well, we have a few different options. So let's say that, actually we'll continue this example. Before I get onto that, I should probably explain what a sample is. So yeah, a census is you look at every single person in the population. Now let's look at what is a sample. So as you can probably guess from what the word of a sample means, is when you take, a few observations from a subset of the population, which means I can't look at everything about the population, but a sample is when I take a subset of the population, and from this subset of the population, I want to understand some more information about the population in its entirety. So a subset of the population gives me information about the whole population. So about the whole population here. So this is a bit more practical because often I can't, ask every single person. So now just kind of put this together and just kind of help you understand it better. So if I had, let's say I had an entire set of people. Let's say this was my entire population here. Let's say this is my population. And let's say in my population, these crosses represent all of the people in my population. This is just an example. So let's draw a couple of crosses. So as you can see, there's a lot of people that are asking. And just imagine there's a lot more. So let's actually draw in a few more here. Let's copy that and paste that across. So here we go. These are all the people in our population. Now, what would happen in a census is what you'd end up seeing is that we would actually ask every single person in this population. So if the blue highlighting represents all the people we'll ask, when it comes to a census, what ends up happening is we'll ask every single person. And if you don't ask every single person, it's not a census. So that means that we've done a census. And a sample, if this is also my population, means I might ask a few people. So I might ask these people, I might ask these people, I might ask these people, could ask this person here, a few different people across my sample. But the idea of my sample is I don't ask everyone, but I ask enough people so that I'm happy that I'm roughly, fairly accurate in what I'm doing. So that's kind of how you can look at what a census is and what a sample is with regards to your population. So obviously we've talked a bit about the advantages and the disadvantages of both of these approaches. And it might be obvious to some people which one they'd use over the other, but it really does depend on what you're trying to find out about the data. So now what we'll do is we'll move on to some of the advantages and disadvantages of using a census over a... So now if we look at a census first. So let's just take a look at a census first. What are the advantages of a census? So one of the main plus points of a census is that it will give you a 100% accurate result. If you've asked every single person in your population a question that you're trying to find out, then of course if you ask every single person in that population the same question, then you're going to have an accurate answer. But then there are quite a few disadvantages. One of the thing is the time taken. It takes a very long time to do a census. Imagine doing this for the whole UK and asking a question. Often in statistics, your population can become very, very large. So a census can become a little bit impractical. You can't also do this when, let's say you're trying to test something. So when you're trying to figure out something, so let's say what is, I don't know, if I was selling 2 bars of chocolate and I wanted to figure out which one people prefer, if I had to give every single person in my population 2 bars of chocolate, then I can't really do that because I can't give 1 million bars of chocolate away. So if the testing process that I have destroys the item, then you can't use it. So you can't use it then because you can't, if you're destroying the item, you can't keep getting the item back to give to other people. And the other thing is there's a lot of data to process. And if you imagine there's a big amount of data, you need to do a lot of number crunching, and that's not always the easiest task. So there's a lot of data processing involved. Data processed. Cool. So that's some of the advantages and disadvantages of a census. Now if you move down to a sample, with a sample things are a bit better, as you can imagine. So one of the main advantages of the sample is that it's less time consuming, so it takes up less time, and also it's less expensive. So less time, less expensive, and that makes it a little bit more practical to do. And then, you have to get fewer responses. Fewer responses are needed because let's say I asked 100 people and I only got like 50 back, then sometimes that's okay too. And of course, you have less data to process. So a lot of the plus points for the sample are the negative points of the census, if just reversed, so you have less data to process. So apart from that kind of stuff, what are some of the disadvantages of the sample? So one of the disadvantages is the final answer that you get, or the final conclusion, let's call it. Conclusion is less accurate. Of course, if I've only asked half of the population, or let's say if I had to do the question I had before and only asked 100 people, it really does depend on which 100 people I picked, and that can really change the answer I get at the end. So it's not always as accurate as a census. And the other thing is that the sample I pick might be too small. So the sample picked might be too small. And why is this a problem? One of the main reasons that this could be a problem is because if I've taken a sample, it might not really give me enough information about my population, or it might give me like the wrong impression of my population. So an example for this is, let's say I picked 100 people to answer a question. Let's say I asked a bunch of 10-year-olds, I asked 100 10-year-olds. It's quite likely that the 10-year-olds will give me an answer which is probably relating to a cartoon that they've seen or something like that. So if I just use that as my sample, then that's not really that representative of my whole population. So in statistics, when we're doing samples, we have to be really, really careful that we pick the right kind of sample. And doing this is not as straightforward as it might seem. So moving on from this, let's just talk a little bit more about, how the sample can affect the conclusions we've made. So how does picking a sample affect our conclusion? So that's the kind of question that we want to answer right now. So how does picking a sample affect our conclusion? Well, one of the main things that we care about is we care about the size of the sample. Obviously, the more people you can ask, the better it is. However, let's say there's a bigger size is more accurate usually. However, it needs more resources. So it would be nice to have a bigger sample size, but we can't necessarily always get this bigger sample size. So usually the bigger the sample, the more accurate it is, but you need more resources to be able to cover it. And also usually if your population is quite different, so if we asked this question when we were doing the TV shows, then if the population has also different segments, then you need a larger sample to kind of capture these different segments. And what I mean by that is, let's say these different colors I'm going to draw, like this, these are probably all the green kind of crosses. These are all of my 5 to 10-year-olds, and all the black crosses are going to be my 10 to 15-year-olds. And just for the sake of an example, let's have some orange crosses that have also got my population, and these can be my 15 to 20-year-olds. So now what I need to be really careful is that if I pick a sample, I might end up picking a sample such as the one over here. So I might end up picking this sample. If I happen to pick the sample from this whole population that I've got, then that's not going to give me the accurate result. Likewise, if I also pick something like this, it'd be a bit more accurate, but it still wouldn't be very accurate. If I was picking a sample from this, I'd probably want something a bit more like such. It's a bit messy, but you can get the idea. I want something which can incorporate, roughly the same patterns I find in my big population in my small sample. So obviously you can see why something like this is bad, something like this is bad, or something just like that is bad. So it really just depends on the kind of sample you pick, and it's very important. If my population was uniform, and what I mean by that is, let's say my population looked a little bit like this. So I knew that in my population, I had some sort of pattern like this, then it's a lot easier for me to pick a sample, because I'm like, okay, cool, I can pick this as a sample because that represents my population, that represents my population, so does that. So because uniform, I know what the patterns to expect. However, if it's not uniform, it's very like the above case, then it's a lot more difficult for me to select a population. And like we said before, the different samples that you pick can end up with different conclusions that you make, and that's just because you have different kinds of things that you pick up in your sample. So like we said before, if I picked up all these 5 to 10-year-olds, I have a different answer to, let's say, if I picked up all of these 15 to 20-year-olds in my sample. So it's very important to get your sample correct. And just some technical terms that you should be aware of. So when you're doing something like this, the individual units that we've got in here, so if I just get rid of that, the individual units that we have in here, these crosses, every single person in this thing is known as a sampling unit. So every single cross that you can see here, every single one is a sampling unit. And usually the sampling units in your population, you'll often number it. So let's say, what I mean by that is, let's actually use this bottom one here instead of the top one. If I was using this as my sample, then normally what you'd want to do in statistics is you would want to number your sampling units as so. So here I might number them from 1 to 12, and all of these things put together are known as my sampling frame. So just to recap that, in my population, every individual cross that I've got, every single individual unit here, all of these are known as sampling units. And normally in a sampling frame, when I numbered them and made a list of everything all put together, this is all known as a sampling frame. So that kind of covers some of the basics of, statistics when it comes to the population and when it comes to taking a sample. So we talked a lot about sampling, and what would be good to cover next is what different approaches do we have to actually undertake sampling. So we'll just cover some of this in the next. So since we've been talking a lot about sampling, let's talk about some of the different ways in which we can actually achieve this. So we're going to take a look at three different things. We're going to be taking a look at simple, random sampling, systematic sampling, and stratified sampling. So normally when we're selecting a sample, it's quite important that we choose it so it's representative of our population. If you're trying to find out your favorite TV show and you go ask all of your friends, it's quite unlikely you're going to get a fair representation because all of your friends might like the same show, and then you're not including people who might be older and have different tastes. So it's quite important that when you're sampling, it's as close to your population as you can get, and hence you want it to be representative. So simple random sampling is one of the methods in which we're going to take a look at first. And before that, what I should also mention is that normally the random sampling, any of these types of sampling we're talking about, it helps to remove bias from your example, and this is quite important as well. So let's take a look at what simple random sampling is. So simple random sampling. So what is this? So this is normally where you want to select, let's say you have a population, or let's say you have a sampling frame, and you need to select a bunch of people from that sample. Then what happens is you say that every single person in your frame has an equal chance of being selected. So it'll make more sense with an example. Let's say I have 1,000 people in my school, and I need to find out what the favorite TV show of all these people are, going back to the TV example. So in simple random sampling, what you would often do is first you have to allocate a sampling frame. So let's say in this case it's 1,000, and it's a list of 1,000 people, and I've got all of that in my register from my school. Now what I might do is, let's say I've got someone called Sophie, Bob, Adam, and so on. What you'd normally do for this is you'd normally number them from 1, 2, 3, and so on. And then what we have to do is to make sure we're randomly selecting numbers, we use a calculator. And on this, you have a simple random generating function, which generates you random numbers. And you can use this to generate random numbers. And based on the numbers that you found, you can select that person. So let's say I use my calculator and I've got the number 3, then I would select Adam. And then let's say I did it again and I found the number 1, I would select Sophie. And you keep doing this until you found the sample size that you want. So let's say my sample size was 10. Then what I would do is I'd find 10 random numbers on my calculator, match the numbers on my register, and then that would give me my random sample. So this way is removing any bias because you're purely basing on the numbers that you've got, and it can be quite a good way for you to select your sample. Another thing is that you can also use something called lottery sampling, and this is very similar to what we've just done. In lottery sampling, what you might often do is you might write the names of the people on tickets and literally draw them out of a hat. And that can also be random if you want to get a random sample. So simple random sampling is pretty much just that. It's in the name, it's pretty simple, and that's how you do it. So another way in which you could do it, which is a different type of sampling we'll take a look at, is something known as systematic sampling. So systematic sampling. So what is systematic sampling? Well, the thing is about a random sample we might also end up selecting like a bunch of 10 people in our sample from before, and they might not actually be the best representation of our group. With random sampling, you're not always going to get the best sample that you always want. Sometimes it might be great, sometimes it might not be so great. And that's just the thing about having a random sample. You never know what's going to happen. So another way you can do it, just to be a bit more careful, is do something called systematic sampling. And what you do here is, if we have our list again of people from 1 to 1,000, instead of just randomly choosing people from it and using the calculator, what we do instead is we choose people at regular intervals. So what do I mean by that? Let's say I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's say I keep going. Let's say I've got about 10 people in my new sampling frame, and I want to do systematic sampling. So what I might say for my systematic sample is that I'm going to choose a regular interval, and at every second person, I'm going to pick them. So in systematic sampling, I'll skip the first one. Or actually, no, it depends how you normally do it. Sometimes you might start from the beginning and then take it on from there. So I'd say I select the first person, then I select the third person, then the fifth person, seventh person, and so on. Or if I chose to start with the second person, I might have chosen the second, then the fourth, then the sixth, then the eighth, and so on. But the key thing is, you're always choosing the people that you want at regular intervals. And that's what makes it systematic when you're going through it. So that's the part where you've got systematic. You saw that at the beginning of deciding where I should start. The best way to start in systematic sampling is actually to choose a random number. So again, you can choose your random number in a calculator, and actually you can use that to start. So let's say on my calculator, I chose a number between 1 and 10, and I got the number 8. So then what I would do then is I'd start at the number 8, skip 1, go to 10, skip this number here 1, go to number 2, then skip 3, go to 4, go to 6. So that's another way it kind of wraps around. So you can also do systematic sampling like that. And the interval you choose will often depend on the question. It should tell you that, or you have to choose it yourself. But that is more or less what systematic sampling is. So that leaves us with the final type of sampling, and this will be stratified sampling. So what happens in stratified sampling? Let's go down here. So we've got stratified sampling, which looks like this. So in stratified sampling, what happens is we take our population and then we try to divide this into mutually exclusive strata. And the word strata is probably something new. So what this means is, for example, if we have a population of people, we might decide to split them into males and females, or we might decide to split them into people from 0 to 10 to 11 to 20, 21 to 30, and so on. So it's kind of taking your population, splitting it into groups that covers everything. So another example might be, if I want to find out, what's the most popular hair color, I might take my population and I might break it into people who have blonde hair, black hair, brown hair, and so on. As long as I've covered all the different types, that's what different strata are. And then what we do, once we've got a different strata, we take a random sample from each of these strata. So this kind of example will make more sense once we kind of draw it out. So let's say that we have a population. So let's say we have a whole population here. And in my population, I want to find out the favorite movie that people have. And I want to make it fair. If I ask just exclusively kids, then I might get, like a Disney film or something which is aimed for kids. And if I ask older people, then I'll get a different answer. And if I want to find out on average what's the most, popular TV show, I should be asking everyone. So what we do here is we take our population and we break it down into different strata. So what we might break it down into, if we were doing strata over here, is we might break it from 0 to 10-year-olds, 11 to 20-year-olds, 20 to 21 to 30-year-olds, 31 to 40, and let's say 41 plus. So this would be the different strata that we have. So once we've got the strata, we will have to take a random sample from each of them. So what will happen here is we might say, okay, once you split it into these different people, I am going to select 10 people from here, 10 from here, 10 from here, 10 from here, and 10 from here. So this is how I can get a sample size of 50. So this is more fair because what we're doing is we're making sure that we're selecting people who are across the board representing our population. So this way we don't need to worry about not representing our population that well. So you can see there's lots of different ways that we've learned about representing our population. So what we've said is we've had simple random sampling, which is because we want to make sure we've represented everyone, we just randomly pick numbers and then hope that's a good representation. We've had systematic sampling, which once we take a starting point, we might go once every 5 people, once every 10 people, but we're hoping that will cover most of the people in the population, give a fair sample. Then we've got stratified sampling, which is probably the most advanced of the three, which is trying to say that, okay, we've got a population, break it down into the different sets we think are good, and select people from there. So there's also an equation which will be worth knowing for stratified sampling, which I'll put up here. So the number that you sample in your stratum, so the number sampled in stratum is equal to the number in your stratum divided by the number in population. And then you take all of this and you times all of that by the sample size. So this will make more sense if we perhaps look at an example specifically for stratified sampling. So let's say that I'm working in a bakery and I've got a bakery which has got a really big event coming up, and therefore I look at the different ages of people I've got. So let's say I've got a bunch of 0 to, or in the case of this 0 to 20-year-olds working, I've got some 21 to 40-year-olds working, and I have some 41 to 60-year-olds working. So what would happen in this case is, let's say I've got 50 0 to 20-year-olds, I've got about 20 21 to 40-year-olds, and I've got about 30 41 to 60-year-olds. So if you remember what our equation before was, we said it was the number sampled in stratum was equal to the number in stratum over the number in our population, and we times that by the population size, like this. So in this case, what would happen is, let's say we've got all of these workers and we want to sample from all the 100 people, we only actually want to sample 10 people. So we don't want to sample everyone, we only want to sample 10 people. Now the thing is, unlike the example we had before, we could see that our stratum was split all equally. So you can see that you've got 10 people here, 10 here, 10 here, 10 here, and 10 here. So this is all equal and it's spread across. But sometimes it might not be the case that you want to argue that you want it to be completely equal across the strata. Because what if my population has a lot of 21 to, let's say, it has a lot of 21 to 40-year-olds. So this section of society, if that is the one that's, got the largest number of people, then maybe I should have chosen different numbers in my strata. Maybe I should have chosen 5 here, 5 here, 15 here, 15 here, and then 10 here. Maybe that would have been more fair. So this equation kind of helps us get around that. So like we said before, we wanted a sample size of 10. And we've got 100 people to choose from. Now, obviously, you can see here, like the example before, the most representative part of our population, there's mostly 0 to 20-year-olds. Then there are 41 6-year-olds, and the least are the 21 to 40-year-olds. So we want to represent this in our stratum when we're doing this. So how can we do this? So for 0 to 20-year-olds, if we use the example that we've got, first we need to take a look at how many workers there are. So there are 50 workers in our 0 to 20-year-old category. We divide, so that's the number in sample. Then, the number in our stratum. And then after that, we need to divide this by the number in our population, which is 100 people. And then we multiply that by the overall sample size that we have. So the overall sample size that we wanted, we said was 10. So multiply by 10. So if we do that, we get a half times 10. So that means we should be choosing 5 people from this sample over here. So if we do the same thing for the 21 to 40-year-olds, we find there are 20 out of 100. We times this by 10, and this will give us 1 over 5. So that will give us 10 over 5, which is 2 people. And if we do this for the 41 to 60-year-olds, what we find is that we have 30 over 100. Multiply that by 10. So that gives us 3 over 10. So that will give us 3 people. So like you can see, if we add up all these different numbers, we have a total sample size of 10. And this is also representative of our original population, because we've got 5 people, which represents the 0 to 20-year-olds, 2 representing the 21 to 40, and 3 for the 41 to 6-year-old. So it's in the right kind of proportions. So that's kind of how you can do stratified sampling. You look at the number you put in your sample. So this top part, where does that come from? You get this top part from here, the number in your sample. Where does your population number come from? Well, to get your population number, you have to add up all of the different people that you've got. So 50 plus 20 plus 30 give me 100. And where do I get my population size from? Well, I get that from my sample size of 10 that I've decided. So the question will usually give you all of that, and you just have to put it into that formula. And the final answer you get will be these, which tell you how many you should pick in your sample. So this means that if I have 5 people I need to select, I should choose 5 people from the 50. Then when I've got 20 people, I should select 2 people from there. And when I've got 30 people, I should select 3 people from there. So that's how that part works. So we've taken a look at a lot of the different types of sampling that there are, and now would be a good time to summarize a lot of the different advantages and disadvantages of each of them. So starting off with simple random sampling, some of the good things about this one is that it's going to be bias-free. So because you're choosing everything randomly, you're not choosing with any preconceived things in your mind. So you are just going to be making sure that everything you pick is purely random, and this will make it bias-free. It's also quite cheap and simple for small populations and samples. So if you have a small population, implementing simple random sampling isn't a very long process, and it can be quite cheap, which in the practical world is quite a useful thing to have. The other thing that you also have is an equal chance of selection for every single sampling unit. So every single member of your population will have a fair chance, or I should say an equal chance of being picked, which is often a good thing when you're doing your sampling. But there are some problems, and these include the fact that when you have a large sample, then simple random sampling can become quite difficult to do. And also you need to actually make a sampling frame to pick from. So if I was saying that I'm going to do simple random sampling for the favorite TV show of everyone in the UK, well, then I need to pick maybe like 100 people from which I'll randomly sample. And if the population is big, like we said before, this could be a problem. So then moving on to systematic sampling, we can see that systematic sampling is also quite easy and quick to implement. And the good thing is with systematic sampling is that I can still deal with large samples and populations pretty well. And the reason for this is you can just have a huge step in between the different picks that you make. So you might want to go every 100 people, every 1,000 people, whatever number you choose, but it helps you deal with the larger samples and get through them more quickly. You still do need a sampling frame for this one, and sometimes if your sampling frame isn't actually randomly picked, then you will have some bias introduced here as well. So finally, we'll take a look at stratified sampling. So with stratified sampling, it's quite good because it reflects your population better. And that's because we broke down our population into separate groups. And this means that we represent our population quite proportionally, which is quite a good thing to have in this kind of sampling. But then one of the difficult things with this is that you actually need to figure out what your strata should be. So it's not as easy as just breaking down the groups or your population into small groups. But someone actually has to sit there and say, okay, what are the right groups for me to split my population into? And this is actually quite a challenging task to do. And also the selection within the strata themselves will also have the same drawbacks as you did with systematic random sampling. So overall, these are the 3 different methods that you have. And what's important to keep in mind is that for your exam, you'll often be asked what is an advantage or disadvantage of each, and this list will be a handy thing to keep in mind. So now let's take a look at some examples of non-random sampling. And the first example we'll take a look at for this one will be something known as quota sampling. So what exactly is quota sampling? So quota sampling is where the person who's conducting the sampling, he'll often choose some characteristics about a population that he thinks will represent it. So for example, let's say you're going for a job interview, and in that job interview, the person decides, well, I'm going to have at least 50 people who I accept will have to have a degree, and the other 50 people who I accept have to have no degrees. So when the people will come into my interview, first thing I'll take a look at is I'll take a look at who I'm going to see, and I'll assess what group they fall under. So the first person comes in, and then I ask them the question, do you have a degree? If they have a degree, then I will say that, okay, the person will then fall into my sample space for people who have degrees. So look a bit something like this. I have 2 sets of quotas, and my quota is I need 50 people who have degrees. I need 50 people who have no degrees. That's the quota that I want to fill. So as the people come in, as these are my people, I'll take a look at the first one and say, okay, you have a degree, so you fit into this quota. The second one may also have a degree, so he will also fit into this quota. The third person may not have a degree, so he'll fit into this, and so on. So as you basically go through each of these people, you want to be sorting them out into different groups, and you'll basically decide whether you think this person will fall into the right quota or not. Eventually, what I might find is that as I keep filling up my different quotas, I might eventually fill up all 50 spaces for the people with degrees. So that means the next guy who comes along, let's say there's someone who came along here, he might also fit into the degree category. But when he takes a look at that, there's actually no space for him to go because my quota is full. So then, therefore, he'll be rejected. So the thing with non-random sampling is, or especially with quota sampling, is you have a quota and you say, I have this many spaces that I need to fill for a certain amount. And as you start interviewing people, as you start taking a look at your the people in your sample, then you'll keep trying to fill up your quota until it's filled up. Now, once it's completely filled up, if you find someone who belongs in our quota, we'll just simply ignore them and move on to the next person. And you'll normally want to carry this on until all your quotas are filled. So then eventually the situation would look something like this. And then we filled up everything. So just to summarize what this would look like. So let's say that I have 4 different quota that I need to fill like this. And as I have people come along, I find that this one can fit about 10 people, this can fit 5, this can fit 5, and this can fit 2 people. So these are the different quotas that I've chosen, and this depends on the researcher. So as I'm going through this, I might find that I've filled a few people here. The next person I meet might go here, some people might go here. Then eventually what will happen is as you add more and more people, you'll eventually start to fill up. So as you can see here now, if I have 2 more people here, and 2 more people here, and 1 more here, now I've filled up all my quotas. So even if I have people who do belong in these quotas, once they're filled up, I can no longer fill these quotas, and the only space left of the people is 10. And this will also continue all the way until I filled up my 10. And once that's done, I finish on my quota sampling. So in quota sampling, you can see you have a bunch of quotas you need to fill. Once you fill those up, then you're completely finished. So that's how quota sampling works. And this leaves us with something known as opportunity sampling. So this is our second form of non-random sampling. So opportunity sampling. So what is this? So opportunity sampling is quite simple. Opportunity sampling is quite simply where we're going to take a sample from the people who are available at the time that we're trying to conduct our interviews or the study that we're trying to do, and they fit the criteria we're looking for. It can also be known as something called convenience sampling. So this is something as simple as, let's say you need to figure out, what's the favorite food of people that people want to have. So then you might be like, okay, if you did other kinds of sampling, you might have to go through a long-winded process of finding a sampling frame. You might want to break them down to strata to find a more accurate representation. However, what you might just do is you might just go down to a nearest supermarket and ask the first 20 people that you see. And literally that is opportunity sampling. You literally just go down and meet the first few people who will fit your correct criteria that you want. You won't just ask some random person that you meet, but as long as they do fit the criteria, at the first opportunity that you meet them, you'll just ask them and you'll carry this on. So this is often quite a quick process that you have. So just like we looked for the random sampling, for this type of non-random sampling, we'll take a look at some of the advantages and the disadvantages. So for quota sampling, what happens is often a small sample can still be quite representative of the population sometimes, and that's because you've broken it into separate quota that you wanted to fill. And also you have no sampling frame. What this means is that you don't have to have a bunch of people to choose from. You can just keep asking people, and if they don't fit in your quota, then you don't count them. And if they do, then you put them in and you keep going until you finish. So you can basically just keep asking people and judge whether they fit your quota or not as you go along. So you don't need the sampling frame. So therefore, quota sampling can be quite quick and easy. You can decide if someone fits your quota or not. If they are, you can decide whether to put them in or not. So that usually works out quite nicely. And it can be quite easy to compare the different groups that you have in your population. So the different quotas that you have, you can kind of compare these two. But the problem is that obviously it's one of the non-random ways of doing stuff. So it does introduce some bias into it. So the bias can be down to the kind of quota that you choose. And the quota you choose can affect the final outcome that you get. And also you have to actually divide your population into the groups. And that means, just like stratified sampling in a way, trying to come up with these groups can be quite difficult. And finally, you don't actually record non-responses, because what I mean by this is if someone comes along and they do not fit in your quota, then you just discard them and just go on to the next one. You don't really make a record that this person didn't fit anywhere, and that doesn't really come into any of your sampling. So apart from that, we also have opportunity sampling, which is a lot simpler. So opportunity sampling is quite simple and quite cheap. That's the main advantages for it. Just going outside and just asking the first few people that you see can be very quick. But the problem is that if you do this, your sample's probably not going to be very representative, and it really depends on the researcher who's doing this. If I was doing this and I went down to my local supermarket, let's say someone else did, someone went down to their local supermarket, it can really vary the results that they get depending on the kinds of people that they go to and who they see first. So while it is quick and easy, it's not always the best way to do things. So for our final part of the video, we're going to take a look at the different types of data that we have to deal with. So the first of these is quantitative data, and this is the kind of data that you can give a number to. So things like weight, things like your height, things like shoe size, all these different things can be given a number to. So you can be 160 centimeters tall, or you might be 50 kilograms in weight. So anything that can be given a number to is a quantitative variable in nature. So that's all it means to be quantitative, something that you can give a number to. You can give age a number, you can give shoe size a number, any of that kind of stuff. Next, we have qualitative kind of data. And this is basically something which you can't give a number to, something which is non-numeric. And things which fall under the category of being qualitative include things like color, things like emotion. So I might say that these flowers are red, this one's blue, this one's green, and I might take that down in a survey. But that kind of data which I've just recorded, that doesn't have any numbers involved. So that's why it's qualitative data. So basically the difference between quantitative and qualitative data is basically whether there's a number involved or not. So it's as simple as that. Then after that, we have two other types of variables. These are continuous variables and discrete variables. And these can only be the cases for usually the numbers that we have. So for example, in a continuous kind of variable, that can take any value. So what I mean by that is I could have run the race in 1 second, in 1.1 seconds, in 1.11 seconds, and so on. Or my weight might be 5 kilograms, it might be 5.2 kilograms, 5.25 kilograms, I could go on and on. So a continuous variable is anything that will take any kind of time in between it. So it doesn't really matter what value it takes, it can take any value in between a time period. So then we have discrete variables, and discrete variables can only take specific values. For example, if someone asks you how many children you have, well, you can't have 3.5 kids, can you? You can only have 3 kids or 4 kids. So this is an example of something which is known as a discrete variable, some kind of variable that can only be considered as a whole number. So that would be one example for it. So that's basically all the different types of data. We've got quantitative, qualitative, and then under the quantitative numbers, we've got continuous and discrete numbers. So that's more or less the differences between them. So if I go down now, we also have something known as group data. And you'll often see this in your frequency tables. And to be honest, there's not too much you really need to know about this that you don't already know. In fact, you'd probably know all of it. So we have things like class boundaries, the class width, and the midpoint. So class boundaries, as you can imagine, will tell you the largest and the smallest numbers inside your table. So if you take a look at this example here that we have, if we want to know our class boundaries, well, here we can see the class boundaries are between 110 and 120. This one here is your minimum value, and this one here is a maximum value. So these are your class boundaries. After that we have a class width. So this is telling you how far apart these are. So in this case, we can see that the distance between these two is 10. So we can see the class width is going to be 10. And finally, we have the midpoint. So how do we find the midpoint of a table? Well, this one's pretty easy. We have 110 to 120. So the midpoint we can easily find as being 115. So that's all you really need to know about group data, and that's how you put it in. So putting all of this together, we essentially have all of the different types of data which we need to understand for this chapter. And along with the other types of sampling, if you put it all together, it should really come together. And this chapter, yeah, it's more or less pretty simple. There's not too many questions in terms of numeric kind of calculations. Like a lot of your other chapters, you have to do a lot of calculations and whatnot. But in this chapter, a lot of it really is understanding the words and the meanings behind it. So the best way to revise the chapter at the end really would be to go through all the definitions, make sure you can remember them. If someone asks you what it is, make sure you can give a good explanation and some examples for each of them. And apart from that, just make sure you remember the advantages and the disadvantages of the different types of sampling. And normally a question will ask you, okay, I've done this kind of sampling, is it better than this one or is it better than this one? And the only real calculations you often have to do might be, can you give an example of how you do stratified sampling? How can you break it down and pick the right proportions from different groups? So overall, I hope this video has given you a good understanding of the basics of statistics. And if you really do understand this video well, it will give you a good base from which to do the next chapters. So I hope this video has been helpful for you, and so welcome back to another video in our statistics series. So today we're going to be taking a look at measures of location and spread. So this is the second chapter normally in year one stats that most people cover. And it's not too difficult a topic because a lot of the stuff that you'll cover in this chapter you might have seen before. So things I will look at in this chapter will be stuff like the mean, the median, and the mode, which you'll have seen many times before. We'll just look at a few ways to do some calculations on this and the kinds of questions you can expect. Apart from that, we'll take a look at something called percentiles and deciles, and you'll probably know a little bit about this. It's quite similar to things like the median, but the median, is in the middle. Percentiles and deciles are just looking at all the other parts in between. So we'll take a look at that as well. Then apart from that, we'll take a look at things you already know about as well, like the range, interquartile range, interpercentile range, and so on. So these topics will be fairly simple, and you'll have known a lot of it from like your past studies in GCSEs. Then apart from that, there's a few new things we'll take a look at in this chapter as well. So things like variance and standard deviation, which you want to get used to since you'll be using this quite a lot if you carry on with statistics or even in the second year. And finally, we'll end with coding, which normally people find quite difficult, but as a concept is not too it's not too bad. So we'll eventually get to that. So there's quite a lot of calculations in this topic, so we'll try and go through a lot of the different ways you can solve the different types of questions, and hopefully by the end of it, any type of exam question or question for each of these should make a lot more sense than it normally does. So to start off with, let's just take a look at the mean, the median, and the mode. So before we get into that, actually, we need to know about something called a measure of location. And what is a measure of location? Well, it tells you basically where a value is in a data set. Now, it doesn't tell you about anything else. It just tells you that, in a data set that you have, where is that value going to be located? Is it somewhere in the middle? Is it somewhere at the beginning? Or is it somewhere at the end? And then going from the measure of location, we kind of go into this thing known as the measure of central tendency. And this basically tells you a bit more information. It tells you exactly about where the center of the data is. So it tells you a bit more information about, where the center of the data might lie. And the things that you've learned, things like the mean, the median, and the mode, all of them try to tell you something about where the middle of the data lies. And there's different ways of figuring this out. That's what the mean, the median, and the mode actually are. So let's take a look at our data set here. So if we're doing something like this, so something like the measure of location might tell you about where this one's located, or where this one's located, or where this one's located. But a measure of central tendency might tell you a little bit more about this piece of data or these sets of data, something more about where the middle of your data is actually going to be. So that should be fairly simple. And apart from that, let's just talk a little bit more about the mean, the median, and the mode, in case some of you haven't done it so much. So really, really quickly, when we're talking about the mode, if I have a set of numbers, the mode is the value which will occur the most. So let's say something like I had the numbers 1, 1, 2, 2, 3, 4, 5, 6, 6, 6. So the number 1 has occurred 2 times, the number 2 has occurred 2 times, 3 occurred once, 4 occurred once, 5 occurred once, but 6 occurred 3 times. So 6 here is going to be the mode. So that's the mode for this one here. Now, when you're doing questions like this, there's also something known as the median. So when you're doing something like the median, you want to figure out what is the middle number. So to do this, if you count this, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 numbers. Oh, my bad, it's 10 numbers there. So if you have 10 numbers, what you want to do is you want to basically count which one's the middle value. So let's just say I added another number here, which is 6. That would mean I had 11 numbers here. So to find the median, I'd say I have 11 numbers, and you always add 1 and divide it by 2. And this tells me the 6th one is the middle number. So I count 6 long, so 1, 2, 3, 4, 5, 6. and that's the median. And as you can see on the other side, there should also be 5 numbers, 1, 2, 3, 4, 5 here. So it's 5 on this side, 5 on this side. That's your middle value of 4. Now let's say we went back to the previous situation where you had something like that, and instead of you had 10 numbers, then you'd say 10 plus 1 over 2, which is 11 over 2, which is 5.5. So this means take the 5th and the 6th number and average them. So the 5th and 6th numbers would be 1, 2, 3, 4, 5, 6. So these two would be our 5th and 6th numbers. And then what we'll do is we'll do 3 plus 4 is 7. 7 divided by 2 is 3.5. So that's going to be your median value. So that's just a quick recap of stuff that you'll already know at GCSE. So hopefully you're already familiar with that. So moving on from that, let's take a look at how we can calculate the mean. I've only done the mean in the mode above. That's because I wanted to show you the formal way that we normally do the mean. So before we go straight into calculating the mean, let's actually talk about the equation for the mean. So the equation looks something like this, and we call this the sum of x over n. Now, what does that actually mean? I'm sure a lot of you are taking a look at this and have seen this symbol here. And if this is the first time you're doing this chapter, then this symbol will be new to you. And what this symbol here means is it means the sum of. And what this means is you add up all the values of x. So if, for example, if I had a data set which was like 1, 2, 3, 5, 7, then the sum of x would be 1 plus 2 plus 3 plus 5 plus 7. So that's what the sum of x would be. So it'd be something like 18. So that's how you can find out what the sum of x is. And n is the total number of numbers you have. So actually, if I go back for a second, x here, like you can see, was 18 if you summed it up. And n would be how many numbers we have in total. So it'd be 1, 2, 3, 4, 5. So 5 would be what n is. So if I did 18 over 5, which is the sum of x over 5, then that would actually give me what the mean of this set of numbers is. And actually, that's quite simple. I was going to do a calculation for the mean, but that's kind of it as well over there. So I'll do an example after this as well. So yeah, so basically, this is the sum of values of all values of x over the total number of data points, and that's how you can find something like the mean. So let's say I wanted to do a question based on this, and a bit harder than just finding the basic mean from what we've done. Let's say I gave you a question where I said, if I had a sample of different numbers, and I said from 25 numbers, I found that the mean of these 25 numbers was 5.5. And let's say from another set of 25 numbers, so let's put that in the first set, from another set of 25 numbers, I found there were 35 numbers. And the average of these 35 numbers was something like 7.3. And then I said, I put these two numbers together. So now that I've got these numbers together, what is the new mean of both of these sets when I add them together? So let's think about what this really means for a second. So I've got two data sets. So what I need to do first to figure out is I know that the sum of x over n is going to equal to my mean for everything. So let's start with the easy part. So what should n be? Well, I have 25 numbers here. I have 35 numbers here. If I add these together, that will give me my value for n. So I had dataset number 1 had 25 numbers, this is 35. Put them together and you'll get a total of what your new dataset should have. So here we can see it should be 60. And how did I get that 60? I did 25 plus 35. So that's the easy part. Now I need to find the sum of x. So how can I find what the sum of x is for both of these numbers? Well, let's take a look at them separately first. So this one here, if I say I already know the mean is 5.5 using the equation. So I'm just using this one here, this equation here. So I'm saying I know that the mean is 5.5. I don't know what the sum of x of these numbers are yet, but I know in total there are 25 numbers. So if I just do some simple algebra, 25 times 5.5 should equal to my sum of x. So based on that, let me just take out my calculator and calculate what is 25 times 5.5. That is equal to 137.5. So that's the sum of all these numbers. And it kind of makes sense because this is kind of saying that in a way that I've got 25 numbers and each of those numbers is 5.5. So I'm just seeing what the total is. Now, if I do the same thing here, I say 7.3 is the same as sum of x, which I don't know. Let's call this one the sum of y, divided by n, which in this case is 35. Then the sum of y should be equal to 35 times 7.3. 35.7.3 in my calculator, 35 times 7.3 is 25 or 255.5. So now I know that these are the two sums. So up here what I do is I actually add up these two sums together. So plus 255.5. And then this will give me another number which I can divide by 60 to get my mean. So 137.5 plus 255.5 divided by 60 gives me 100. Oh, not that makes sense. Divided by 60. Yeah. So actually, let's try this again. My calculator equals to that divided by 60. Okay, equals 6.55. So that's what the average of all these numbers together should be. So that's basically how you do it. And also, how did I get this number here? Well, I did the sum of x plus the sum of y. It might be a better idea if I call this the sum of z. Say it's the sum of all the numbers. But essentially, what did I do? I found the sum of x from here and found what these are, found the sum of y, found out what these numbers add up to, and then just add up all of that, divided by 60 because there's 60 in total, and that gives you the new average. And that's probably the easiest way for you to figure out averages and the such from these kinds of questions. So hopefully that makes some sense, and that's pretty much it for that style of question that you'll have. So before I move on, we'll talk a little bit about how you can do the mean for frequency tables. But before we do that, what I wanted to do was talk a little bit about the different measures, the mode, the median, and the mean. Like, which one's the best to use in which situation? Because they're all measures of central tendency, but they're all good in different kinds of situations. So the mode is usually quite good when you have like qualitative kind of data, or if you have quantitative data, you only really want to use it when you have a single kind of mode. Because if there's one example where something is chosen the most, then you probably want to use that. So it's quite useful in that case. Or if you have like two modes, it tells you that these are the two most popular kind of things that you have. So something like if your graph looks like that, or your graph looks like that, you can say that these are the most popular points. So the mode tells you something about that. And it's not very useful if each of your values only occur once. So if I had like 1, 2, 3, 6, 7, something like that, then all these values occur once. The mode would not really tell me anything, to be honest. And so when do we use the median the most? The median is good as quantitative data, so numbers, and it's usually quite good when you have extreme values, because extreme values tend to affect your mean. And what I mean by that is, imagine I had like 1, 2, 3, 4, and like 500, and I told you to find the mean of that. The mean of that would be quite large, and that would be affected because the 500 is quite large, and that affects the rest of your data. Whereas if I found the median of this set, I'd have only 3, which is a lot more representative than whatever the mean would be with that 500. So the median is very good to use when you have extreme values. Just keep that in mind as well. And finally, the mean is very useful for quantitative data, where if you have data which you use every single piece of data and to measure it, so it kind of gives you a true kind of measure of the middle value. But it's affected by extreme values, so you kind of have to be careful with that. But yeah, I hope all of that kind of gives you a quick primer into the mean, the median, and the mode. So what I want to do now is I actually kind of want to go into how we can solve this when we're doing a frequency table. So you've obviously learned that the sum of x, the mean of x, which we write like this, by the way. Notice I've had a bar. That bar means the mean of x. If you put the bar over anything, like a bar, b bar, that means like the mean of a or the mean of b, and so on. So this means the mean of x. So mean of x is equal to the sum of x over n. That's what you're used to learning from the part we just did. So how do we do it for a frequency table? So this is the kind of thing you use when I used to give you 7 numbers, like 1, 3, 5, 6, 8, something like that. And I said, find it for me. But sometimes we're not given data in that kind of form. Sometimes you're given data in a frequency table. In that situation, what you do is you use, again, the mean of x is now the sum of x times f over the sum of f. So don't let this kind of put you off if, this whole sum notation and all of that. I'll give you an example of how this works when you have a frequency table and how you actually use it. That'll be a lot more useful. So the x is the same, it just means the values again, and f is just the frequency of those values. So let's actually draw up a table. So let's say I had a table where, let's say something like the top one is people's favorite colors. Or let's say actually, I want to use a quantitative. I want to use something quantitative, not qualitative. So let's just say how many, I don't know, sweets someone has in their pockets or something like that. Well, let's say I have a few children and then they'll have a bunch of sweets. So we want to know how many sweets everyone has. And then here we can say the number of students with those sweets. So here we can say there's 12 sweets. Let's say some people have 14 sweets, let's say I have some 16, and let's say one guy had 22 sweets over there. So looking at that, let's just give random numbers here. So like 4, 16, 22, like 10 over there. Okay, so this is like your frequency table that you'd have. So just so you know, this would be your x values and this would be your f value, because the number of students you have is obviously your f is how many students have it. So 4 students have 12, 16 have 14, and so on. So to do this, first of all, let's actually find like the mode, the median, and the mean. So you'll know how to do each of the three. So the easiest one to do would be the mode. So to do the mode, all we need to do is say which one is the most popular out of the number of sweets people have, or how many sweets, do people have the most. So only 4 people have 12, 16 people have 14, 22 people have 16 sweets, and 10 people have 22 sweets. So clearly the number of sweets which is the most popular would be this one here, since 22 people have 16 sweets. So very simply, based on that, we can say the mode is 16 because it's the most popular one. So that one's quite simple there. Next up is the median, which is also fairly simple. So to do something like this, what we need to do, like we did before, is you group the numbers from smallest to biggest, and you would find out which where the middle number is. Now, in your frequency tables, normally the numbers are given to you like smallest to biggest, so you can see this is in ascending order. So you don't need to worry about reordering the table. If they weren't, then you just make sure that these numbers all come in smallest to biggest form, and you just do some reshuffling and whatnot. So for this example, let's see how many total numbers that we have. So how many students do we have in total? We have 4 plus 16 plus 22 plus 10 in total. So based on that, let's take a look at what that gives you. So 4 and 16 is 20, plus 22 is 42, plus 10 is 52. So we have 52 in total. So based on that, we need to take 52 plus 1 over 2, which will give us 53 over 2, which means we need to take the 26.5. So we have to say the 26th and the 27th values in our table. So where does that happen? Well, let's start with this. So 4 carries us into 4, plus 16 means we're in the 20th value. So the 26th and the 27th values lie somewhere in this 22 over here, probably somewhere here and somewhere here. So since they're both values of the 26th number and 27th are both 16 and 16, then that means I can say 16 plus 16 over 2 is 16. So again, just like the mode, it happens to be the case that our median is also 16. So that's fairly simple again to do. It's the same kind of stuff you've done in GCSEs. I think they also do frequency tables in GCSEs. They just don't tend to use all this notation we've used, but it's pretty much the same idea. So I'll get rid of that now, and now let's talk a little bit about how you would do the stuff for how you'd find the mean. So what we've been waiting for in this chapter is how do I use this equation? So the way you use this equation is, let's actually write it out. That's what I always tell my students all the time. Always start out by writing this equation at the top first, and then ask yourself what values do you know what you're trying to find out. So we're trying to find out this value for x, and therefore we need to figure out this one and this one here. So if x bar is equal to that, the easiest one again to figure out is the sum of the frequencies. So the sum of the frequencies is quite simply that plus that plus that. So I can't remember what that was again, so let's just calculate that again. That's 20, 42, 52. So sum of the frequencies are equal to 52. And I did that by doing 4 plus 16 plus 22 plus 10. And now what I need to do is find the sum of x times f. So what is x times f? Well, a nice way to figure out what xf is x is this value here, and f is this value here. So xf, if that's x, that's f, then xf is simply 12 times 4. Then I do the same thing for these two. I do 14 times 16. So at the top, what I'd write is something like 12 times 4. And since it's the sum of all of it, you remember that sum sign there. Then I do plus 14 times 16 plus 16 times 22 plus 22 times 10. All of that together will add up to a number. So let's actually figure out what that is. That's 48. And let's just use a calculator for the rest of them. So we have 14 times 16, which will give us 224, plus 16 times 22, which will give us 352, plus 22 times 10, which is 220, all over 52. So the sum of this is equal to 48 plus 224 plus 352 plus 220, which gives us 844 over 52. And if we do that value, we will get a final answer, 52, of 16.23. So to one decimal place, that's 16.2. So we can see that the data is fairly well distributed actually. The average is somewhere around 16, since the mode, the median, and the mean all have similar values. And that's how you use the equation. It was quite simple. If it helps sometimes, if you want, you can also draw another row under here, and you can say like the sum of this is 48, this is 224, this is 352, and this is 220. You can also do something like that if it helps. And then you can just put those numbers in here. But just remember, all I did to get these numbers at the top was 12 times 4 is that. 14 times 16 is there. And this times this is there, and this times this is there. That's all I had to do. I summed all of these up to get my 52. And that was it. So the equation might look a little bit scary or off-putting, but to be honest, pretty much that is the most useful answer. Now, based on all of that, I hope that the mode, mean, and median are fairly simple to understand, and you can do the calculations. And it's definitely worth practicing using this equation a lot with frequency tables, and also doing it on numbers which don't come up often. And there's lots of different variations of the questions. For now, I'll go over the variations of the different questions in another video, but the stuff you've learned so far should help you be able to solve a lot of the exercises that you've done. So yeah, from there we'll move on to the next part. So far we've taken a look at the cases where I have numbers like 1, 3, 5, 6, 8, and so on. Like if you have an example like that, or we've seen times where you might have some sort of frequency table and they tell you about each of these values. So like 1, 2, 10, and like 16, something like that. So you have like a frequency table of some kind. But I want to take a look at questions, and this is the final type of thing you should really know for the mean, median, and mode, which is what about tables where instead of that I have something like 15 to 20 and like 21 to 25, 26 to 30, and so on. So you can see the difference is that here I've got single numbers, but here I've got a range of numbers in between. And that does actually change the way we do our calculations. So rubbing that out, I'll give an example, and I'll be very quick to understand this. So all you do is, let's say we have like the length of a tree. And let's say we have, the frequency of these. And the lengths we'll have are 10 to 11, then 12 to 13, 14 to 16, and let's have 17 to 19. Okay, and let's just put some random frequencies in. So let's put 3, 25, 26, and 15. So there's not much difference when you're doing something like this. So when you're doing something like this, when you have to find the mode, you're not really finding the mode anymore. You say something called a modal class, and this is again the most frequent one. So you can see here the most frequent one to occur is this class here, and that's the 14 to 16 range. So the modal class is quite simply the 14th to 16th one over there. Now, the mean that you need to do is quite simple as well. So the mean, the only difference between this and what you had to do before was, since I've got a range here, you just need to find the middle part of that, and to do that you can just do 10 plus 11 over 2. So the middle of each of these values, this would be 10.5, this would be 12.5, this would be 14 point, actually no, this one wouldn't be, this one would actually be 15, and this one would be 18. Once you found the middle part of each of these things, you simply multiply that by this value instead of like these ones. So since that's 10.5, 10.5 times 3 plus 12.5 times 25 plus 15 times 26 plus 18 times 15 all over the frequency once again. So adding all of these up. So adding this up, I get 40 from that. Then I get 66 and 69. So that's your mean. Then simply do the calculation in your calculator and you'll get what your answer is for the mean. So the median is also very simple. So in this one, you also need to find something called, so the median, you find the median class. And for this, what you need to do is you add up the frequencies, add 1, divide by 2 to find where your median should lie. So we already know the 69 numbers. So 69 plus 1 over 2 means it's in the 35th number. And where does that lie? Well, here's 3 numbers. This gets us to 28. So the 35th number is somewhere in here, which is, again, in this class here. So our median class, once again, would be 14 to 16. That's the answer for that one. That's what the median class is. And hopefully that makes enough sense. And that's pretty much all you need to understand for the mean, median, mode. These are the 3 types of questions you can get. Either you could have a list, you could have a frequency table, and in the frequency table, either you have one it's a single number, or you will have one where you have a class. But pretty much the principle is the same across all of them. And I just hope you get used to using the formula, and that's pretty much it for that. So now we're going to move on to the next chapter, which is how we look at different measures of location. So things like quartiles and percentiles and all that lot of stuff. So like we said before, we've done the mean, the median, and the mode, but there's also other things like quartiles. And actually, the median is an example of a quartile. The median is actually known as the second quartile. So before we actually go through this, let's actually talk about what do we mean by the quartiles. So the best way to explain what quartiles are, so let's call this chapter Quartiles, is we should start with a line. This is our number line. And along this, we're going to mark somewhere roughly 25% across, 50% across, and 75% across. So this is 25%, this is 50%, this is 75%, 100, and 0%. So these are different locations within our data. So what quartiles and percentiles are about. So we'll start with quartiles first. So the quartiles tell you how far along the data that you actually are. So the thing that everyone knows as the median is actually known as the second quartile, and it means that it is 50% of the way through the data. That's why you always order it from smallest to biggest and go halfway through. But you don't always have to go halfway through. Sometimes you might only go 25% of the way through, in which case you're going to be known as the lower quartile. That's what we call Q1. That's when you only go 25% of the way in. And if you were to go all the way to 75%, well, we have another thing for that, known as the upper quartile. So this is known as Q3. And that tells you something where you are 3/4 away through a data set. And then here you'd have your lowest value, whatever the smallest value in your data set is, and this part here, which is at 100, would be your highest value. So somewhere in between your lowest and your highest value, you have a middle number, you have one which is 1/4 of the way and one which is 3/4 of the way. And the different quartiles are just telling you how far you are going through, in each of those values. So you could find, the 23rd quartile or something. Well, we don't really call them quartiles, but how much through you are. But we tend to say lower quartile, upper quartile, and the median. Those are the ones we're really interested in. Now, we also have something known as percentiles. So percentiles are quite easy to understand as well. So let's say I just chose a random number. So let's say rather than using a lower quartile, the percentile, if let's say I went 27%, then the 27th percentile is just 27% of the way through the data. Or if I had something which is like the 87th percentile, that's just 87% of the way through the data. And all this tells you is if I'm getting the 87th percentile, then it means that 87% of the values are less than this number. So if I chose a number and I found what this was for the 87th percentile, finding that would tell me that 87% of my values would be less than that. Same for 27. The 27th percentile tells me if I hit the 27th number, let's say this was 10, then 27% of the numbers are less than that. That's what percentiles tell you. So that's pretty much all there is to it. So just like how you know how to find what the median is, there's a simple way to find what the quartiles over there are. So we'll go through what each of these are. So if you want to find the lower quartile, you just have to do the total number of things divided by 4. And for the upper quartile, it's just 3/4 times n, so 3n/4. So n/4 would tell you what the lower quartile is, 3n/4 would tell you what the upper quartile is. And then obviously the median, we already know how to do that. So that's pretty much all you need to know for that. I guess the best thing to do now would be to look at an example. Actually, just before we do take a look at an example, one thing I would like to point out is when you do your median, you do n+1/2, which is something you'll be used to. But when you're doing the lower quartile and the upper quartile, just notice you don't have that 1 over there. So that doesn't actually come across. So, okay, let's come up with a bunch of numbers then and see how exactly does, this stuff work. So I'm just going to come up with a bunch of random numbers. 22, 24, 26, 28, 28, 28, 30, 32, 36, 37, 39, 42, 46, and 50. So I don't know how many numbers I put there, but we'll go through it. Let's say for, this set of data, we want to figure out, quite simply, what are the 3 quartiles? What is the lower quartile, the median, which is the second quartile, and the upper quartile, which is Q3. So let's start with this. How many numbers are there in total? What is n equal to? So we've got 1, 2, 3, 4, 5, 6, 7, 1, 2. So we've got 14 numbers in total. Okay, so let's start with the median since we're always familiar with it. So the median mean we do 14 plus 1 divided by 2, which means we have to get the 15/2, which is 7.5. Therefore, we need the 7th and the 8th values. So what is the 7th value? I've already ordered it on purpose. So 1, 2, 3, 4, 5, 6, 7. So 30 is our 7th value. What is our 8th value? That's 32. So you add them up, you get 62. So 62 divided by 2 gives you 31. That's our median. So that's okay there. That's our median, which makes sense. Looking at this data, 31 looks like it'd be pretty much, in fact, it is pretty much halfway through our data set. Now let's do Q1. So Q1 is pretty simple to do, actually. So we just simply do 14 divided by 4. And once you've done that, all you've got to do is, let's take a look at what that number is. 14 divided by 4 is 3.5. So now we've got 3.5. So what we're going to do, quite simply, we know that it's between the 3rd and the 4th values. So the 3rd and the 4th values into 3.5, which is 26 and 28. Same thing as before. Add them up, get 54. So divide that by 2, get 27. So our quartile 1 is 27. And finally, for the last one, 3 times n over 4. 14 times 3 is 42. So I'll just put that here actually. 14 times 3 over 4. So 42 divided by 4 gives us 10.5. So that means we need the 10th and the 11th number, since it's 10.5. And the 10th number would be, so 7, 8, 9, 10. So 37, 37, 39 are the two values. Add them up. So you get 69 plus 7, so you get 76, I believe. Divide that by 2 and you get 38. So your three quartiles are, that's Q1, that's Q2, and that's Q3. So it's pretty much as simple as that. All you need to do is find the value of n, which you can find by counting all the numbers you've got. Then to find Q1, you do n divided by 4, gives you which numbers to look at, figure that out. If that's not like 0.5, if it's just 3, then it's even easier. You just go to a third number. The median you always know how to do, just remember the +1, and Q1, Q2. Don't need the +1. For Q3, take your n, times it by 3, divide it by 4, and then again get the numbers, and it all works out just as you intend. So hopefully that's useful, and that will help you out. Next, what we're going to take a look at is, I mean, this is pretty simple to understand. It applies the same way if you're doing a frequency table. So we won't go over that because it's pretty much going over the exact same thing, but in a frequency table where the numbers are of this form, where it's like 10, 15, 20, and like 25, and like 1, 2, 3, like these are the frequencies, and like these are, you know, x values, then in that case, you just simply do the same thing. You find n the same way as you did, because you can sum up all the numbers over here and add these up, and then you do the same thing. You can find, you know, which class it falls in. Actually, there's no class, sorry, in this case. It's just straight up which numbers they are, and it's pretty much easy to do that. So nothing too tricky there. However, if I give you a different type of table, which is no longer that type of frequency, but it's like 10 to 15, 16 to 20, 21 to 25, then you actually need to learn a different method to do that. And this is one that you probably wouldn't have had to do at GCSEs, because this is new to A-levels. And that's a particular kind of question which I like to go through just to show you a trick you can use to do it. It makes it very easy to understand. And we'll just go through an example where we've got a question like that. So let's try that next. Okay, so here's an example of what I mean by group frequency. So we're going to use a technique known as interpolation to figure out the quartile stuff for this kind of question. So it's called interpolation. What we mean by that is we're going to assume that the data in each of these sets is evenly distributed. So what I mean by that is there's not like a bunch of like lots of 20s and there's a random 21, but I think the data is fairly evenly distributed. So you can see that the chances of something happening here are the same as the chances of happening here. So let's say there's a question here which we need to figure out what is the upper quartile for this set of data. And you'd want to follow these steps very carefully, and I'll show you one by one what you need to do. So to find Q3, the usual way, first thing we needed to know was the frequency. So we add up all these frequencies together. So 4 plus 29 is 33, 33 plus 32 is 65, 65 plus 15 is 80. Okay, so that's quite nice. We've got a nice round number there. So we'll put down 80 times 3 over 4 to find out which value we need to find. So this is how we normally find our quartiles. So 80 times 3 would give us 240, and 240 divided by 4 tells us we need the 60th value. Okay, now we're going to be very careful here. Where is the 60th value? So this would give us 4. This would get us to 33, because 4 plus 29, which means that our 60th value should be somewhere in this class over here, because if we've already got to 33, then if we add on 32, that'll take us 65. So that means there's somewhere in here. So now we know which class it is. So just based on that information alone, we're going to draw something like this. So let's put down the different numbers we get. So which class was it? We found out that the value was in this class. And what you need to do here, this is the part you have to be careful. Notice this doesn't take into account like 23.5 or values in between 23 and 24. That's because your groups here take that into account. So we don't write 24 or 26. What we actually write is 23.5 and 26.5 because those are the actual boundaries of our class. And we know that our number, which is quartile 3, is somewhere in between, but we don't know which one that is. And then at the bottom, what we're going to write is a cumulative frequency. So what I mean by that is, where are these two numbers? So this one here is just 4 plus 29. So we start off at 33. And if you then want to come to the other side, which is here, then you've got to add up all of these numbers. So that and that will tell you what that is. So that's 33 plus 32, which would give us 65. So this would be 65. And also we know that, our quartile 3 is the 60th one. So it's a lot closer to, even though I've drawn it like this, it's a lot closer to here than it is to here, but you can just put it in the middle for now. And now we're simply going to use the idea of ratios. So you want to follow this very carefully because you don't want to get this part wrong. So what we're going to say first is, as part of our calculations, is that Q3 subtract this number here. So this subtract this value here, 23.5 over the 26.5 minus 23.5. So what I've done here is I've got this value minus that, and on the top I've got this value minus that, is equal to, so this is where the ratio stuff comes into account. Now we do the same thing for the bottom part. So what we'll say here is 60 minus 33 over 65 minus 33. So that's what we do. So I know there's a lot of numbers which just, got down here, but let's actually look at what we did. It's quite simple. On this side, over here, I'll say do this value minus that value over this value minus that value. And then on the other side, I do the exact same thing. I do this value minus that value over this value minus that value. So the way you do it is you do this minus that, then this minus that, then this minus that, and then this over that. And that's how you get the ratio of how far along your thing should be. So like you can see, there's only one unknown in this situation. So in this case, what do I do? Well, let's just solve it. So Q3 minus 23.5 over 3 is equal to 27 over 32. So that means Q3 is equal to 27 over 32 times by 3 plus 23.5, whatever that turns out to. Let's put that into our calculator. So 27 divided by 32 times that by 3, and then add 23.5 would tell us that the value we get here is 26.03. So 26.03. So that is what your length would be. You can see that just about fits in for, you might be thinking that's 26 and it ends at 26, but remember it ends over here at 26.5. So that is actually within the values that we were expecting. So yeah, that's pretty much how you do that part there. So hopefully that was helpful. That's how you do Q3. Let's say, now that you understood that, let's actually get rid of the fact that's Q3 and let's actually talk about the percentile stuff that we've done, because percentile stuff is pretty much the same kind of thing. So let's actually figure out how we do that kind of thing over there. So for this, let's rub everything out. Let's rub that out and let's keep that line there since we'll need it. And let's just get rid of all of this. So now let's say I asked you, could you find me what the 10th percentile is? So, the upper quartile was the 75th percent. Now we're finding the 10th percentile. So just in case you get like a random number, which is not like your lower quartile, median, or the upper quartile, this is how you can do any number. So let's say I had to do the 10th percentile. So the 10th percentile would mean we need to be 10% of the way through our data. So how many sets of data do we actually have? I mean, what was n again? So it was 33, 65, and 80. So 10% of the way through would be 80 divided by 10, which is 8. So it means our eighth value. Eighth value falls between, well, 4, it's not going to be in there, it's going to be somewhere in this one over here. So that means we know what class we're in. We're in this class here this time. So let's get rid of that. Cool. So since we know that, we'll do the same stuff as before. So what did we do before? We need the 10th percentile, and you write it as P10. That's how you write the 10th percentile. And also now we have to see which class it was in. It was in 22 to 23, so this is 21.5. This is 23.5. Now, let's put the bottom stuff in. So again, these two parts here. So this here is 4 across, and this here is plus 29, so this is 33 across. So this would be 4, and this would be 33. And also we know our value, which we're looking for in the 10th percentile, is number 8. So now following the same equation we did before, we'd say P10 minus 21.5 over 23.5 minus 21.5 should equal to 8 minus 4 over 33 minus 8. So same thing as before, P10 minus that, 23.1 minus that, 8 minus 4, 33 minus that, and that pretty much is all you need to do, and that will give you the answer. So apologies, the video cut out for a little bit. So yeah, just picking up back at where we were, we said the answer for this one would just be solving this equation here. So that's what we've got over here. So let's solve that. So P10 is equal to 2 times 4 over 25, which is 8 over 25, plus 21.5. That will give us P10. So let's just put that into our calculator. 8 divided by 25, and then add on to that 21.5, giving us a final total of 21.82. So as we can see, our final value for P10, probably I would give that roughly as 21.8. That's the value, which is our 10th percentile. And that's pretty much it. So you can pretty much find any number you wanted, to be honest. The only thing I'd say is that, let's say I randomly said you have to do like the 72nd percentile for some reason. Then when you know you have 80 numbers, just times that by 72% to find out, you know, which two numbers you need to look in between. And that's pretty much it, to be honest. And yeah, that's one of the more, it's not very complicated, it's just a lot to follow. Just make sure you're very careful in that. And as long as you're careful, all the numbers should fall out. Should be fairly standard and should be a bunch of free marks in the exam. So now that we've looked at all that stuff, let's take a look at the last thing that we've got left before the main topic of standard deviation and whatnot. So that's something known as the range, the interquartile range and the percentile ranges. And you've actually done the hard work for this already by doing all the stuff up here. Because quite simply, the range is the difference between the biggest and the smallest values. So you just do the biggest value minus the smallest value. And that's it. That would give you what the range would be. And then if you wanted to find the interquartile range, which you call that as IQR, that also quite simply is just the difference between the upper quartile and the lower quartile. You know how to find both of these already from the stuff we did before. And if you subtract them from each other, you get the interquartile range. And the interpercentile range is simply the difference between the two percentiles are given. So let's say you're given, like, find me the difference between the 90th and the 10th percentiles. Then you just do the 90th percentile minus the 10th percentile, and that would be it. So you know how to find these values again from the stuff we've done before. You know how to find the 10th percentile or the other things using all this stuff you've learned up here. And I won't go through a question on this because, to be honest, the question boils down to, can you find these values and subtract them from each other? And you already know how to find those values, so it'll be quite easy. Again, the range is also quite easy. Biggest value minus smallest value. In this case, you just do 39 minus 20, and your range would be 19. We found what Q3 was before. You do the same thing to find Q1 and put together, you would get your final answer. You can normally expect questions like this. So they might give you like, find the interquartile range, because they want you to do what we did up here. They want you to do it twice and then find the difference. And that would make like for a nice question which has a lot of marks in it. Same for the interpercentile range stuff. So hopefully, yeah, that helps. And to be honest, that's all there is to it. These are known as measures of spread. So measures of spread, and that's what each of these three things are, your measures of spread. So hopefully, there's not really much to say there, so hopefully that's okay. Just make sure you're comfortable finding each of these values and you'll be good to go. Cool. So now let's actually move on to the more new and the slightly more exciting stuff in this chapter. Okay, so what we're going to take a look at in this chapter is something known as variance and standard deviation. So you'll be shown this the first time in stats during A-levels, something you probably haven't seen, and GCSEs. And just a disclaimer, the equation coming up might look like it, is scary, it's quite complicated because you haven't seen a lot of these signs before, but it's actually pretty easy to follow. And hopefully if I go through an example of, how you would make it work, it should be helpful. And I'll go to a bit of the theory as to like, what does the variance actually mean? Because a lot of people don't really understand what the variance is. They might be able to figure it out, but they're not always the best to understand, like, what does someone actually mean when they're saying, find the variance of this or find the variance of that. They're not very comfortable with that. So I kind of want to explain to you what the variance kind of is. So what is the variance? The variance basically is trying to tell you how the spread of the data is. So how much does it spread out from the mean value? And what I mean by that is the variance is trying to tell me that, or let me give you an example. Let's have a set of 4 numbers, 5, 5, 5, and 5. Or actually, for the sake of this example, 15, 15, 15, and 15. Then I'll choose the 7 numbers, 20, 10, 10, 20. And then finally I'll choose 30, 0, 0, 30. So if I averaged these numbers and found the mean, it would quite simply be 15. If I found the average of these numbers, it would actually also be 15. And also if I did this last set, it would also be 15. So you can see the average of all 3 of my sets of numbers is actually all 15. But the data you can see is quite different. It's spread out quite differently. And what I mean by the variance being how spread the data is from the mean, I mean, sorry, pardon the pun, if I have 15 as a mean, then 15 is pretty much on the dot with all of my other numbers here. But in this case, 20 is quite far away. It's plus 5. This is minus 5. This is minus 5. And this one's plus 5. So this one's a bit, the data, even though my spread is, my mean is 15, my variance will have some sort of number. So here you don't have any variance. Your variance would be 0. Here would be some number, but we'd have to figure out what it is. Let's say it's roughly 5. And then if you're taking a look at your variance over here, then 15 is 15 away from that, minus 15 from that, minus 15 from that, and plus 15 from that. So these values, even though the average is 15, are quite different to 15. Here they're a bit closer, but they're still a bit further away. And here, they're exactly on it. So what the variance is trying to tell you is going to be how far away are your numbers from your mean. So the higher your variance number, and I've just made these up here, but the higher variance number, so I'm just going to make up a number and let's say that's like 15. The higher your variance is, the more spread out your data is from the mean. So here you can see they're not very spread out from the mean. That's why the variance is 0. Here it's a little bit more spread out. So my variance is 5. And here my thing is very spread out. So it's 15. So even though they all have the same means, their variances are different. And that tells you how spread out each of these data points are. So hopefully that makes a little bit of sense in terms of what is the variance. So that's the theory behind it. And so if someone asks you what's the variance, you can simply say how far away each point in the data is from the mean. So now we're going to take a look at the equation for variance, and there are actually two versions of the variance, and then we'll take a look at what standard deviation is. Or actually, I'll just mention what that is now actually. So the standard deviation is actually just the square root of the variance. I might as well just say that now, just so you know, that's pretty much all you need to know in this chapter. So the standard deviation is the same as the square root of the variance. So normally what you do is you'd find the variance and then we just square root that and then we get a standard deviation. So yeah, what is the equation for the variance? Well, there's two equations. Let's take a look at the first one first. So the variance is given by the sum of x minus x bar squared. So x minus x bar is quite simply the x value, take away the mean that you figure out and you just square it. So that's pretty much it. The reason you square it is because if you remember before, we had like 5, or we had, what was it? We had 20, 10, 10, 20. You know how we were saying that the differences from 15 were plus 5, minus 5, minus 5, and like plus 5. They all add up to 0 because the minus 5s and the plus 5s go to 0. So sometimes you might be above the mean, sometimes you might be below the mean. So by squaring it, you can get rid of that negative sign here. So these would all be taken as like 25, 25, and 25 because you square each. That's why you have the squared there. So yeah, you have the sum of x minus x bar, which is a mean, all squared, divided by n. And that's actually all the variance is, but we can just break that down further because sometimes we don't have that information. So that's the same as saying find the sum of all the x's squared, divide that by n, and subtract the sum of x over n, which you'll recognize this is just a mean, all squared. So this part is just saying sum up or find all the x squared values, add them up, divide them by n, then find the mean, square the mean, and subtract that from whatever you found here. But don't worry, we'll go through an example. And we often write this whole thing as s subscript x over n. And what is s x actually equal to? So s x is equal to the sum of x minus x bar all squared, which is the same as saying x sum of x squared over n minus so x's squared minus n. So it's pretty much the same thing as saying that. So that's that's just what sx is equal to. So there's a lot to keep track of, and I'm sure that it seems quite scary at the moment because, as you know, there's a bunch of different numbers and whatnot over here. Or there are no numbers, it's just a bunch of symbols, and you're probably thinking, do I remember this one, this one, this one, or like what do I have to remember here? But don't worry, I'll go through the questions and show you which ones of these you'll use. Just depending on what data you're given, either you'll use like this one or you'll use this one over here. But if you think of it as only really two equations, it's this one and this one. So let's these are the different ways you could write the formula actually. So you know, so there are two ways. There's actually three. This is one, this is the second, this is like the third. You can write it depending on what data you're given. So sometimes you can actually use your calculator to find that quite easily. And it's just, it's quite simply just finding this over here. Or you could use this, or you could use this. But yeah, this is the first part of the equation, this is the second, this is the third. Once you found it, and if you square root it, that will give you the standard deviation. So just so you know, another thing is the variance, we call this a variance. That's the symbol for the variance. So if someone tells you to find the standard deviation, that's the symbol for standard deviation. So yeah, kind of to summarize what we've just said is, yeah, these are your three equations, and then this is your standard deviation, which is square root. And I think the best way to go forwards from here would be just to give you an example, the same we did before, how you do it with a list of numbers, how you do it in a frequency table, or something like that, and how you might do it in a grouped frequency table, which is something like that. So I'll give you these 3 examples for how to find the variance and the standard deviation. And hopefully that will get you a lot more familiar with the equations that we have, because with the group frequency stuff, as you can imagine, we'll be putting a bunch of, F's everywhere and stuff like that. So it won't be too bad, but try and keep up with the examples. So, okay, let's actually go through and try how to do this. So the first type of question we'll do will be with a simple set of numbers. So let's say 4, 6, 8, 8, 5, 6. So let's say you've got this list of numbers and someone told you, I want you to find the standard deviation of this. So in order to do that, first we'll start off by trying to find the sum of x. That's the first way you'll start off with. So what is the sum of x? The sum of x is equal to 4 plus 8 plus 6 plus 8 plus 5 plus 6, or whatever that is. So this is 10, 18, 26, 31, 37. So our sum of x is 37. Hopefully I got that one right. There's no silly mistakes. But yeah, so we've got 37. So the next thing we want to figure out is what is the sum of x squared. Now be careful here. You can't just square that to get this value here. That's not how it works. What you have to do instead is the sum of x squared means first find x squared and then sum them up. So that means 4 squared plus 6 squared plus 8 squared plus 8 squared and so on. So 4 squared plus 6 squared, 8 squared plus 8 squared, 5 squared plus 6 squared would give us something. So this is equal to 16 plus 36 plus 64 plus 64 plus 25 plus 36. So if I just pop all of that into my calculator, 16 plus 36 plus 64 plus 64 plus 25 plus 36, that's 241. Cool. Now we know what x squared is. So like we said with how do we find the variance, we had the equation before, which was this one here. Sum of x squared over n minus the sum of x over n squared. That was it. So if you just pop in the numbers, we know what the sum of x squared is. That's 241. We know what n is because we just count up how many numbers we have. So 1, 2, 3, 4, 5, 6. Minus, and this is just a mean. So the sum of x, like we did before, 37 over 6 numbers, all squared. And that's it. That will give you what your your variance is in this question over here. So if I were to do that, calculator 241 divided by 6 is about 40.12. 40.17, my bad. Subtract 37 over 6 and then times that by itself is about 38, so minus 38. So looking at that, we get 2.17 as our variance. And so our variance is 2.17 and the standard deviation is just 2.17 square rooted, whatever that would give you. And yeah, I mean, whatever that gives you would be the answer to this one over here. I guess I might as well just do that. So 2.17 in my calculator, that's about 1.47. And that's it. When you have a set of numbers, the easiest way to do this would be to use this equation here. Find sum of x squared, find the sum of x. N is easy to find, and like you can see, you quite simply just pop in the numbers and everything falls out. So hopefully it seems a little bit less scary now. What did we do? We found the sum of x, found the sum of x squared, and remember the way we did it. We didn't just square this number here, but no, we squared each of these numbers and then added them up. If I said the sum of 3x, then what you do is you do 3 times that, 3 times that, 3 times that, and you'd just add up all of these numbers with each other. That's what you do. So the thing inside the sum, like if it's 3x plus 2, just tells you what to do to each number, and then you do that to every number and then just add them up. So 3x plus 2 means you do 3 times 4 plus 2, do 3 times 6 plus 2, and so on. That's how you can work with sums. But yeah, when it's a simple list of numbers just like that, then pretty much that's it. That's all you need to know. So from that, let's actually move on to doing frequency tables where the numbers are fixed. So for something like that, the variance is actually equal to, it's a similar thing to what we did before, but now I'm just going to put a bunch of f values in for frequency. So f, and what I'll do actually is I'll put them in red to show you the difference, because you can see all I've added is a bunch of x's. Everything in black is the same as what you would have done before. So this will be the sum of fx over here. Sorry, not sum of x, sum of f. Then just trying to remember what it was. It's equal to the sum of f squared, sum of f minus, oops, just put that in red, x over sum of f. And oh yeah, I should probably put that in red, sum of f, sum of f over there, then that's in brackets squared. So it's pretty much the same equation as before. It's just I've got, instead of all the, I've just added, instead of n, I've got sum of f, and then I've added a few f's on the top. But that's the equation that I would use for doing the variance in your tables. And then again, the standard deviation is literally just, this is literally just equal to all of that square rooted. So I think the best way to do this would be to probably just do another example. So let's do the usual thing. Let's say length, let's say frequency, and let's just put a bunch of lengths in. So 25, 26, 27, 28. And let's put in a bunch of frequencies. So like 4, 18, 25, and 30. So these are your values. So if you had a table like this, then it's pretty simple again. So you start off by finding the sum of fx squared before you started off by finding the sum of, fx. So you can also do that actually, but it doesn't matter which order you want to do it in. So actually, let's do that. Let's stick to what we did before. Before, we found the sum of x. Now we'll find the sum of fx, because your frequency table, that's quite simple. You just multiply each of these values and then add up what you get. So sum of fx, and I'll write that out in full. It's 25 times 4. You can see how I got that just from there. Plus 26 times 18, plus 27 times 25, plus 28 times 30. Whatever that comes out to. So let's just put all of those into our calculator once again. 25 times 4 is 100, plus 26 times 18, which is 468, plus 27 times 25, which is 675, plus 28 times 30, which is 840. So if you add that all up into your calculator, you get 100 plus 468 plus 675 plus 840, which is 2083. Cool. That's the sum of fx. So in our equation that we're going to use, we found this part here. Sum of f is quite easy, so we might as well also do that. The sum of f, put that here on the side, is just 4 plus 18 plus 25 plus 30. So that plus that is 22, plus that is 47 and 77. So that's what we should get over there. That's our sum of frequencies. So we found that one, we know that one. What does that leave us with? Just this one here. So how do we find the sum of fx squared? So that's also quite simple to do. So x, remember, is this part over here. So we have to do 25 squared. So you do 25 squared times 4, 26 squared times 18, 27 squared times that, and that times that. So it's quite easy. If you imagine what we wrote here, it's actually the same thing. So I could even copy all of that. it's the same thing as that, but the only difference now is the x's are squared. So instead of doing fx, like you can see here we did, this is the x, this is the f. Now since x is squared, that's just squared. So this becomes just 25 squared, 26 squared, 27 squared, 28 squared. And yeah, it's a bit of a headache because you have to actually calculate these values and there will be some huge numbers, but don't be worried, it doesn't mean you're wrong. That's just how you do it. So times that first one gives you 2500. 26 times 26 times 18 give you 12,168 plus 27 times 27 times 25, which is 18,225 plus 28 plus 28, or times 28 times 30, which is 23520. Cool. So now let's just add all of those up. 2500 plus 12168 plus 1, can't tell what that is now, but I guess it was an 8. 18225 plus 23520. So that gives us 56413. So what you can see now is that it is quite a big number, but don't worry about that. Like that's pretty much what it should be. So now you just simply put it into the equation that you knew before. So the sum of fx squared was this value we just got. So our variance is quite simply 56413 over the sum of our f's, which was 77, minus, in brackets all squared, that sum there, and 2083 there. And then I won't put that into my calculator for now, but whatever you get for this in your calculator would give you your variance, and then if you square rooted that, you would get your standard deviation. And that's pretty much how you do this kind of question when you're trying to solve it for a fixed frequency table. Now, for the very last one, it's the kind of table where you have classes, and I won't step through the whole thing because it's actually pretty much the same as the equation is the same. It's just that when you have classes, so let's say I had like 10 to 15, then 16 to 20, and then I don't know, 21 to 23 or something like that, then, and you have some frequencies. This is pretty much the same as what you did before, but instead of taking 10 to 15, you need to find the midpoint. So your f or your x values would just be the midpoints. So what I mean by that is, or let's not do it like this, let's just say, let's do it in a different color. So let's say in green. So the midpoint of this one would be 12.5. The midpoint of this one would be 18, and the midpoint of this would be 22. So you kind of find the midpoints, and then you just kind of use those as your values. So I use 12.5, 18, 22, then 10, 15, and then 20. That's it. And then you do the same thing as you did above, and then you can find your variance and standard deviation. So the only key thing is you need to find the midpoint of the table, and once you found the midpoint, then you're pretty much done. That's all you need to do. And then you can do the same thing. So sum of f's would be like 10 plus 15 plus 20, which is 45. Sum of fx would be 12.5 times 10, 12.5 times 10 plus 18 times 15 plus 22 times 20, and then the sum of fx squared would just be 12.5 squared times 10 plus so on, like you know the rest, and then you put that into your equation like before, and that's pretty much it for standard deviation and the variance. And so you can see it's not so bad, even though there's lots of equations. To be honest, the only ones we really tended to use, if I go back a little bit, would be this one over here. So we've used this one here and the same one for the fx stuff. So don't worry about the sx stuff at the moment. I'll go through a few questions and stuff later where you can use that. But normally what you'll be given in the questions that you'll do when you're solving standard deviation is pretty much just, you might just be given these straight up, which is great. You can just put them in the equation. Otherwise, they'll give you the table. And from that table, you need to figure out. But if you've got the information, then it's very, very easy to do. So my tip would be write out this equation. Either you've got these numbers or they're given in a table, and figure them out, put them in, and should be okay. It's a little bit fiddly, but you'll get used to it with a couple of exercises. So hopefully that was useful. Cool. So now that's done, we're going to move on to something which is called coding, and that's the final part of this chapter. Okay, so when it comes to coding, a lot of people tend to find this quite difficult as a topic, but it's not a very long topic, and there's a few examples we can go through. Two different examples to hopefully help you figure out how it works. But I'll try to explain you just like I did with variation and standard deviation, like what is the actual idea behind coding? And you can learn how to do it, but why do we actually do it in the first place? So coding is kind of like this concept where, let's say I had a set of data, right? And let's say my data was huge. Let's say I had like things where I had a lot of numbers which are huge, and then I wanted to find something about these numbers. To find these numbers, I'd have to do a lot of computation, let's say, because let's say these are millions of digits long or something. That's very hard. And that might give me some sort of, final answer for some sort of mean. But then rather than spend the whole time to figure out and crunch these numbers and, go through a lot of pain because they're very big and very difficult to work with, why don't I just code them into something easier? So your code, using this code, make it into something easier. So maybe turn this into 15, 16, 18. And then from that, I can find a coded mean. And then from my coded mean, I can just convert back to my original mean. So what's happened here? So I had some data which is really complex and really hard to work with, or took up a lot of space in my computers, let's say, or just very hard to work with in general. Then I came up with some sort of code which made it easier and converted it into its translated form. And now since I found the coded mean of this easier form, I could then convert that coded mean to find the original mean of my data. So what I've done from here is just use a code, simply found a new set of numbers, got the coded mean, and then found my original mean. So that means I hadn't had to go through the pain of crunching this, and I can actually instead do it through computing the same stuff on an easier set of numbers. That's kind of the idea behind coding in a sense. The key thing here is that when you do code your values from here to here, this code doesn't lose information, because if you lose information, then you can't really convert back into the original. So this code needs to preserve all the information, get your coded mean, and get your original mean back. But that is kind of the idea behind how coding works. That's why you do coding, because a lot of books don't really mention why you do it. They just tell you what the equations are, and a lot of people tell me like, cool, but don't get it in the first place, and why do I do it? So this is why you do it. So just going down, let's actually take a look at what is the equation for a coding. So when you want to code your values, it's y equals x minus a over b. So let's talk about what are these actual values. So the y values are basically going to be your new coded values. So your original data set, well, this will be from your original data. The x values are from that. You put that into your original data, and then a and b are just set parameters. They're just numbers which are usually given. So they'll tell you what like a and b are. So to basically code your data, if I gave you like 10, 15, and 20, and so let's say a and b were like some numbers, then I just put in 10 into here, then minus a over b. That would give me my value of y. That would give you your coded value of y from there. So something like that. But if we're doing an example, that would make a lot more sense. But this is the equation. It's just x minus a over b. That gives you new values. And then the mean of your coded data is just given by the mean of your original data minus a over b. So the idea is that I use this formula to turn every single number into a coded set of numbers. Then I find the mean of that coded set of numbers to give me this. And then since I know a and b, because they're the same a and b as here, I can just rearrange this formula to find the true mean from the actual thing. So that's pretty much how you do that. So that's how you can find the mean. And also you can also find the standard deviation of the coded data. So the standard deviation of y, the same way as we have the stuff here, or the mean of y here, the standard deviation of that data is just equal to the standard deviation of the original data over b. So if you know what this is, just divide, times it by b, and that gives you the standard deviation of your original data. So these are your equations. I just remember this one, and this one. And let's actually just use an example, because that's the best way to to understand how this works. So go into a new page. Let's say I have some numbers, 232, 255, 206, 217, and 240. So these are some common examples which are often given in textbooks and stuff like that. So you're sure to follow any examples which you've got. So if these are your numbers and then I give you the coding, let's say my coding is x minus 200 divided by 10 is the coding that I have given you to use, then quite simply what you do is to find the coding of this data, you just put them in. So you put in these values all into there, and then you'll get it. So what's the first one is 232 minus 200 over 10. So that gives you 32 over 10. So that gives you 3.2 and so on. So if I do that for all these numbers, I get 5.5. I get 6 over 10, that's 0.6, 1.7, and 4.0. So that's my coded data. So now that I've got that, we'll say, can we use that to find the mean and the standard deviation of the coded data? So for the coded data itself, if you were to add up all of these numbers, let's start off by trying to find the mean. So the mean is just the sum of x over n. In this case, the sum of x is 3.2, so 5.5, plus 0.6, plus 1.7, plus 4.0, all over, well, there's only 5 numbers in total. So if you do that into your calculator, again, it would seem we've got 3.2, 5.5 is 8.8, 9.4, 11 point, let's make sure I've done this right. So 3.3, 1.7, 4.0 should turn out to give you a total of 15, it would seem. Let's just try that out, calculator. 3.2 plus 5.5 plus 0.6 plus 1.7 plus 4, yeah, 15 over 5 gives us 3. So our coded value, our coded mean is 3. Now, can we find out what our coded standard deviation is? So that's what the question wants us to know. What is the standard deviation? Well, for that, we know that we always start by finding the variance of the data. So since this is what we've got to work with, how do we find the variance? Well, same thing as before. We said you find the sum of x, which we knew is 15, or let's call it, since we're finding the coded data, I think it's better to call these values x, since the original values is to call them y. So the sum of y is 15. What is the sum of y squared? Let's just quickly figure that out. So it's 3.2 squared plus 5.5 squared, and so on. So doing that would give us a total of 59.74 for all of the data that we've got over here. And so you just put that into the equation. So putting that in the equation, we get 59.74 over 5 minus 15 over 5, which we already did above, all squared, which will give you a total value of 2.948. That's what you're going to get. So that's the value of your variance. Just remember, because people tend to find the variance and forget to square root of a standard deviation as the last step. So just remember, you have to square root this now. And that gives you a standard deviation of 1.72. So that's how you can find your coded one. But now that we found this, we want to use our coded mean. So I'll put these in green, and the coded standard deviation to find the original data's value. So for the original data, we said the equation was y bar was equal to x bar minus a over b. So we just put the numbers in that we know. So y bar is the coded mean, which is 3, is equal to x bar, which is the original mean, which we want to figure out. A, like we know from before, is just 300. B was just 10. So we get 30 is equal to x bar minus, 200 was it? That's 200, and 230 is equal to x bar. So that's how you find that. And at the same time, we wanted to find the standard deviation. How are you going to do that? Well, we know that this was the equation we're working with. So what is standard deviation y? It's 1.72. Standard deviation x, no clue. Divided by 10. So standard deviation of the original data is just 17.2. 10 times 1.72. And that's it. That's all you need to do to find the coded values. So hopefully that was okay. What we did was we just found what the code was first. So we found the new set of numbers, found the mean and standard deviation for these, and then using this method here and this one here, we just put in the values we knew, and that gave us the new value here. Put in the values we knew, gave us the standard deviation there. And that was pretty much all we had to do there. So it'll be worth just going through perhaps one more example, because sometimes you're not just going to be given like the numbers, sometimes you're going to be given these actual values themselves, if you know. So you're not going to be given the numbers, and it's a good way for us to show you how to use like SXX and stuff like that. So let's say you have some code, and the code is given by, the code for H is g minus 5 over 10. So it's the same example that many people often have in their books, and I'll just try and explain that. So, and they've given you the SHH is equal to 43.58. They've said that H bar is equal to 2, and they've said that N is 61. So this is probably the same example you've got, and I just want to explain how that works. So when you've got this, let's say they want you to find the mean and the standard deviation from this data. So in order to do that, it's a lot easier than the last one actually, you don't have to do much working out. We know that the coded mean is given over here. So we can just say 2 is equal to the original mean of the data that we can get. So the original data will be whatever that is, the mean of the original data, minus 5 over 10. So therefore, if we do this, we get 20 plus 5. So the mean of the original data must equal to 25. That was it. Quite easy to do that, not very difficult. And now let's also use this data to figure out the standard deviation. So if you remember from before, we said the standard deviation was the square root of the variance, and the variance was SXX over N. So here all you actually have to do, since we have SHH, so let's put that in, is 43.58 divided by N, just all square rooted, and that gives you 0.845. The equation told us that the coded standard deviation is equal to the original standard deviation divided by B. So we have all those values here again. This one here is 0.845. We don't know the original value, and divided that by B, which in this case was 10, tells us that the standard deviation for the original stuff compared to the coded one was 8.45. And that is pretty much all you need to do. And that's how you can answer this question if you've got this stuff here. It's very easy if you've got that. It's literally just like plug and play. You just put in the numbers which you need, and everything just works out. So this is a coded mean, so that goes here. You've got A and B, that's the original value. Just remember what the different things mean, but that's kind of how you follow through it. So hopefully coding is also quite easy. So this is quite a long chapter. There's quite a lot of calculations we had to do and whatnot, but hopefully that made more sense to everyone. And if there's anything you're not sure about, if there's any exercises you're stuck with, just let me know which ones those are in the comments below. Or if this video was helpful, it's very nice if you could, comment, subscribe and like on these videos and the channel, just because it makes it a lot easier for me to create more videos if I know a lot more people are watching it. So yeah, that would be very helpful. And just share these with anyone you know who's stuck, because I'm pretty sure there's not much like this out there on YouTube, which is very specific to the courses that people do in A levels. And I wanted to kind of go through the chapters that teachers don't really explain that well. So I'm trying to go through all the chapters, explaining every single example and exercise and every type of question that you can expect to have. And then once I've finished the series, I'll move on to just doing purely questions and how to answer every type of question from the different exercises. But in the meantime, just share these around with your friends. And yeah, I'll see you in the next video. So welcome back to another video in our statistics series. So today we're going to be taking a look at data representation, and this chapter is probably one of the easiest chapters out of everything year one stats. And that's probably because a lot of the stuff you're going to take a look at here, you would have touched upon somewhat in your GCSEs. So let's just go straight into it. So what are we going to be taking a look at in this chapter? So in this chapter, we'll be taking a look at how we can figure out what is an outlier and what actually outliers mean. We'll take a look at how you can plot box plots, cumulative frequency diagrams, histograms, and then finally, after learning about all these three different ways of representing your data, we'll look at how you can compare these different data sets together. So going on to the first thing. So the first thing we need to take a look at are what are outliers and what are anomalies. So you've probably heard these words in just like general speak and context, but in stats, they tend to have very specific meaning. So an outlier, if you had to talk about it in general terms, that's usually like an extreme value, and that's not really lying inside the pattern of your overall data. So imagine I had like a bunch of ages, right? Let's say I had let's say I was just checking the heights of different people. So let's say I'd have someone who's 150 centimeters tall, 160, 180. Let's say someone was 170, 150, and so on. And then suddenly I had a value which was like 230. So in general, these values are quite close to each other. But then this one seems particularly larger than the rest. So you can see the biggest difference between all of these numbers, between the largest and smallest, is probably 180, 150 here. So there's only a spread of about 30. But this one over here is much, much larger. So depending on how large this is, if it's too large, then in different cases, you would call this an anomaly. So for example, let's add another one who's 350 instead of 230. Well, in this case, what would end up happening is we'd say, well, this one probably is an anomaly because it's so far from the other piece of data. So essentially that's, and also, yeah, we'd consider that as an outlier basically. So that's essentially what we've got here. Now, sometimes you might have outliers from your data, but it doesn't necessarily mean that it's not part of your data. Sometimes it might genuinely be that you actually have got someone who's 350, but we'll talk a little bit more about that after we've discussed the definition for an outlier. So hopefully that makes sense. So essentially you have a pattern of data, and if something is either too low or too high compared to that data, then you call it an outlier. And sometimes if you consider this data point, which is outside, or this one over here to be wrong, you normally call that an anomaly and you get rid of it. So let's talk about the statistical definition of what an outlier is. So there's different ways you can define it depending on different values, but the way that we do it in stats is usually if you take your third quartile and you add on k lots of the interquartile range, so that's Q3 minus Q1, then anything which is going to be more than that is considered an outlier. And anything is if you take your lower quartile and you take away k lots of the interquartile range, that's also considered an anomaly. So just to explain to you what this looks like on a graph is something like this. So let's say we have a box plot like that. Or before that, actually, let's actually have an even easier example. Let's say I've got a line like that. This is Q3, or this is actually Q1. This is Q3, this is Q2. So what I'm trying to say is that anything which is k times the interquartile range more than Q3 is an anomaly. So I have a tolerance of this much. Anything which is within that is okay, but anything which is more than that would not be good. Same thing from Q1. The only difference is this I'm going down. So we care about minus lots of that. So k Q3 minus Q1 lots. Anything over here is okay, but anything which is beyond that is bad. So basically we have a tolerance level between the two different parts that we have. So anything like that would be considered an outlier. And sometimes, just coming back to what anomalies are, there's sometimes that we find our data has outliers. So let's say this is my data, and I found that this is everything which is fine, and then these are the points, let's say, which happen to classify as outliers. Now, sometimes what happens is that if I were to include these data sets or these data points in my calculations, since they're outliers, they might skew my data or they might give me misleading results. So sometimes your outliers can be considered anomalies, and the ones which you get rid of or data points which make your outcome misleading, they're called anomalies, and you tend to get rid of them. So you wouldn't actually include any of these if you're doing that. But you have to be careful as to what actually is an anomaly, because sometimes outliers are genuine values which could be correct. So, if I was doing heights, there really could be someone who's like 230, let's say. So sometimes you don't want to take it out, and that depends on, kind of experiment you're doing or what you're trying to figure out. That's like one of the questions you have to solve in stats. But in A-levels, you won't have to worry about that. They'll usually tell you what's considered an outlier and whether to get rid of it or not. So since we've done all this talking about this equation here, it would probably be a good idea to go through an example of actually how we use this equation. So moving on, let's take a look at our first example. So here we have a set of numbers. So let's see how many numbers we actually have in total first. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers in total. So let's just write that down. We've got 12 numbers. That'll be useful to know. And basically, we're going to be given what the outliers are. And I know that last time we wrote the equation as being k lots of q3 minus q1. The thing is, k will normally be given to you in your A-levels. You don't actually have to work out a value of k. So you're normally going to be given that. So let's say we're given the set of numbers, and the definition is that here, your outlier is plus or minus 1.5 times the interquartile range. I'm just using that because that's the same thing as q3 minus q1. I can't even bother to write that out. And from q3 and q1. So it's just basically saying it's these two here. So let's take a look at what our answer should be for this. So how do we start this? Well, the first thing you want to do is you want to figure out what your q3 and q1 values actually are for this one over here. So to do that, we need to figure out how many data points you have in total, which is 12. Great. So let's do q1 first. So we now have 12 data points, and we know to find the lower quartile, divide that by 4, which gives us the third value. So the third value, if you just look along, would be number 5 over here. That's our third value. So that means 5 is our lower quartile. Now let's find the upper quartile. So this will be 12 times 3 divided by 4, which is 36 divided by 4, which is the 9th number. So the 9th number along would be 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 13. So let's mark that down as our upper quartile. Cool. So now we have our two quartiles. Now, according to our equation, what we said was the outliers were anything which were plus or minus 1.5 times the interquartile range. So let's do that here. For anything to be an outlier from Q1, it has to be 1.5 times the interquartile range, which we know that now. We can write interquartile range as being the 9th number was 13. So interquartile range is 13 minus 5, which gives us 8. So anything which is 1.5 times 8, and then our lower quartile is 1. So we do 5 minus 1.5 times 8, just following from this equation over here. This over here, we found that to be 5. That's given us 1.5, and we just found the interquartile range of this whole thing was 8. So coming back to here, that's what we get. So if we were to solve that, this goes to 5 minus 8 times 1.5 is 12. So our lower quartile gives us a number of minus 7. So if you had any numbers which are minus 7, then those would be, or anything less than minus 7, that would be an outlier. But you can see in this data, we don't actually have anything which is less than minus 7, which is completely fine. That means we have no outliers on the left-hand side over here. Let's try that for the other side, on this upper one over here. So the upper quartile is 13. So 13 plus 1.5 times 8 gives us 13 plus 12, which is 25. So here we can see that nothing is more than 25. So actually there are no outliers in the data set. Everything is fine in this data set according to this definition. Let's say I had randomly added on like a number which is like 48. What I might have ended up doing is it would change your interquartile range and the other values, but probably the value which is the upper one here wouldn't be 25. It could have been something like 27 maybe. But then what ends up happening is this number would have fell outside it. So in this case, we have no outliers, but anything which is less than 7 or more than 25 is considered an outlier, and you just have to check if there are any outliers in there. So that's pretty much all you actually have to do for a question like that. So these are quite simple to follow. It's just essentially you've got to find the interquartile range. So before that you have Q1, find Q3, find the interquartile range, put it into these two equations, get these two numbers, and then you check if anything satisfies that. So is it anything which is less than what it should be or more than what it should be? So that's the first type of question you can get for stuff like this. Now let's take a look at the other type of question you can get. Okay, so for this next question, again, you can see we've been given a set of numbers over here. And this time we've been given some information about the sum of x, which means what happens if I add up all of these numbers, and the sum of x squared, which is what happens if I square all these numbers and then add them up. So that's what we've been given. And the first part of the question would like us to find the mean and the standard deviation. So this is actually just following on from the stuff we've done in chapter 2 before. So this was actually quite simple. So to find the mean, we quite simply have to do the sum of x divided by n. So we already know the sum of x, that's 148. And how many numbers do we have in total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 again. So we do 148 divided by 12. So if we put that into our calculator, that gives us a value of 12.3 recurring. So we'll just write 12.333 for now. And then the standard deviation, we also just follow the usual thing that we did. So we find the variance first, and we square root it. So the equation for our variance was the sum of x squared divided by n, subtract the mean squared, or if you prefer to write, I could have just written this thing here squared, but it's the same as the mean squared. And that will give us the variance. So if you do that, we put 2362 divided by 12 minus 12.333 all squared. Or actually, just for the sake of accuracy, let's actually write that as 148 over 12 all squared. Rather than use that, I'll just use the fractional form of that. But anyways, putting that into our calculator, we get 2362 divided by 12 minus 148 over 12 squared. That gives you 44.72. So that's what our variance there for your standard deviation is, the square root of that. So if I were to square root the answer, we get 6.69. So that's going to be your standard deviation. So that part of the question is quite simple. So the next part of the question says, an outlier is plus or minus 2 standard deviations from the mean. So this one's actually easier to understand. So this one's actually using the equations we learned before, but it's giving us a new way of finding the outlier. So all you have to do is just pretty much follow this. So 2 standard deviations away from the mean. Well, the mean is 12.33. Let's say that. If I add on 2 lots of the standard deviation, so the standard deviation was 6.69, so 2 lots of 6.69, that will give me the upper bound. And let's just move that into the center. And if I did 12.33 minus 2 lots of 6.69, that would give you the lower bound of your thing, just according to what the questions told me. So for part A, you do that. This is what you do for part B. 12.33 plus 2 lots of 6.69 gives us a total of 25.71. And 12.33 minus that gives us a total of minus 1.05. So anything which is more than this would be an outlier. Anything less than that would be an outlier. So let's compare that to our data. So again, in the lower bound, there's nothing which is less than minus 1.05. So everything here is okay. But as you can see, this value of 30 is more than 25.71. So all of these values are fine. But then since our upper bound is 25.71, anything more than that is bad. So you can see here that 30 is more than that. So 30 is considered to be an outlier. And that's pretty much all there is to it. So when it comes to outlier questions, it's usually quite simple. It's either you find the mean, the standard deviation, and you do this kind of way, or you have something like the previous question where you use interquartile range and just use the equation that you learned before. And normally we're given a list of numbers or some data that you can use to find it. And it's pretty much as simple as that. So hopefully there wasn't anything too hard there. And let's take a look at the next part in this chapter. Okay, so now we've moved on to box plots, and box plots is something that people are quite used to from GCSEs. So I'll just go over the basics. There's not too much to actually go over for box plots. In general, when you draw a box plot, you'll have some piece of graph paper, and you'll tend to just have to draw. If we just draw out a random box plot, it'll look something like this, something like that. And then these different lines will, there'll be different sizes. So this might be further out, this might have been in the middle, this could be further out, and so on. But this is generally what your box plot looks like. And you usually have some sort of scale down here. So this might be something like 0, 10, 20, 30, 40, and so on. And then you can just read off the different values of what you're looking for based on the box plot. So what do the different lines actually mean? So basically, when you're doing this here, this is considered your lowest value. That's this line here. This one here is considered your Q1, otherwise known as your lower quartile. This middle line here is Q2, otherwise known as a median. And this one here is just Q3, which is the upper quartile. And then you can probably guess that this one over here is just the highest value in your data set. And that's it. So if you had to draw a box plot, all you had to do was find out what each of these are, and then just literally draw the lines on the graph, and then you just join them up like that. So anything between Q1 and Q3 you have to draw as a box. Once you've drawn the box, just draw the median inside it, then draw your two highest and lowest values, and then just join them up with a line like that. And that's pretty much all you have to do for that. If you were to have an outlier, the way you'd represent that on these graphs would be something like an X outside, and then this over here would be an outlier. And likewise, you could also have it on this side. So basically, this is kind of how you can represent your data. And that's pretty much it, actually. And normally you can compare different sets of data with different box plots. So if I just gave an example of what I meant by that is, let's say comparing to that, I had another box plot, which was something like this. Let's say this is the other box plot I had to compare. Normally when they ask you questions about comparison of box plots, what you tend to say is you want to talk about the medians and how they compare, and then you want to talk about interquartile ranges and how they compare. So normally if I had to compare, like, let's say I call this A, I call that B, what I would say is A has a higher median than B. So if these were like the heights of boys and girls in a class, let's say that A is boys and B is girls, then I say the median height of boys is higher than the median height of girls, which shows that generally they're taller than them. However, the interquartile range of boys is much higher than the interquartile range of the girls. Hence, the spread of heights of the boys is much higher than the spread of heights of the girls. Something like that. So that's kind of how you compare two sets of box plots usually. But before that, let's just see if you had a question like this, how would you draw your box plots and how would you do questions on here? These ones are quite simple, so there's nothing too much to do. So basically, when you have a question like this one over here, then all you need to do is you take your data set. So normally you won't get it like this. What will happen is you might have like a set of numbers like this again, like 1, 5, 4, 6, blah, 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 like, and so on. And based on all of that, what you should do is just use all the normal stuff to actually find this stuff here. So find the lower quartile, upper quartile, and stuff like that. But let's just assume in this question that you've already found all of that from your data set and you've got all of these. Then quite simply, all you really need to do is, to be honest, you just draw this on your graph. But I think the best way to do this will be, let's actually draw it to scale somewhat. So let's say every 2 is equal to 5. So 1, 2, 3, 4, 5. Let's draw an extra bit on for that. So let's say it starts from 0, 1, 2, 3, 4, 5, and 6. So we know our lower quartile is 3.5. So our lower quartile would be somewhere here. We know our upper quartile is 4.9, which is somewhere here. So we can draw that box. So we've done that. We've done that. We know the median's 4.1, which is somewhere there. And we can take that off. The lowest value is 1.5, somewhere over here, and the highest is 5.1, which is somewhere over here. And then you just connect those up. And there you go. You have your box plot. Now, let's say I had some values these came from, right? So this won't be the exact values they came from, but let's say they came from like 2, 3, 6, 7, 10, like 1. Let's just say some random values from that. It's not, these values won't match up with these numbers, but just to make an example. So it says an outlier is 1.5 times the interquartile range from Q1 to Q3. So the interquartile range for this question is just Q3 minus Q1, which is just 4.9 minus 3.5, which is 1.4. So my outliers should be 1.4 plus 1.5 times, the interquartile range. That should be what's my lower quartile is 3.5. Take away 1.4, which is interquartile range, times 1.5, which is my k value. And my upper quartile is 4.9, so plus 1.4 times 1.5. And these two will give me my different ranges which are allowed. So 3.5 minus 1.4 times 1.5 is 1.4. And if I do 4.9 plus that, get 7. So anything which is less than 1.4 is bad, and anything which is more than 7 is bad. So if it happened to come from this data set, this is less than 1.4, so on this side, this is bad, as that's an outlier. Anything which is more than 7, so 7's okay, it's on the dot, but then 10 is too high. So these are the two outliers in the data set, if that's where these numbers came from. And that's pretty much how you answer these kinds of questions over there. And that's pretty much it. So box plots are usually quite easy to understand, and normally what happens is when you draw the box plot, they'll give you another box plot and be like, can you compare the two? In which case you'll just do what we talked about here. You'll compare the medians and say this median is bigger or smaller, or larger and fewer, and then you have the two interquartile ranges which you compare, and that is pretty much all you need to know for box plots. So moving on from box plots now, let's take a look at cumulative frequency. So cumulative frequency is another thing that you'll be used to from GCSEs, and it's just something that you kind of have to get used to. So let's say you got a question like this, and you can use cumulative frequencies basically to estimate your mean and estimate the quartiles from your graph. So let's say I give you this kind of graph, and I say, look, I want you to draw the cumulative frequency diagram from here, and then let's estimate what the median heights are and what the upper quartile and the lower quartiles are. So the way you do cumulative frequency is you take your graph and then you add another column to it. So you see our frequency, it's called the cumulative frequency. And all you do is you say, I started with 5, then onto 5 I add 12. So 5 plus 12 is 17. And what I did was I added that to that, then I add that to that, that to that, and that to that. So what happens if I add that to 8? I get 25. Then I do 25 plus 2, get 27. And then add on to that, I've got 32. So you can see my cumulative frequency graph has given me a total number of 32. So that means that everything in here adds up to 32. So you can just double check that. 5 plus 12 is 17. 17 plus 8 is 25. Plus 2 is 27. Plus 5 is 32. So that's all you need to do for the cumulative frequency graph. Once you've done that, and this won't be quite to scale, but just be roughly, you draw out your graph like so, something like that, let's say. And then what you want to do is plot these onto your cumulative frequency. So this will be known as the cumulative frequency in the y-axis. And let's say this is the height on this side. So then what you would do is, let's actually do this somewhat to scale. So let's say this is 0, 4, 8, 12, 16, something like that. Normally you'll want to draw it to like much more accuracy. So you might want to go 0, 2, 4, 6, etc. But for this question, we'll just do that. And then what you'll say is, where does the lowest class start? So lowest class starts here at 4. So we start off at 4 for our graph. So I'll put in a thing here at 4. Then I know that the next one that I've got, this one at 4 starts here, but when it goes to 6, the cumulative frequency is 5. So let's just draw on the axis here as well. So this is 5, 10, 15, 20, 25, 30, 35. So when it goes to 6, we know the first class ends at 5. So I can draw a point at 6, about at 5. Then I know from 6 to 8, it goes to 17. So when it's 8, it should be roughly at 17, which is somewhere there. Then at 10, I know it goes to 25. So at 10, it's 25. Then I know at 12, it goes to 27. So that's somewhere here. And then at 14, it goes to 32. So that would be somewhere over here. Once you drew these points in, you just want to connect them with some sort of smooth curve. So it's important that the curve that you have is smooth, but that's essentially all you need to do for your cumulative frequency graph. You have to just join it up. Don't join it up like some people do with like lines, and don't do like lines which join it up. So what I mean is, don't do this. That would be wrong. It has to be a smooth curve. So something like that would be okay for it. But make sure that it is a smoothish kind of curve that you're doing. So yeah, that's pretty much all you need to do for cumulative frequency there. And then you've got your cumulative frequency graph. Then if someone asks you to find the median, it's actually easy, because normally if you had to find the median, if you remember, normally we said you have to do total number of things plus 1 divided by 2. But that's because you're normally working with discrete data. When you're working continuous data, you quite simply don't have to add the 1, because continuous, you just divide straight by 2. And you say, well, the 16th value is my median. So you go to your cumulative frequency, go to 16, wherever that is. Still a different color. You hit the graph wherever it is. You go down and you read that value, whatever that value there is, that's your median value. If I asked you to find the different quartiles that you've got, so let's say the lower quartile, that's just 32 divided by 4, 8th value. So on my graph here, find the 8th value here somewhere, hits it there, that's your Q1, that's your Q2. Same for Q3, it's just 3/4 of 3 times 32 over 4. So that cancels out to 8 times 3, which is the 24th value. So again, just go to here, 24th value, draw it down. And so this value here is your Q1, this one here is your Q2, and this one, whatever here, is your Q3. That's it. You just simply have to read off the diagram, and that's it. So if someone asks you how to find the quartiles, that's what you do. If you then have to find percentiles, it's also easy. If it's like the 90th percentile, I say 32 times 0.9 gives me whatever. That's that number they have to do. So if I say like find me the 80th percentile, so I'll do what's 80% of 32. Oops, 80% of 32. That'll give me some sort of number. Based on whatever that number is, you can usually round to the nearest number and then just mark it from the graph, and then you can find different percentiles like that. But that's pretty much it for cumulative frequency. A lot of it is the same stuff as what you've probably done during your GCSE times, so there won't be anything too tricky there either. And then normally you can draw box plots from this too, because you found Q1, you found Q2, you found Q3. The lowest value is 4, the highest value is 14. So I mean, if I'll just do that here, actually, if I was doing a box plot, let's just draw a random one like that. Then in terms of what you'd mark the values at, this would be 4. This is whatever I found in my graph on Q1, Q2, Q3, and this would be 14. So I got the 4 from here, and I got the 14 from here. And the rest of these I found from my graph. So that's pretty much it. That is cumulative frequency in a nutshell, and the different kinds of questions you can get from that. So from there, we'll look at the last way that you can represent your data points, and that will be histograms. So those are the ones that people kind of get confused with every now and then, but they're pretty simple to do. So we'll just kind of go through how you can do that. So let's take a look at histograms next. Okay, cool. So let's take a look at histograms now. So the area is proportional to the frequency in histograms. So what that means is, in a histogram, what tends to happen is, when we're working with data, the class intervals might not be the same. So it might be something like some intervals like 25 to 25 to like 30, and then the next one might be 30 to like 50, and then the other could be like 50 to 100, something like that. So the class intervals aren't always the same. So in histograms, what you want to do is, if you have a bunch of squares like this, then what we say is the area is proportional to your frequency. So we care about the areas, we don't care about how high and stuff like that is. The area is a key thing we want to know. And when you graph them, you have the frequency density on this side, and on this side you tend to have whatever x values you have. So normally what we do is, on your histograms, to find the height of each of the bars, so the height of each bar is a frequency density, we have to use a formula which is known as the area of the bar. So area of the bar is equal to k times the frequency. Now the thing is, it's just easier to say that k is equal to 1 if you want to draw graphs. So k can be anything, but in A levels it's just easier to take k is equal to 1. So if we assume k is 1, then we say the frequency density, and this is the equation you actually want to learn, the frequency density is the same as the frequency divided by the class width. So that's how you can figure out what frequency density is. You just take the frequency that you've got and you divide that by the class width. And once you've done that, then that's pretty much it. You can get started with drawing histograms. So the best way really to learn this topic would probably be to just do an example. But one thing you should understand before that is just that the area is proportional to the frequency. That's the key thing that we want to know. So let's take a look at an example next. And one thing before you actually carry on might be worth mentioning is, if I had something like this for my histograms, then if you take the midpoint of each of these and you join them up with a line, then you can make something which is called a frequency polygon using this method. So we can also take a look at that when we actually draw the histogram from our example. So let's go next. Let's take a look at an example here. So here you can see you have a set of data, and this can be the time taken for people to finish a race, and these are the frequencies of how long each person took. So we're just going to draw a histogram, and from that histogram we want to estimate how many people took 18 to 25 minutes to run this. So let's start off by drawing this histogram. So like we said before in our histogram, that the key thing was the left hand side, or the y-axis I should say, is a frequency density, and that's frequency density, and this will be the frequency in terms of the time that people took to run. So that's the time in t. So before we even do that, we should probably construct a table. So we say something like the time taken to run was 10 to 15, 15 to 20, 20 to 30, and 30 to 50. Now to be technically correct, I should write it like this, not like this, but this is just for the working out, so I'm writing it like that. Then after that, we have the frequencies, 60, 54, 36, and 40. Once you've got that, all you need to do is write another one known as the class width. So the class width of this one is 5. And how did I get that? That's class width of 5. The other one is also 5. This one is 10 because 30 minus 20 is 10. And then this one is 20. So we have different class widths you can see here. And now we can actually find what the frequency densities are. And quite simply, to the frequency density, like we said before, frequency density is equal to the frequency over the class width. So just using that formula, we can find what the different frequency densities are. So 60 divided by 5 here. So you look at that divided by that, gives you 12. 54 divided by 5 is 10.8, I imagine. And then 36 divided by 10 is just 3.6. 40 divided by 20 is just 2. So those are your frequency densities. And now you've got that, all you need to essentially do is you just need to plot that onto a graph. So if you go down here, and we'll do a graph again, roughly to scale. So let's draw a line over here. And in terms of our time, we're going all the way to 50. So let's just keep going all the way down. So let's say 0, 5, 10, 15, 20, 25, 30, 35. Cool, we've gone a little bit off. So 40, 45, 50. Let's draw that there. This is the frequency density. This is the time t. our frequency density only goes up to a maximum of 10, actually 12. So let's just go up something like 2, 4, 6, 8, 10, 12. That fits in perfectly. And now let's just fill that in. So starting from the beginning, our first class doesn't actually start from 0, it starts from 10 to 15. So we're actually looking at something which is between 10 over here and 15. So that's where the first two are. And what is the frequency density? The frequency density of that is 12. So what we do is draw the bar over here. So this one here would look something like that. So now from 15 to 20 is 10.8. So that would be somewhere here. That's 15 to 20. Then 20 to 30 is 3.6. So 20 to 30 is somewhere over here. And 30 to 50 is just a small value of 2. So 30 to 50 is something like that. And that's it. That's all you have to do for your frequency densities. And this is how you draw a histogram. We actually have a histogram now. And like I mentioned before, if I were to join the middle parts of each of these, so this one is 30 to 50, so that's 40, that's the middle part, then I'll basically just get myself a frequency polygon. So what I mean by that is a line there, a line there, a line there. That essentially gives you your frequency polygon in terms of how you work with that. But that's it, you've drawn your histogram. Now the question was, based on that, how many people it took between 18 to 25 minutes to do that? So how do we figure that out? So what we need to do first is, let's actually figure out in a different color. Let's do it in orange. Where exactly is 18 and 25 minutes on a graph? So 18 is somewhere here. 25 is, or 24 it was, 25 is here. So we said the area under the graph is representing the frequency, and here we're asking how many people, hence the frequency. So if I drew a line from here to here and here to here, this question is just asking me, what is the area of the shaded part of this histogram? That's what it wants me to know. So that's what I need to do. I need to find this area. So how do I actually do that? Well, I need to figure out the number of people in that, area that I'm using. So let's take a look at how we do that. So to figure that out, let's take a look at what classes this falls into. So just, I'll write that down here actually, so I don't forget, between 18 and 25 minutes. So where does 18 fall? So 18 falls into the class over here. And where does 25 fall? 25 falls into this class. So in this class, I've got 15 to 20 people, and 18 falls somewhere over here. So I need to extrapolate between this graph. So since 18 people falls between 15 to 20, I say that from 18 to 20, how much does that give you? Well, that's just 20 minus 18. So there's a gap of 2 to get from this 18 to the 20 people that you have. So you take 20 minus 18, and all you do is you times that by the frequency density of that class. So the frequency density of 15 to 20 is 10.8. That's what you do. Now, which class does 25 fall into? That falls into 20 to 30, and 25 is somewhere here. So how far is 25 from that? It's only 5 away, or otherwise 25 minus 20 away. And you times that by the frequency density of that class, which is 3.6. So as you can see, these two will give you some answers. So let's see what that gives you. So this one gives you 2 times 10.8, which is 21.6. And this one gives you 5 times 3.6. So 5 times 3.6 is just 18. So now that I've got 18, we can add up these numbers, 21.6 plus 18, giving us 39.6 as a value. So the estimate would be roughly 39.6 students, and you can say, if you round that up, is roughly 40 students is what you should have. But in terms of student-wise, or in terms of numbers, you can say that this is the answer of the estimate that we've given. Obviously, you can't have that many students, so it actually should be something like either 39 or 40. But that's how you figure it out. So what did we actually do? First, we figured out that this is the times we want to go in between. So which class does 18 fall into, and which class does 25 fall into? We found it fell into this class and this class. Then we want to say, if it's 18, well, this is 15 to 20, and 18 is like somewhere over here. So we need to find out how far 18 is from 20. And same for the other one, this is 25. How far is 25 from 20? So when you find out how far they are, so this is 20 minus 18, so it's 2. and this is 25 minus 20, you multiply them by the respective frequency densities, and then you get your two answers, which you add up, and that gives you your final frequency. So I hope that wasn't too bad, and then we can go through some more examples in another video of how to do this kind of question. So once you've done that, there's another type of question you can expect. So this is a question that you can take a look at. So it's quite a bit to read, so let's go through it together. So it says on a histogram, a rectangle represents the class 12 to 14. It's 4 centimeters high, 3 centimeters wide, and the frequency it represents is 36. And X is the mean number of days that's cloudy. So let's say maybe the number of days is cloudy in a year. That's the mean number of days in a city. So what area is each day represented by? So just so you know what's happening is we have a rectangle from 12 to 14, which is 3 centimeters wide and 4 centimeters high. And it represents a total frequency of 36. So the frequency it represents is 36. Now, this is a rectangle which is part of a whole histogram set. So this is actually what the whole thing might look like. And it's just talking about this one histogram square or rectangle that we've got here. So the first question is quite easy. It says what area is each day represented by? And to do this, what you have to do first is you find the area of the bar, which is 3 times 4, which is equal to 12. And this area of 12 is representing 36 as a frequency. So you just say the area divided by the frequency is what you want. So the area divided by frequency is 36, or actually 36 on the area. The area is 12. And this area of 12 represents 36 people. So the frequency density is 1/3, or 0.33 centimeters squared. And that's what each day is represented by. That's what each day is represented by for the area. And then quite simply, it says the total area is 60. So if the total area is 60, then how many days are there in total? Well, for part B, we know that each day is represented by 0.33 centimeters squared. We have 60 centimeters squared. So quite simply, to find the total number of days, you just divide the two by each other. And I think what might be better is, since we know that actually it's 1/3, so let's stick to 1/3. So let's say 1/3 is the area for each day, and we have 60 in total. So 60 divided by 1/3 means that we have 180 days in total. And that's it. We know that there's 180 days in total. So these kind of questions are quite simple. If you just follow the area, figure out if you've got a total number of frequencies, then for that total number of frequency, all you have to do is do the area divided by the frequency, and it gives you what area is represented for each kind of day. And then if you have a total area, you can just divide it by that and get the total number of days. So these kind of questions quite simple to follow. And that's kind of it in terms of representation. The last thing we have in this chapter is just comparing two data sets, which we've already talked about, but we'll just really briefly recap what we said. So there's two things you can do. You can compare the measures of location. And we've already done this before because we talk about the interquartile range, or not that one, sorry. We talked about compare the median. So you talk about Q2, or you might talk about the mean in some questions. You might talk about stuff like that. You might talk about the mode or whatever. And then the other thing you're going to compare is a measure of spread. So that's another thing you want to put. So you might want to put in stuff like, the variance. You might want to talk about the standard deviation and so on. But these are the two things you want to compare. You want to compare a measure of location and a measure of spread. So normally when you have a question, you can either compare data using like mean and standard deviation. So usually a measure of location, the standard ones would be if you have the mean, you would then use a measure of spread, which is the standard deviation. Or if you have the other one, that would be where you look at the median. And if you have the median, you tend to compare that with the interquartile range as your measure of spread. So that's pretty much it. So if your data set has like extreme values, so it's like huge values, then the mean will be affected by that, like we talked about before. The mean is not good when you have extreme values. So in that case, when you have extreme values or outliers like that, you want to use the median and the interquartile range because that's better to use. So for questions like that, that's the stuff you have to keep in mind. So yeah, other comparisons might be stuff like the box plots we talked about. So we already talked about how you can compare the box plots, just compare the two different medians, compare the different interquartile ranges, and that tends to be it. So usually they'll get you to actually calculate the mean and the standard deviation or stuff like that before. And once you've done it, they'll say, look, another data set has this mean and this standard deviation. And then you just say data set A has a lower or higher mean, and then it has a lower standard deviation, and you just compare that back to the question. So these questions are quite simple to do, and that's pretty much it. So I hope that this topic was okay. A lot of it does come from GCSEs, and yeah, pretty much that's all good. So if this was helpful for you, it'd be great if you could share this with your friends. The statistics set for year 1 is complete now, so if you follow through the entire playlist, you'll pretty much be able to catch up on everything in year 1 stats. And from now, we'll be carrying on with year 2 stats in the other videos. So I hope it's helpful. And as always, just if it is great, then just leave a comment below or subscribe, or just let your friends know, because the more people that watch it, I can make some more videos on other topics like pure and mechanics and further maths and so on. But I just want to make sure that it is helpful for everyone. So I'll see you in the next video in the next series. Welcome back to our series on year 1 statistics. And in this series, we'll be going through all of the different chapters you need to know about to sit your A-level exams. So in this video, we'll be looking at correlation, and more particularly what is correlation and what is linear regression. And as well as looking at these topics, we'll also be looking at a few questions so you can, better familiarize yourself with some of the different questions that are out there. So we'll go over some theory and we'll look at some examples, and hopefully put together, it will really help you to understand this topic much better. So some of the key takeaways we want you to have from this chapter is understanding what is bivariate data, understanding what is correlation and why that doesn't mean you have causation, as well as what is the linear line equation and when to use this. So we'll be looking at all of these 3 different areas. So just going further down here, let's start off with what is bivariate data. So bivariate data is usually when you're looking at 2 different variables usually. So if I had to put it in a better way, I'd say bivariate statistics looks at how one variable compares with another variable. So how does it influence it? So some good examples of this would be, let's say you're looking at someone's height and someone's weight. So on one side of the graph, what we might have over here is, let's say we've got a graph like this. And looking on this graph, on this side, we might have someone's weight. And on the other side, we'll have someone's height. So we want to look at the correlation between these 2 things. So in bivariate data, if I have a single data point right here, for example, this point incorporates both what someone's weight is. So you might have this one person's weight is like 60 kilograms, and the height might be 165 centimeters. So this is bivariate data. And the reason this is bivariate data is, as you can see, we have 2 different sets of data. So bivariate data can be anything. I could have how far you've been able to run compared to how long you've been in the gym, what your weight is compared to how much you eat, and lots of different things like that. So usually when you're looking at this, you might have learned this at GCSEs. The area we're looking at the bottom of the graph, so that's the x-axis, this part here is considered your independent variable. So that's your independent variable here. And that's the variable which, that's the one that you're trying to control. That's the one that you don't want to, that's the one that you're actually saying, okay, look, well, if I'm changing my height, what happens to my weight? So it's saying that if I change the independent variable, how does my other variable change? And this other variable that we talk about, which is everything on the y-axis here, this is going to be considered as your dependent variable. So put together, that's what you've got. And this is the variable which you measure. So if I had to summarize what we said, the independent variable, so independent variable, this is the one which you control. So this is your controlled variable. Controlled variable. And your dependent variable is your measured variable. So this is what you are trying to measure. So yeah, put together, that's kind of what you're looking at for bivariate data. So that's just hopefully going to give you a better idea of how bivariate data works and what that means. So normally when you look at these different sets of data, if I then move further down, so looking further on, there are a few different things you might want to know. So let's draw a few graphs here first. Let's look a little bit at what do we mean by correlation. So if I just copy over that graph, show you all the different types of graphs we can have. Okay, so now looking at this one, let's start off with what is positive correlation. So positive correlation. Positive correlation is where your data points as you're drawing them are somewhat going on an upwards trend, and in general they are going slightly up. So looking at this graph, you can see if you're low on the graph, you're quite likely to have a lower value for one than the other. So if this value is low, then this value is also low, and on the other side, if this value is high, then this value is also likely to be high. This is what we consider as weak positive correlation. However, if your points are going up, but there's a much clearer kind of pattern in it, so something like this, you can see the points are much closer together, and you can more accurately say where your points should lie. So again, you can see why it's positive correlation, because it's going upwards. This is considered as strong positive correlation. So that's how these two areas work. So now let's say that we were looking at our other side. So you can probably figure it out. If that's what is known as positive correlation, we also have something known as negative correlation. So if we copy this over again, over here, and just put that down here, what we'll be looking at now is some weak correlation. So to be honest, it's just pretty much the same thing. Negative correlation. And this is where your points are all going down slightly. So, there's not a very obvious downwards trend, but there is somewhat of a downwards trend if you take a look at this. Whereas again, with the strong negative correlation, it's very clear that the points are going down. So if I had to, again, draw a line of best fit through each of these different things, if I was drawing it through here, it'd be something like that. Through here, it'd be something like that. And then here would be something like that. And here would be something like that. So just to reiterate, this is again weak negative correlation. Oops, this is known as weak negative correlation, and this is strong negative correlation. And you might be wondering, what does no correlation look like? So if you want to know what that's like, if I draw that down here, then no correlation is where you can't really see a pattern either way. So it's kind of like your points are randomly scattered across your graph, and there's no obvious trend going up, going down, or going anywhere. So here there is no correlation because we can't really draw any such line of best fit through it. There's not really any correlation there. So that's what it means to have correlation. So in your exam, you'd be expected to identify the different kinds of correlation that you may have between different variables. So what you say is, for negatively correlated variables, if you want just like a nice phrase, so for negatively correlated variables, what happens is as one variable increases, the other will decrease. So one variable goes up, the other variable goes down. That's what it means to be negatively correlated. And if you're positively correlated, variables, spelled that wrong there, then it means as one variable goes up, the other variable will go up as well. So just to show that on the graphs up here, you can see on the positive correlation side over here that as one variable here is going up, the other one is also going up, and here you can also see as they're going up, they're also going up. But here you can see as one is going down, then the other one is also going down. So that's just how you work with the different areas of correlation. So hopefully that makes a lot more sense now. So apart from this, the next area that we will need to look at is to do with, if I just go through it, is linear regression. Now this is a topic which might look like there's a lot I'm drawing at the beginning, but it's not a very difficult chapter to understand. So let's take a look at what is linear regression. So linear regression. Cool. So now for linear regression, what happens is normally let's say we have a diagram. So let's just draw a nice large scatter diagram. And in the scatter diagram, what we find is that we have a bunch of points through our graph. So actually, let's not have one there. Let's have one here, 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 and let's say there. So looking at this graph, you'd say, you know, there is some sort of line of best fit you can draw, and you'd say there is probably a weak positive correlation, or depending on how close they are, you can even say it's a strong one. But if I told you to draw a line of best fit, some of you might draw a line of best fit which is like that, some of you might draw me a line which is like that, some of you might draw me a line which is like that, or like that, or like that. And to be honest, all of them could seem as if they're all correct. But if you want to find out what is the exact line of best fit, we use a method known as least squares of regression, and this is basically the regression line that we're talking about. And what this line is doing is, let's say we draw a line of best fit, which is, actually let's do this, let's draw two lines of best fit. Let's draw one which is kind of going through like that, and then let's draw another one in a different color which is going through somewhat, let's say, something like that. Okay, so if I have this as my line of best fit, what the idea is you have a bunch of distances from each of these points which will meet this line. So let's go up. So each of these points have a distance where they meet this line. And what you want to do is, if I call this D1, D2, D3, D4, call this one D5 and D6, D7. The idea is that D1 added all the way on to D7 equals to some number. And if I do the same thing for, that would probably reach up there somewhere. This one reaches there, this one's up there, this one's down there, this one's up there. Just drawing on, should probably have continued the line, but you get the idea. Now again, these would be, let's call this one like B1, B2, B3, B4, B5, B6 and B7. Then if I added up all of these lines, eventually I get another number. Now the different lines I draw will have different distances from each of the points. Now the thing is, you can probably tell by looking at this graph that if I add up all the orange lines, which are the B1, B2 and so on, that if I add them up, the final total I get will be much bigger than the total I'll get for the lines which are in blue. So what that would suggest is that the blue line is a better fit than the other line. And what you're trying to do in least squares regression is you're actually trying to find the data points which will actually minimize this maximum distance. So if you can draw a line where if I have like B1, B2, B3, and you can make that as small as possible, then that is considered the least square regression line. And that's what this kind of topic is about. So this is the idea kind of behind it. You want to minimize the sum of the squares of the distances of each of the points. So that's kind of what you're doing in that. That's a very high level simplified version, just to give you a conceptual understanding. We can look at it more deeply in another video, but that's kind of the idea behind it. What you actually do in this video is, in this topic, is normally because let's say I had a line like this just on the side, let's say I had some random line like that. The thing is, the distances that I'd have between the points, these might be considered as positive and these might be considered as negative. So what I mean by that is this might have a distance of 2. This you might count as -2 over here. This might be like 5 and this might be considered like -6. So in order to get rid of all these minus signs which will interfere with what you say is you do something like 2 squared plus -2 squared plus 5 squared plus -6 squared, and the squaring part kind of gets rid of the minus sign so you can get some number which works. So that's why you call it the least squares regression line. But the good thing is, for your exam you don't need to actually be able to calculate this, you just need to understand the concept, which is why I explained the part before. So if that makes sense, what we can continue to look at now further down here is, what is the regression line formula on its own? So the regression line of y on x is written in the form y equals to a plus bx. Now this will look very familiar to the line of the equation of a straight line, and that's because this is exactly the same equation as the equation of a straight line. As you know from your GCSEs, the equation of a straight line is y equals mx plus c, where the m is a gradient, the c is a y-intercept, and in this topic it's literally the same equation. The c is just an a and the m is just a b. So if you're thinking of y equals a plus bx, just think of it as literally the equation of a straight line. So what the b is trying to tell you is it's kind of telling you information about the correlation, because as you know, in any graph, if you have a line and this line is a straight line going in the positive direction, this has a positive gradient. Oops. And you have a positive gradient when your b or your m is positive. So if you know that, then you know you have positive correlation. And then the same thing counts for if you have negative correlation. So if you have a negative gradient, what do we know about our b? Well, we know b must be negative. So as soon as you see b is negative in your equation, you know that you have negative correlation. And that's basically the main idea. This is the kind of stuff that you can use to find out what is true about your bivariate data. Because in your bivariate data, what you'll find is that if you can find, you'll usually be given in your exam what the value of b is, and they'll say something, and you also know what a is, and they usually say something like, okay, if your graph is like this, for example, let's say this is your graph, they'll say something like, and this is your x value, and this is your y value. They'll say, okay, for a given value of x, which is an independent variable, can you predict what is the y value going to be? So he might say, look, here's my line of best fit. It looks something like this. And then they will give you a value for x, which is, let's say, 100. And then the idea you have is that, okay, if I've got 100 here, I can predict what my y value is supposed to be. And you might find here that your y value should be something like 250. So you can use this equation to have a value of x and use that to predict the value of y. So you're using your independent variable in order to predict your dependent variable. Now, what you cannot do in this one is use your dependent variables to figure out independent variables. So what I can't do, and what I'll do is I'll put this in red, is I can't say, oh, if this is 150, then I can work backwards and I can find out that this is actually meant to be 50. So this is actually wrong, and so you can't do it going that way, but you can do that. So you can use x to find y using that equation, that's fine, but you can't use y to find x, that's going to be wrong. So that's the idea of correlation in that chapter over there. So apart from that, what else you need to know is that if you know the value, so if I just say it formally, what I've said in like maths talk, you'd say if you know the value of the independent variable from your bivariate data, then you can use your regression line to make a prediction on the estimate, or the estimate which corresponds back to your dependent variable. So your regression line is used to make predictions for values of the dependent variable, basically. And usually you want it to be in the range of the data that you've been given. And what I mean by that is, let's say I had another situation where, let's say this is my graph. And in my graph, I've got a bunch of data points like this. So once again, got some of that. So based on that, you can definitely say that there's some sort of regression line, let's say like that you've come up with. Now, the problem is, it would be fairly okay for you to say, okay, I'm trying to make a prediction for something. Let's say I'm trying to predict what the value at this point here in x is. Let's just make up a number and say that's 90. Well, that's fine. I can just go up, go to the left, and I can say, okay, I've kind of predicted that this maybe is 160. That's the value I read of my y-axis. But then the problem is, let's say I had another very small variable here, which is like 5. If I keep going up, there is no line to hit. And the reason is that I don't have any data points on this side. If I had some extra data points, so let's say I had some more data points here and here, then I'd be able to extend this regression line, which I've got further, and that would be more accurate. But unfortunately, these points don't exist. So by trying to predict something outside of the given data, that might not be the most accurate thing to do. And sometimes the questions in the exam will have that as like the last question, like why is this value accurate? So why is 90 a good idea to use, but why is 5 not a good idea to use? And usually that's the answer. And another thing that you might want to know about this question is, another thing you could say to answer these questions is that, well, you can see that this would be more accurate if I had more data points. If I had a ton of data points like this, then I can say this blue line is fairly accurate. And sometimes you might not have that, and that's your value of n. So at the beginning of this drawing, back when I was doing this, I only had about, let's say, 6 or 8 variables, so n was 6. So that's not so accurate. Whereas now if I have, let's say, 20, that's slightly more accurate. And now let's say I had n as like 2000, then n would be much more accurate. So sometimes you can say the answer to these questions are that, you know, the value of n is quite small and hence your data might not be as accurate. So that's the idea behind regression in this chapter. Next, what we'll take a look at is how you can use these and how these are used in some of the questions that you'll do, and hopefully that will give you a much better understanding of this topic. So when it comes to some questions, let's take a look at an example. So let's say you're given a table as so, and it gives you a bunch of people and it tells you the age and it tells you their favorite number. So normally the questions you see will often give you a table and you have to draw some sort of scatter diagram from it. So as you can see here, it says, please draw a scatter diagram. So for that, let's try and draw out our diagram. So what it would look like is we draw our axes as so. And once we've done that, let's put down the age on the x-axis. And normally what you should write down is age in years, as it's given to you in your question normally, but this is just an example. And let's put down your favorite number. So if you were to just, draw this the usual way and plot it, you would find that your diagram would exhibit some sort of correlation, and your diagram would end up looking something like this. So that's just roughly what you would get if you should plot these points. And normally you'd get some marks for just drawing your scatter diagram properly, so make sure you do that right. And then the next thing you'll be asked to do is to describe the correlation between the 2 points that you have. So as you've seen before, when we've done this kind of thing, you can see there's a clear downwards trend, and you probably have a line of best fit, something like that. You don't have to draw it in, but this is just to demonstrate the point. You can see that you'd say there's probably a weak negative correlation between these points here that you've got. And then the next part of this question will ask you to interpret it. So this is normally the part where you have to put into words what you found. And what's important to understand here is you'd say that, well, I can see here that as the age increases, so as your age is going up, we find that the number, which is the favorite number of this person, also tends to actually decrease. So that's what you find with this kind of question. So normally what you do is you'll say something like, the thing that I found or saw on the x-axis, as this thing either increases or decreases, we find that the thing on the y-axis is also either increasing or decreasing. So depending obviously on whether it's positive or negative correlation, you'll change your answer. So in this case, because it's negative correlation, we'll say as the age is increasing, we find that the number, which is the favorite, is decreasing. But if we had positive correlation for a different question, we'd say as the x-axis thing is increasing, we find that the thing on the y-axis is also increasing. And what is important to mention at this point is that sometimes you might see things are correlated, but that doesn't imply that those two things cause each other. So you can only say two things cause each other if you change one thing. It means you definitely should be changing the other thing, like it causes a change in the other thing. But sometimes you might just find correlation between two different variables, but it doesn't necessarily mean a change in one variable is actually causing the change in the other variable. So that's just one thing to be careful with. So that's pretty simple, these kinds of questions. You draw your scatter diagram. Correlation is fairly simple. You can figure out if it's negative or positive, and you have to figure out if it's weak or strong. And apart from that, for the interpreting part, you now have a plan for how to do it. So you'll say, based on what I have in my x-axis over here, as this increases or decreases, the thing on my y-axis here is either increasing or decreasing. That's normally how you'll answer that kind of question. And yeah, just substitute it in. So here you've got age and number. You just choose whichever ones you've got. So that's how you do that kind of example. Now let's look at a different type of question that you might get. Another kind of question you might get is something like this. So you've got the same data as before, but now they've given you the equation of the regression line. So if I just go back, that might be the equation of this orange regression line that I've drawn in here. So the question is, what does that gradient mean about correlation? Well, the gradient over here is this part here, the minus 2.2x. And as we said before, a negative gradient means that you will have negative correlation. So the answer to this question is simply that we just have a negative correlation in our graph. So that's fairly simple to understand. Now, the next question that we have to answer is, can we actually use a regression line? And in order to understand this part here, what we need to see is that when can we actually use this regression line? When is it always correct? And there's always like a set answer for this part. And that is the correlation of the data suggests there's a linear relationship between x and y, and therefore we can use a regression line. So the key parts of this question that we just saw is the part about having a linear relationship, and the correlation of this data is why we have this linear relationship, and therefore we can use a regression line. So when you see data and when it looks like it has some correlation where it's linear, so as one thing goes up a certain amount, the other thing also goes up a certain amount, what I mean by that is like your data looks something like this. So it's something like that, it's something like this. Your data could be going somewhere like somewhere like that, somewhere like this, doesn't matter. All these are linear because as one goes down, the other one goes up or down in a certain amount. And if you wanted something which is non-linear, it looks something like that. That's non-linear, something like this is non-linear, something like this is non-linear, because it's not always the case as one goes down, the other goes up, or the other way around, because you can see it always changes depending on what part of the curve you're at. So the set answer you give for something like this is the correlation of the data suggests a linear relationship, and if you have a linear relationship, only then can you use regression line. So that's kind of the set answer you give for questions like this. So another example of kinds of questions you get would be something like this. So here we have a bunch of plants, and we've given the time in, let's say, in hours or days. Let's say days, the days for which these plants have been growing, and the height in centimeters for how much height they have achieved. The question gives you the regression line is y equals 8.85 plus 0.62x, and that's the question you've got so far. And it says that here, some estimate of a plant has been taken for 38 days. So they've found a plant, and they want to estimate what that plant would look like at 38 days. And the estimate of a plant is also found at 28 days. And then the question is saying, well, how accurate are these estimates? Well, in order to answer this kind of question, what we need to do first is we need to draw the graph. So again, this is just an example for now. It's not one of those worked ones, just one to understand the theory. So I'll just draw a normal graph. And here, if we were to plot all of these points onto a graph, what we would probably find is it's something like this in terms of the points which are plotted. This is roughly what they would look like. And if we just put in our line of best fit, you would have something like that. Now, the thing is, if you look back at this data, you'll notice that the biggest value that you have for the plant in terms of time, so just putting time on this axis here, and putting down the height on this axis here, what we are finding is that the biggest value I've got for time is 39. So you know that this value here for time is 39. And the smallest value we have is 32. So we have somewhere here 32. And also, my bad, I just realized that 42 is the largest time we've got there. So let's swap that out. So yeah, we've got 42 here. Now, for the first one which we're estimating, we estimated some plant at 38 days. And 38 days actually falls within our expected estimate of the line. So 38 falls here. And therefore we can be, fairly confident, somewhat confident that 38 would fall there. However, we've got another plant which is found to be at 28 days. And 28 days is probably somewhere all the way down here. Now, the problem, like we said before, is there's no line or no points that we have which extend the line there, because the smallest value we had before was 32. And because 28 falls outside that value, we can't really say that this estimate is as accurate because we don't have no data points covering this side of the graph. Whereas for 38, we have plenty of data points covering this side of the graph. So that's why we would say that 38 is fairly accurate and can be considered more accurate than the value of 28, because 28 as a value falls outside of the interpolation that we have of our data, and it falls over here. So that's not correct. So that's why 28 doesn't work. The next question says that someone wants to find the time of a plant given the height of 36. So what that kind of implies is that, let's just go back a second. If I wanted to find out the height of a plant given the time, what I would do is I would input the time into the x value here, and then after I solve this equation, I will get what the height of the plant is. Now, the problem we have is in this question is saying that someone wants to find the height of a plant given the height. He wants to find the time of the plant. So they want to find what x is given this value of y. Now, the reason this is wrong is, like we said before, you can only use the independent variable in order to find the dependent variable. So now in this one, we have this is our section, which is the independent side, and this is the dependent side. So we can't use a value over here on the y side to find a value here on the x side. So the reason that this is wrong, and if you had to give a reason for it, is to say the independent variable in this model is supposed to be time. However, we're trying to find the value for the height, which is the dependent variable, and you cannot be using an independent variable in order you cannot be using a dependent variable in order to find out an independent variable. So just to summarize, what we're trying to say is you cannot use this dependent variable in order to find this independent variable back here. You can only ever put a value of x to find a value of y. And that's usually the answer to these kinds of questions. What we'll do next time is, this kind of topic had more theory involved, so in terms of the answers, there weren't very many calculations. A lot of it was to do with explaining. In future videos, what we'll be doing is, a lot of it is more calculation based, so we'll actually go through the full worked calculations from the beginning right to the end, and that way you'll have like fully worked solutions. And in this example, I just wanted you to really understand how the theory of these work. So these questions are quite similar to what you might get in the exams, and we'll do another video separately, just purely going through exercises from the beginning to the end, where I fully write out what the worked solution should be and have some custom questions for you to try out, which will be related to this video, and that will come out soon, so look out for that. In the meantime, I hope you've understood correlation a bit better for exam board, and if you have any concepts that you did not understand or some theory you did not understand, just ask in the comments below and I will get back to you and let you know. Hi, and welcome to another video in our statistics series. So today we'll be taking a look at probability in stats, and this is one of the later chapters in statistics, and it's actually usually one of the ones that people usually have a little bit of trouble with, probably because the basic concepts are not something that teachers tend to go through. They tend to just give you a bunch of questions that you have to do. So in this video, we'll be covering a few different things. So we'll be taking a look at how to actually calculate the probabilities for single events, how to better actually understand Venn diagrams. So that would be stuff like, how do you find the intersection? How do you understand or, and how do you understand like the not stuff, so everything which is outside. So I'll just make it a little easier to understand a little bit about how to draw the Venn diagrams, and when it tells you something about it, how to know what's the right part to shade. Apart from that, we'll take a look at mutually exclusive independent events, and this is something which people tend to get mixed up quite a lot, or they're not really sure how to give the definitions for these. So we can take a look at some of that. And finally, we'll end with probably what's the easiest part of the chapter, which will be tree diagrams. So there's not too many subtopics to go through in this video, and hopefully everything will make sense as we go through it. So let's get straight into it. So one of the first things we'll take a look at is, when we're actually calculating probabilities, there are a bunch of words which you need to be familiar with. So the first one of these is an experiment. So let's start with that, an experiment. So what is an experiment? So an experiment is basically just like a process or something that you can do and keep repeating a bunch of times, and that will give you some sort of outcome. So it's a process which is repeated to give an outcome. So the key word here really is the word outcome. So an experiment is a process which you repeat and gives you an outcome. An example of an experiment would be you rolling a dice, and when you roll the dice, you might roll a 6, in which case your 6 would be the outcome. So if I had a dice here and I had to roll it, and then I end up getting a 6, the 6 here, that's my outcome, and the experiment was rolling the dice. And you can do that a bunch of times. So if I do that, then this is also known as an event. So an event is a collection of one or more outcomes. So that's the next word you need to know. What is an event? Collection of one or more outcomes. So it could be that I roll the dice like 20 times and I say, okay, what's this event? The event is how many evens did I get when I rolled my dice, or something like that. So that's the next keyword you need to know. So you need to know what an experiment is, you need to know what an event is, and you need to know what an outcome is. So after that, there's only another thing we need to know, which is something called the sample space. And this is something that people tend to get confused with. So sample space is basically all the possible outcomes. So all possible outcomes. And what this means is if we're rolling the dice, we can only roll a 1, 2, 3, 4, 5, or 6. We can't actually roll anything else. So our sample space would be all the numbers between 1 to 6. And that's basically what a sample space is. So every single outcome you could possibly get, that's essentially what your sample space would be. So yeah, so basically what happens is if you look at all your events and each of your events are equally likely, then the probability of one of your events is just the number of outcomes that you have in that event, and you divide that by all your possible outcomes. So that probably sounded really confusing. So let's actually explain what I meant of that. So what I meant is, so I said, where outcomes are equally likely. So if we have our dice again, each side is equally likely. We have a chance of 1/6 of each side being rolled if we had our dice. So the probability of one of the outcomes happening, so probability of any event, so let's say what is the probability of a 1, then to do that, all I have to do is I have to do the chance of the event is basically just the number of outcomes I can have of the event. There's only one way I can get the event divided by 6 different ways I can have it. If I said, what's the probability of a 2, then the probability of a 2 would basically be how many ways can I do that? Well, it's 1/6 again. So now if I change that question and I said, what is the probability of even numbers? Then how many different ways can I have the outcome occur for even numbers? Well, I could have 2, 4, or 6. So there's 3 ways I could have it out of a total of 6 ways, and each of them are equally likely. So that would give you a half. So essentially all of this stuff is basically how you would kind of start to understand probabilities. And if there's anything you want to get from all of what I've just said, is essentially you don't need to remember all of this completely, you just kind of need to understand the concept. So it's the idea that in stats, when we're doing probabilities, we do an experiment. That experiment will give you some sort of outcome. An event is a collection of those outcomes, and a sample space is all the possible outcomes. So when we're actually doing probabilities, we just kind of want to take a look at something like the event that we're looking for divided by all the possible outcomes which you could have, which is a sample space. So in the sense where we got like a half for the even numbers, it's kind of saying something like, well, I would expect 1, 2, 3, 4, 5, or 6. And for even numbers, then the only way they can get that is 2, 4, 6. So obviously here you can see there's 3 ways you can get even numbers and 6 ways you can get any of the possible outcomes. So that's why your answer is 3/6. So that's just like kind of the basics of all of that. And you probably already know this, but basically your probabilities can only be between 0 and 1. So 1 means it's impossible. I know that can never happen. I can't roll a 6-sided dice and roll an 8, for example. That's impossible. And 1 would be certain. So I know 100% if I do some kind of experiment, I 100% know the outcome. So if I roll a dice, I can guarantee the number is definitely either odd or even, because that's the only thing I could possibly do. So usually your probabilities are going to be somewhere in between this range. So don't worry if that was a little bit confusing. Let's clear stuff up by going through a couple of examples. So let's take a look at examples. Let's say I have a random number generator that I have. Well, let's have 2 random number generators. And what these do is they generate me a number between 1 to 4. And the question would be, I use both random number generators, generate numbers, and to find my final answer, I add the numbers. So add both outcomes. So for example, if I had machine 1, and I had machine 2, then if machine 1 gave me 4, machine 2 gave me 2, then my final answer would be 6 because I'd add them up. So that's how my machines work. They just add up all the numbers. And let's say the question was asking you, could you tell me, based on that, how many ways can I get exactly 4? So that's the first part of the question. And the second part would be asking me, how can I get a score which is more or equal to 5? Something like that. So let's start off with how we'd solve this question. So the easiest way to do this would be to draw some sort of diagram over here. So we could basically put in all the different things we could roll. So we could get 1, 2, 3, 4, 1, 2, 3, 4. And then let's add up all the different numbers we could get. This could be machine number 1, and this is machine number 2. So for machine number 1, we get 2, 3, 4, 5. This would be 3, 4, 5, 4, 6, 8, 7, 6, 5, 7, 6, 5 there. So that's what would happen if I added up the numbers. All I did was add up. So 1 plus 1 is 2, 2 plus 2 is 4, 3 plus 2 is 5. Like so on, you can see I've just added up the numbers to get these. So now that I've got this, we're trying to figure out how we can get exactly 4. So how many total outcomes are there? So the probability of getting a 4 is equal to something over 16, because there's only 16 possible outcomes. And referring to what you said before, this is actually our sample space. This is all the possible answers we can get. So based on that, we add this up and we get 60 numbers. And how many of our numbers are 4? Well, there's 1, 2, 3. There's only 3 ways. So that becomes 3. So 3 over 16 is the probability of you getting a 4. So then what's the probability of you getting a score which is more or equal to 5? So the probability of the score being, or let's write that like this, score is more than or equal to 5 is equal to, again, there's only 16 different things we can do. However, from these 16, how many of these are more than or equal to 5? So that would be everything over here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different things. So the answer for this would be 10 over 16. So there's 10 over 16 different ways to do that. And that's a probability of your score being more than or equal to 5. So hopefully that was quite easy to follow and easy to understand. So those are kind of standard questions that you can expect in probability, nothing too difficult. So apart from that, sometimes you might have different kinds of tables in order to answer it. So let's say how long we can say, or let's say how long people spend on average having their lunch, for example. So the average lunch times, and let's say the frequency of that. So let's say our lunch times range between 5 to 7. Then let's actually do this in a way that you can expect in the exam. So we might say lunchtime is equal to t. So let's say your lunch times could be between 5 to 7. Then between 7 and 9. And then between 9 and 11. And then the frequency of each of those was 7, 10, and 11, something like that. So someone said this question and said, okay, based on this question, what is the probability that someone will spend less than 9 minutes? So what's probably t is less than 9 on their lunch? And so yeah, let's figure out how we answer that question. So for something like that, all we really need to do is we have to basically take a look at this and say, okay, for the total frequency, we have 7 plus 10 plus 11. So in total, there are 28 different people who have done this entire thing. So again, our sample space is that's a sample space. And how many of these people are less than 9 minutes? Well, everyone who took 5 minutes to 7 is less than 9. And everyone who took between 7 to 9, since there's I should have had less than sign here, is also less than 9. No one in this bracket is less than 9, since this is more than or equal to. So basically I only count these two people here. So I do 7 plus 10 up here. And that gives me 17 over 28 people. So that would be the number of people who I can expect to be over in about that kind of time frame. So that's how you can do one type of question. Another question might be, what's the probability that t was less than 10? Now for this one, you can see we don't really have a way of doing 10. And let's just say I change this number slightly. Let's change that to 12 just to make the numbers easier. So if I did something like that, again, there's only 28, or actually not 28 anymore, there's only 29 ways I can do this. Then once I've done that, what ends up happening is these people are less than 10 minutes, these people are less than 10 minutes, but here I've got 9 to 11. So in order to fix that, you can see that 10 is exactly halfway through. So using interpolation, what I'll assume is about 6 of these people count in there. So what I'll do here is I'll say 7 plus 10, but since 10 is only halfway through the third class, then all you can do there is add on the 6. So if you do that, you will get 23 or 29, and that's your probability. So that's kind of how you answer those kinds of questions. So hopefully that kind of made sense. Essentially what you want to do is you want to understand what's your sample space, and then how many ways can the thing that you're trying to get, how can it occur? So here I said in this question, there's 29 different ways that things can occur, because I got that from here. And then I said, well, t is less than 10. Well, that's 7, that's 10, and that's half of that, which is 6. Add them all up, and then get what this part here is. So that's pretty much it. So that's like very basic single event probabilities. Yeah, and that's how you want to kind of understand it. If you want a kind of a way to understand it, you can say the probability of an outcome is equal to the ways you can get the outcome all over the sample space. That will essentially give you the probability. So that's kind of what we've done. So you can go through a few exercises and hopefully all of that will make some sense. Okay, so now let's move on to Venn diagrams. So let's try and understand what exactly is a Venn diagram and what is it used for. So Venn diagrams are basically a nice way for you to represent all these events and stuff on a graph, and it makes it a lot easier because you can put like frequencies, probabilities, and all those things in different parts of a Venn diagram, and they'll tell you different things about it. So you've probably heard of something called the event A and B. And even though in first year stats I don't show you the symbols, I'll show you that anyway. So that would be A and B. That's how we tend to write A and B. And this represents the middle part of the graph, where our two circles, this is a circle for A, this is a circle for B, this is where both A and B are occurring, and that's basically where they overlap. So that's what A and B means. It means that if A is occurring here, then B is also occurring here. So just to give you a bit of a way to navigate your way around these graphs. Let's say my event occurred here, then it occurs within A. If it occurs here, it occurs in B. If it occurs here, it's occurred inside A and inside B because it's in both the circles. And if it occurs here, it's in neither A or B because it's in none of the two circles. So yeah, like I was kind of saying that A and B is the intersection. The next thing you need to learn is A or B. A or B. And the sign for that is A, U, B. Again, you only learn that in second year, but I'll show you that now. And this is basically everything which includes A or includes B. So this would be everything. So basically when it's A or B, you just shade all of A, shade all of B, that's it. When it's A and B, you just shade the parts which overlap, like that. So you know if it was A and B and C, something like that, then you'd only shade this middle part. Whereas if it was A or B or C, you would actually shade all of that, and all of that as well. So those are the two. And then there's a final one which you need to know, which is known as the event not A over there, and we tend to call that's how we show that in probability. So not A means basically everything which is not inside A, and that means also this part, because this part outside is not in A either. So that's how this part works. So these are three parts you just need to be kind of familiar with. A and B, A or B, and not A. So yeah, it'll be quite good to show you some examples because there are some word questions which people often get confused with. So we'll show you a few examples of how these work. So let's say we have a question here where it says, I have a class of 40 people where 9 people play football, 5 people play cricket, and 3 people play both. So I want to find the probability of someone who is, what's the probability if I pick a child that they do not play cricket, for example. So not cricket. What's the chance they do not play cricket? That's the first question. And then let's take a look at a question where what's the chance that if I pick someone, they play neither football nor cricket? So then the probability of neither football or cricket. That's the second question. So before we do that, the actual main part of these questions is you just need to fill out this diagram. Once you fill it out, solving the questions is not very difficult. So how can we start? Well, there's 40 people in the class. So we know for sure that 3 people play cricket and football. So that's the only one we can be certain for. So that's the first one that we put in. You always put in the one which is got everything involved in it. The reason I can't put 9 for football here is that, well, if I put 9 for football here, and let's say it happens that 5 people play cricket here, then 9 plus 5 is equal to 14, which is more than the number of people allowed to play football. So that's why you don't just start by putting 9. The 9 here and the 5 here just means that everything in this circle adds up to 9, and everything inside this circle adds up to 5. But we don't know which ones are here, and which ones are here, and which ones are here, because they're all shared. So the one that you should always start with is that the fact they're both 3. So you put in the 3. So now I've done that, I can cross this out. Now I can start filling out the rest of the information. Since I know there's 3 people here and 9 people play football, then this one has to be 9 minus 3 over here, because 9 people play football in total. So if I put in a 6 here, this circle now adds up to 9. So that's how many people play football. So now I can cross that one out too. Same for cricket. I know 3 people play cricket here, and there's 5 in total, so this one must be 5 minus 3, which is 2. And now I can cross that one out as well. So now I know in total we've got 6 plus 3 plus 2 people who play football and cricket between themselves. So if you add them all up, that gives you 9 plus 2, which is 11. So that means in my class of 40, there's 11 people I've accounted for. So everyone I haven't accounted for would be outside over here, which is 40 minus 11, which would give me 29 people. So, and that's it. Now I've done this, the questions are very easy. So what's the probability if you're not playing cricket? Well, there's 40 people in my class in total. And what's the chance that you don't play cricket? Well, either it's people here or people here. So the people who only play football and the people who play neither. And that's 35 over 40 over there. So that was pretty simple to do, nothing too hard to understand there. And that's pretty much it for that. And then we have the next question, which is what's the probability that they're neither F or C? Well, again, there's 40 students in total, and the ones who play nothing are this lot here. So the answer to that is just 29 over 40. And that's pretty much all you have to do in these questions. The main part is just be careful, don't make that a 9, don't make that a 5 just because you saw these numbers here. Always start with the one which is both, or the one that isn't common for everything, and then from that, once I figured out this, then I was able to figure out this part, and then I was able to figure out this part, and then finally the whole thing. So just start with the one which is usually both or everything in the middle, and that will make it much, much easier for you to answer the question. Cool. So since we've done that one, we can now carry on with this question and show you a slightly harder one. So there's another circle here. So let's say now we've introduced another sport, which is golf. And now I wanted you to find out what's the probability that the person plays, let's say, football only. What's the probability that he does not play golf? And let's say the last question would be they don't play any of these sports, so plays none of them. Okay, so again, it's actually the same concept of the one we literally just did. All you got to do is fill out this graph with the numbers you've got. So like we said before, we want to do the same thing. Start with the one which is all and put that straight into the middle. So if we do that for all, we'll get 2 right in the middle, and that's for sure. There's 3 people who play football, golf, and cricket. So since I've done that one, I can cross this out. And now let's take a look at cricket and golf. So once I've done the one with all 3, now let's do the ones which are sets of 2s. So people who play cricket and golf, there are 10 people who play cricket and golf. So that means, where's cricket and golf? Where does that intersect? That's this part here. So that means we've already got 2 people there. So 8 people must be playing that. So now this adds up to 10, just like we wanted. So now I can cross that off. For football and golf, we have 8 people. So here we've already got 2, so we'll make that a 6. That means that this adds up to 8. We can cross that off now. Football and cricket is 6. So now you can see here, we've only got 2, so to patch that up, we have to put in a 4, and that makes that up. Now we've done all the ones with sets of 2s, we can do all the sets of 1s. So 17 people play football. So if you add all of that up, we've got 4, 6, and 2 already in football, which means 12 people, which means to finish off, we need a total of 5 there. For cricket, 4, 2, and 8 again adds up to 14. So this time we've got 14, so that means only 3 people can be playing cricket over there. And again, that adds up to the right number. And the rest play golf. So 2 plus 8 is 10, plus 6 is 16. And the ones which are left would be 7. And that makes up everything. So we've accounted for golf. And if you add up all these circles, you'll see that it all adds up. So now we've got the people who are outside. So if you add up everything, 5 plus 4 plus 3 plus 6 plus 2 plus 8 plus 7 equals something. So that would be, if I just try to do that, there's 17 people who play football, plus 3 is 20, 28, and 35. So there's 35 people in total inside. So that means here we should be 100 minus 35, which is 65 people play none of them. So if you had to answer this question, how many people play football only? Well, that would be these 5 people here. So how many people in the total? There's 100. How many people play football only? 5 out of 100. How many people do not play golf? Well, anyone inside this circle plays golf, and anyone outside this circle does not play golf. That means the ones in the squares are not playing golf because outside of this circle over here, which I've got. So 5 plus 4 is 9, plus 3 is 12, plus 65 is 77. So 77 out of 100 people do not play golf. And how many people play none of the 3? Well, that's everyone who's outside the circle, which would be this one here, and that would be 65 over 100. So the kind of questions you'll get will either be usually these 2 circle Venn diagrams or 3 circle Venn diagrams, and you'll be given a bunch of information. Just remember, start with the one which has information about all 3, then all 2, then one of them, and then just subtract to find the one outside. And actually these questions are pretty simple if you just follow that. Same thing for this one. Start with the one which has all 2 in it, then start with the ones which are just single ones, and then find the one outside. So if you, as long as you do that, you fill that in first, and then you just check up how the thing should add up, then it all kind of works out. So for Venn diagrams, actually, that's pretty much it. It's a pretty short topic, and hopefully there's not too much that you need to take a look at that to understand. So let's now move on to mutually exclusive and independent events. Okay, so next up, we're going to take a look at mutually exclusive and independent events. And these are 2 things which people I've seen get wrong quite often. So people often mix up the definitions for mutually exclusive and independence. So I'm going to try and show you how the 2 are different in this part over here. So with mutually exclusive things, what I'm trying to say is basically, if event A occurs, then that means B can't have occurred. So that's why you can see that these 2 Venn diagrams here are separate and they're not overlapping. If they weren't mutually exclusive, then they'd have this overlap where this middle part would be shaded in. And that means that in this part, for example, if A has occurred, then B has also occurred. But if they're mutually exclusive, it means if something happened in A, you can see that anything I have in A can never be in B. You can see they're always separate. There's no overlap. So being mutually exclusive means that, yeah, if A doesn't happen, B can't happen, and same for if B happens, A can't happen. So the way you write that in the probability notation is the probability of A or B is equal to the probability of A plus the probability of B. And why is that? And that's because our 2 circles are separate. So if you want the 2 probabilities, we just add up these 2 circles together. And that's pretty much it. That's mutually exclusive events. So independent events means that if A occurs, then it has no bearing on B. So for example, if I go shopping today, it has no bearing on my friend in another country going to bed at a certain time. Those 2 events are completely independent. So any events which have nothing to do with each other, don't affect each other, are independent events. So something which is not independent would be if it's raining, I took my umbrella. Usually if I take my umbrella, then it's probably dependent on the fact it's raining or not. So independent events are where event A has no effect whatsoever on event B, and hence, if you want to find the probability of A happening and B happening, because these 2 don't have an effect on each other, the probabilities are just the probability of A times the probability of B. That's quite simply it. So these are the 2 rules you need to know. Mutually exclusive, PA plus PB, and independent is PA times PB. So hopefully that clears up how the two are different. So let's take a look at a couple of examples of how we solve questions like these. So we can also use this idea here to prove independence, and we'll get onto that later. So let's say we had a question like this where I said the probability of A was 0.3, probability of B was 0.4, and someone said find the probability of A or B. Well, quite simply, the probability of A or B would be this probability plus this probability, since they're mutually exclusive events, and we said A or B is just those two added together. So this would just quite simply be 0.3 plus 0.4, giving us 0.7. And therefore we can tell that the outside part should be 0.3 because 1 minus 0.7 is 0.3. So the probability of A but not B, well, what is that probability going to be there? The probability of A happening but not B. Now the thing is, they're mutually exclusive events. So A but not B means that pretty much it's the same as having the probability of A, because in this case we know they're mutually exclusive. So B happening has no effect on A happening. So probability of A but not B is basically just the probability of A, which is 0.3. And you can see that here, the probability of A but not B is 0.3, since there's no way of B overlapping with that. If I had an overlap of A and B like that, then there'd be some overlap and then we'd have to take care of that. But because they're mutually exclusive, there's no overlap over there. So that part is quite simply just 0.3. Now the probability of neither A nor B is the probability we've already found over 0.3 down there, because neither A happening nor this happening, well, that's just this one out here, 0.3. So I hope that's a simple type of question to understand. Let's take another look at another kind of question. So let's say A and B are independent, and we say the probability of A is 0.3, the probability of B is 0.2. So what is the probability of A and B? Well, normally, because we know this is independent, we can quite simply just multiply this times this to find A and B, since that's our rule for independence. So here it's just 0.3 times 0.2, which should be 0.06, I believe. And that's going to be your answer for the probability of A and B. That's probability of A and B, that one there. And that's because they're two independent events. So that's why we can just multiply these two numbers together. So those are just two simple examples to show you how mutually exclusive things can be used, and here how independent things can be used. So now let's actually move on to a slightly bigger question on something over here. So let's say I give you this Venn diagram and I ask you, can you find the probability of A happening, or B happening, or both happening? So probability A or B or both would be the probability of A, the probability of A happening, or B happening, or both, so everything in between. So basically what we're trying to say is just everything in these circles here. So it's quite simply just going to be part A, just 4 plus 6 plus 7 plus 10 divided by how many we have in total in this question. So in total, how many different things do we have? Let's add that up. So we've got, this is 4 plus 6 is 10, 17, 27, 37, 52. So that's just 52. So the answer for this one will be 27 over 52. That's the probability A or B of both happening. And the next kind of question you often get asked is reading A and B, so these are just probabilities of reading books A, B, and C, are those probabilities, or are A and B independent of each other? And the way you solve these kinds of questions is quite simply, you need to find the probability of A, then you need to find the probability of B. So to do this, we have to find probability of A. So that's just 4 plus 6, because that's all we've got in that circle. And we just have to take that and we divide that by the total number. So 4 plus 6 is 10 over 52. That's going to be probability of A. Then you find probability of B next. So the probability of B would be 6 plus 7 plus 10, which gives us 23 over 52. And once you've got the probability of A and the probability of B, well, the thing is, if you take a look at the diagram itself, this represents the probability of A and B. So the probability of A and B according to our diagram should be 6 over 52. However, we can check this, because if we know that they're independent, then P of A times P of B should also give us this equation here. So let's actually put in our numbers for P of A times P of B. That gives us this number, which gives us 230 over 52, which squared. So I'll just check that in my calculator. That gives us a value of 2,704. And these two numbers are not the same as each other. So these two numbers, since they're not equal to each other, we can say they are not independent. So they are not independent events. If they were the same as each other, then you would say they're independent. So whenever a question asks you, are these two events independent, what you should do is find probability of A, find probability of B, multiply them together to get a certain number, and then from the graph, read what the actual probability of A and B shows us, and then if that number you got matches the number you got here, then you know the two events are independent. If that's not the case, then unfortunately they are not independent events. And that's all there is to figuring out that kind of question. So I hope that that helps. So now we can move on to the very last part, which is probably the easiest part. So for this question, we're going to take a look at tree diagrams. And you've probably seen these in GCSEs, and they're nothing too difficult in year one stats either. So tree diagrams is kind of tell you the outcome of probabilities as they're happening, like one after the other. So like I pulled a ball out of a bag, then another one, then another one. So you just draw more and more trees. So I guess the easiest way to kind of go through this is just go through examples. So a bag has 8 blue counters and 7 yellow counters. So straight away I can say there are 15 counters in total. Just write that as a note. And then we know that the probability of both being green, we want to find the probability of both being green and the probability that they're different colors. Well, before we start, let's say that we have to take this. So in this question, let's say, I haven't written it down, but you're supposed to take 2 balls. So you take first pick, then after that you take another pick, and you don't replace the balls after each other. That's important. So on my first pick, what's going to happen? What's the probability that I pick a blue counter? My first one, I just read the question doesn't make sense. This can't be green. This has got to be blue. We only have blue and yellow counters. So what's the probability that we have a blue counter, and what's the probability we have a yellow counter first? So probability of a blue counter is out of 15, we have 8 blue counters, and we have 7 over 15 yellow counters. Now, if we already picked a blue counter in our first pick, that means there's only 7 blue counters left, and because we've picked one counter, there's only 14 things left. Here there's only 14 counters left, but then there's still 7 yellow counters. In the case at the bottom, if there's 7 over 15 yellow counters and we pick a yellow counter, then there's only 14 counters left and only 6 are yellow, and here there'd be only 14 counters left, but all 8 would be blue. So that would kind of give us our tree diagram there. And if someone asked us how to solve it now, we could quite easily solve part A, that what's the chance that both are blue? Well, for that we just travel along this part of the graph and this part of the graph, which are corresponding to these two probabilities. So we just say 8 times 15 times 7 over 14, which is 56 over whatever that is in my calculator again. 15 times 14, 210. So that's the answer for your blue counters. And what's the probability that they're different colors? Well, there's 2 ways they can be different colors. I could either pick blue, then yellow, which means I have to use these 2, or I can pick yellow and blue, which means I use these 2. So there's 2 different ways that can happen. So I do 8 over 15 times 7 over 14 plus, so that was taking this part here, and now I'm going to take this part here. That would give me 7 over 15 times 8 over 14. So that, if I do put that together, you need 56 again over 210 plus 56 over 210, which is equal to 112 over 210. So that's the answer for them being different colors. And in probability, that's pretty much all you need to know for year 1. So the main things you need to really understand, if I have to kind of go through all the chapters we've done again, would probably be just understand from the beginning what the different parts are and how to find single kind of probabilities. But I think that's a part that everyone's fairly comfortable with. The key part that you really need to understand is the Venn diagrams. So if someone asks you to shade Venn diagrams in or put in the different numbers like you've done here, you need to be comfortable with that, with 2 or 3 circles. Apart from that, make sure you know how to do mutually exclusive and independent events. these are the different kind of questions you can be asked. These two are the easiest type. This is the kind of type you can expect in year 1 stats for question 3. So something like, are these two really independent? What's the probability of A or B or both? And that should be okay. Usually in your exams, year 2 stats does build upon probability quite a bit. So a lot of your questions will probably be from that chapter, but for like the first parts of your questions in your paper, this is the kind of stuff that you can expect. And then finally, the tree diagram stuff is not very difficult either. And again, in year 2 stats, I'll build upon that. But for year 1, it should be fairly simple. There's not too much content and it's fairly easy to kind of go through. So hopefully that should be good enough. And then for our next video, we'll probably be taking a look at statistical distributions. And yeah, just if you found this video helpful for understanding probabilities, please just share it with your friends so I can continue making more in this series. Thanks a lot, and I'll see you in the next video. Welcome back to another video in our statistics series. So today we're going to be taking a look at statistical distributions. And this is usually chapter 6 in if you have any of the textbooks that you follow here in the UK. So this is a chapter which is actually not too difficult if you just follow along. A lot of it at school can seem a little bit confusing, just like the rest of stats as a whole. And that's because there's quite a few definitions you have to learn, but the kinds of questions you do won't be too difficult if you're able to understand the chapter previously on probability. So in this lesson, we'll be taking a look at how to understand what is a discrete probability distribution. We'll try to understand what the binomial distribution actually is. And using the binomial distribution, we'll figure out how to find probabilities from there and how to get cumulative probabilities from there. So this is a relatively short chapter, so there'll be quite a few exercises in this video compared to theory. So hopefully it should be quite easy to follow along. So let's just jump right into it. So let's take a look at what are discrete random variables. Well, to understand what a discrete random variable is, let's break it down into what does discrete mean? What does it mean to be random? And we already know what a variable is. A variable is something which can take any value. So let's just try and understand each of these 3 parts of what a discrete random variable is, and that should make it a lot easier to understand this word whenever someone says it to you in statistics. So a random variable is a variable whose value will depend on the outcome of a random event. So this random event could be me rolling a dice. So if I roll a dice, the outcome of this random variable depends on what happens when I roll the dice. So if I roll the dice, I could get a 1, 2, 3, 4, 5, or 6, but I don't know what's going to happen until I've done this random event and I've got the random event giving me some sort of outcome. So that's a random variable. Its value, and normally we might call it like x, y, or z, doesn't really matter. But let's say you said x is the value of a dice roll, then this variable would depend on what happens when I roll the dice. So that's what a random variable is. So the sample space is the same thing as what we said before in probability. It's just all of the values that a random variable can take. So before we said the sample space is all possible outcomes. So that's pretty much the same thing here. It's all different possible outcomes. So in the case of a dice again, that would be equal to 1, 2, 3, 4, 5, or 6. That's the sample space for my dice. So then now we have to understand what does it mean to be discrete. So if you're discrete, that means you can only take certain values. So we've already talked about what it means to be discrete and continuous. So this is the same thing. You can only take certain fixed values. So a dice can be like 1 or 2, 3, etc. But it can't be 1.5, 1.6, 1.111, stuff like that. It can only be those fixed values. Then moving on from there, we have to understand what does it mean for you to be random? Well, random means that we don't know the probability until we do the experiment, because if we knew what the outcome would be without doing the experiment, then it's not random anymore. So in order to know the probability, we have to actually do the experiment, and that's what it means to be random. So you don't know until you've done the experiment. And then finally, let's understand what is a probability distribution. A probability distribution just describes the probability of any outcome in the sample space. And what I mean by that is, let's start by this. It says it's the outcome in any sample space. So what is our sample space? A sample space is 1, 2, 3, 4, 5, 6 rolled dice. And a probability distribution will describe the probability of each of these outcomes. So in a fair dice, this should be equal to 1/6 on each. So that's kind of what a probability distribution is. It's telling you what outcomes you have, and it's also going to tell you what is a probability of each of those outcomes. So that's the idea of a probability distribution. So hopefully if you put all of those separate words together, you can understand what we mean by a discrete random variable, otherwise known as a DRV, in case I just can't be bothered to write that out anymore. So yeah, that's pretty much that. So let's actually move on to seeing how we can do some questions on this. So let's say one of the questions, actually, oh yeah, I realized before that I should probably also show you how can you actually show a probability distribution. So there are actually three ways that you can show a probability distribution. One is through the probability mass function, which we'll take a look at. One is in tabular form, and one is as a diagram. So we'll go through each of the different ways you can express a probability distribution. So the probability mass function is just trying to say that the probability that my discrete random variable x takes on a value x, which I have to choose, is 1/4. And this is for values of 1, 2, 3, and 4. So this means the probability that x equals 1 is equal to 1/4. The probability that x equals 2 is equal to 1/4. The probability that x equals to 3 is 1/4. And you can see the pattern and so on for the last one. So this is saying, in order to find the probability for x, I can put in any of these numbers into here, and that number will have this probability. Now here it's fixed as 1/4. If you imagine the probability was x equals x is equal to, let's say, 2 lots of x divided by 10, I'm just making that up on the spot. Then if I put in, like, for example, 1, then the probability that x is going to equal to 1 is going to be equal to 2 times 1 over 10, which is equal to 2 over 10, which is 0.2. So that's how you can use probability mass functions to find probability. So you basically input these numbers in there to find it. And if there's an x here, then you replace that x over here as well. But we'll look at some questions on how to do it. And just note that if you sum up all these probabilities, all the probabilities should add up to 1, since the rule is that probabilities always add up to 1. So apart from that, we can also express it as a table. So here you can see we've said the value of x can be 1, 2, 3, or 4. And these values go in here again. And the probability of, for example, x being 1 is equal to 1/4, and so on. So this is another way you can write it in a table form. And then the final way is you can do it in a diagram. So in a diagram, we've said the y-axis is a probability x equals x. This is probably this is a chance of, or this is just x itself, and then the probability of x being 1 is 1/4, x being 2 is 1/4, 3 is 1/4, and 4 is 1/4. Sometimes you might have different probability distributions, which might look something like this for different things. So that's one you might have seen quite often because it's something like that. In this case, it's just straight because it's just a straight line. So when we have all of these probabilities, if the probabilities are all the same, like in this case, the probabilities are all 1/4 each, then we call this a discrete uniform distribution. And the fact that shows you it's straight is the word uniform. Uniform means that everything is the same. So yeah, those are the three different ways in which you can express the different probabilities and the distributions. So hopefully you're comfortable with that. And we'll take a look at some questions on how you do that. Okay. So now let's try to do an example question on how to use these probability distributions. So we'll go through 3 different examples of how to use these, and hopefully that will get you familiar with what we've just learned. So let's say we toss 3 fair coins, and we want to figure out what are the possible outcomes we can get. And then we want to draw the probability distribution as a table and as a PMF. So we'll show you both ways to do it. So first of all, if I'm tossing 3 coins, what are all the possible outcomes? Well, I could either get 3 heads. That's one of the possible outcomes. I could either get heads, heads, and tails. I could get heads, tails, tails. I could get tails, head, heads. Or I could get tails, heads, tails. Then apart from that, I could get tails, tails, head. And finally, I could get all 3 tails over there. So as you can see in my probability distribution, there should be 1, 2, 3, 4, 5, 6, 7. And there should usually be 8. So I'm probably missing 1 out in here. So that would probably be this one here, which is heads, tails, heads. So because there's usually 8 for this kind of question. So yeah, you can see all these are different, and these are your different possible combinations you can have. So this is the answer to all the possible outcomes you could have. So there's 9 possible outcomes in total. Okay. So now the next part of the question says, can you show this as a probability distribution, one as a table and one as a PMF? So if we're doing it as a table, it's quite simple. We'll say the number of heads, like that, and we'll call that x. And beneath it, you can always just write probability of x equals x. That's always the same. And as a table, let's put in, there's only going to be 4 columns. And the reason is I can either get 0 heads, 1 head, 2 head, or 3 heads. So since I know already that there are 8 possible, oh, my bad, I wrote 9 before. That should have been 8. So there's only 8 possible outcomes. So I know all these probabilities are out of 8. So how many of these have 0 heads? Well, the ones which have 0 heads are only this one here, actually, the one that everything is tails. So I have 1 out of 8 for that. How many of these only have 1 head in them? So that would be this one here, this one here, and this one here. So that's 3 out of 8. How many have 2 heads in them? Well, that would be this one here, and this one here. So again, that's 3. And which ones have all 3 heads? Well, that's just heads, 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 which is 1. And that's it. That's all you need to do to draw a probability table. Now that you've got the table, actually, we can also represent this as a PMF. So in order to do that, we'll say the probability that x is equal to x is going to equal to, and this is how you normally write it. You draw something like that, and you'll write down all the different probabilities. So you can see that here we have 1/8, and here we have 3/8. So what we'll do is we'll write the common ones we've got down. We've got 1/8, 3/8, and then as convention, you always write 0 here. So which cases of x gave us 1/8? The only ones that gave us 1/8 were 0 and 3. So what we write here is when x is equal to 0 or 3, the probability distribution is telling us that when these are 0 or 3, the probability is 1/8 over here. In which case is it 3/8? Well, that's when x is equal to 1 or 2. And then we write it's 0 otherwise. In this case, none of them are 0. So if we have any number, like let's say someone said, what's the probability that x equals to 7? Well, x equals 7 is none of these or none of these. So it falls into the otherwise category, which tells you the probability is 0. That's why this probability would be equal to 0. But that's pretty much it. That's how you can draw your probability mass function for a question like this. So now let's move on to another example. And let's say I have a biased 5-sided die, and the number I roll is going to be denoted by x. So x is my random variable, which I can only know the value of this variable once I've done my experiment, which is rolling this 5-sided dice. So depending on what happens when I roll this dice, I'll get an answer, which is what I put into x. And I'm given that the probability distribution for this is x equals x is equal to k over x. So I know what my thing is. So first thing is they want me to figure out what is k. So how can I solve a question like this? Well, first of all, before we start, let's draw our table for this question. So for x, the probability that x equals x, then the values that x can take is it's defined for as a 5-sided dice. So there's only 5 things I can roll. I can roll 1, 2, 3, a 4, or a 5. So if I have all of those, then that means that the probability that, for example, that x equals to 1, how would I do that? So I know the probability that x equals x is k over x. The probability that x is equal to 1, all I do is put that 1 into this x here, so I get k over 1. The probability that x is equal to 2 is just k over 2, and so on. So all you can see, all I've done is I've just had to replace the x here with whatever is over here. So I put 1 there, so I put 1 down there. So it's just k over 1, k over 2, k over 3, k over 4, and k over 5. Now I know based on the rules of probability that all of these will add up to 1. So the probability of k over 1 plus k over 2 plus k over 3 plus k over 4 plus k over 5 should equal to 1. So now all I need to do is solve this equation. And this is a fairly simple equation to solve. So I just take the k out as a factor, and then I have 1 over 1, which just gives me a grand total of 1, plus a half, plus 1/3, plus a quarter, plus a fifth, and that equals to 1. So now I just need to add up all of these, which means I need to find the common denominator, unfortunately. So taking a look at that, I guess we could do 60. So 1 plus, if all of them are over 60, then the answer for this one would be 30, this would be 20, this would be 15, and this would be 12. So now let's add them up. So k is 60 over 60. So I'll just rewrite the 1 as 60 over 60. Plus 30, plus 20, plus 15, plus 12 equals to 1. Therefore, it's quite a long question, but let's just carry on. So 60 plus 30 is 90, 110, 125, 137 over 60. Hopefully I've added that correctly. Equals to 1, therefore k is equal to 1 divided by 60 over 137 over 60. Or what I was trying to say is if you divide it by 137 over 60, it's the same as multiplying it by 60 over 137. So it's just 60 over 137. And that is your answer for k. So now we know what the value of k is. That's pretty much how I do it. So it seems like quite a long kind of question in terms of how you do it. But that's pretty much it. So now the next question says, can you write the PD as a table? Well, we know what k is now. We know that k is just equal to 60 over 137. So all we need to do actually is, if I copy this table down for part B, and we put that down over here, then all I need to do is, for these questions, is just replace my k with the value of k I actually got. So k divided by 1 would simply give us 60 over 137. Then k divided by 2, we have to divide that one by 2. So we'll have to go through that. I'll just pause the video here and I'll actually calculate it because I realize it's quite a long one. So I'll just do all the calculations and skip ahead. Okay, so back to the video, you can see we've just calculated the numbers and put them in. Now the key thing was actually it wasn't that difficult. I had written a different number here before, but that was before when I didn't bother to cancel out the numbers we had at the bottom. But if you cancel them out, you can actually cut it and get a number like this. But basically, if you do the calculations, these are the numbers that you'll get, and this will be the probability table that you need to do. So now in the questions it asked us, what is the probability that x equals to, or x is more than 3, is between 2 and 5, and it's more than 5. So if we have that, if we just put that down here, and let's actually try and solve each of these probabilities, then based on that, what we can see, the probability that x is more than 3, which values would that one be? Well, that one would be more than 3 means you have to be, can't be 1, can't be 2, can't be 3. You have to be either 4 or 5. So the probability that x is more than 3 would be the probability of x is 4 plus the probability that x is 5, which adds up to 27 over 137. And how did I get that? I just added up these two because that's from these two probabilities. Then what's the probability that x is more than 2? So it's everything here, but it's less than 5, so it's everything this way. So more than 2, less than 5 means basically only 3 and 4, since that's more than 2 and less than 5. So again, we add up those probabilities, 20 over 137 plus 15 over 137, and you get 35 over 137. And finally, what's the probability that x is more than 5? Well, unfortunately, there's nothing else after 5, so the probability of x being more than 5 is just going to simply be 0. And that's it. That's how you solve this kind of question. So you can't get these kind of questions where they ask, solve k, and to do that you need to put all your values of x into your graph first. So you get this table, then make them all equal to 1, add up that, make that equal to 1, and then solve it for k. That's it. Once you have k, you can put it back in, get your table, and then these questions are quite simple. So that's how you do that second kind of example. Now let's take a look at a third and final example. So if you have a spinner and you spin it, we have a spinner here which basically has 3 green portions to it, and the rest of them are all red. So as you can see, there are how many portions are? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 portions, of which, let's draw them black. 8 portions, of which 3 are green and 5 of them appear to be red. So based on that, the question says you spin the spinner until you either hit the green part or you span it 5 times. So if I span it 5 times and I haven't hit a green one yet, then I stop. So what's the probability distribution of how many times you spin X? So to do this, we need to figure out. So X is the number of times we'll spin it. The probability of X being X, basically we just need to fill out this probability distribution. So we can only really ever spin it either once, because we either land in the green straight away, or we spin it twice, 3 times, 4 times, still haven't landed in green, and 5 times. So 5 is the maximum time, because after 5 we stop. So how can we find each of these probabilities? Well, to do that, we need to say what is the probability that we will land or stop the first time. The only way we can stop the first time is if we land on a green straight away. So let's say we landed on a green straight away. The chances of that happening out of 8 things, only 3 are green. So that will quite simply just be 3 over 8. So now so this is simply coming from, if I make a note, from 1 green. Now what is the probability of us landing and stopping after 2 attempts? So that's if we had a red first, and then, so we have 1 red, and then that is followed by a green, meaning that we stopped. So the chance of 1 red followed by a green, well, a red has a 5 over 8 chance, times that by the chance of green, which has a 3 over 8 chance. So then we have a 15 over 64 chance of getting a number like that. So that's what we do for this one over here. Next, what's the chance of getting 3? Well, for 3, what happens is you have to have 2 reds followed by 1 green. So to do that, we have to get 1 red times another red times 1 green, which will give us that. So 5 times 5 will give us 25 times 3 gives us 75. So 75 over whatever 8 times 8 times 8 is. I'm just going to write it like that. Then same one for this. How can we have it 4 times? Well, that's 3 reds and 1 green. So that would be 5 times over 8 times 5 over 8 times 5 over 8 times 3 over 8. So that would be 125 times 3, which will give us 375 over 8 to the 4. So just for consistency, if it's easy, I can write this one as well as 8 squared instead of 64. And then finally, how can we have this as being 5? Well, that means if all 5 are going to be reds. So how can we get 5 reds? Well, that's if I have 5 over 8 and I do that 5 times. So what's that going to be equal to? That's 5 times 5 times 5 is 125 times 5 is 375 times that by 5. So let's just put that into our calculator. Lost track now. So that's 3,125 over whatever 8 to the power of 5 is. But that's your numbers, and that's how you answer a question like that. And that's it. And then you've basically found how you've done it. So the key thing here was you have to ask yourself, okay, it says what's the probability distribution of how many times you spin X? So first you ask ourselves, what are the possible outcomes? Well, we can only spin 1, 2, 3, 4, or 5 times. And then we ask ourselves, how can we get only 1 spin? Well, that's if you have 1 green. How can you have 2 spins? That's if you have 1 red and 1 green. How could you have 4 spins? That's if you have 3 reds and 1 green. And that's pretty much what you have to do. And that's how you answer this kind of question. So I hope that was helpful. So next we're going to take a look at the binomial distribution. So this is one of the new distributions that you're going to learn and you're going to be using quite a lot. So the binomial distribution is used only when you have an experiment which only has 2 outcomes. So if you do something which only 2 possible things can happen, then you can use a binomial distribution. And normally we call one of the things that happens a success and the other one happening is like a failure. So one of your outcomes is success, the other outcome is a failure. But the key thing to remember is you can only do it when there's 2 outcomes. So our random variable x in this case will represent the successful number of trials. So whatever x is talking about is always going to be saying how many successes we had. So if I wanted to find out if I flipped a coin, the chance of getting heads and tails, then a success might be heads and a failure might be tails. So x would tell me how many heads I have since that's a success. And the trials have to be independent of each other. In a binomial distribution, if the trials will affect each other, then that's not a fair test. and then you can't use the binomial distributions. So every time you roll a dice, well, let's say you can't use the dice because there's 6 sides, and we said it's only 2 outcomes. So let's say you flipped a coin, there's only 2 outcomes, but every time you flip the coin, it shouldn't affect another coin flip, for example. And that's just these are just rules that they might ask you to remember in the exam. So just remember that these are your rules. So let's take a look at the binomial distribution itself. And like everything in stats, at the beginning, this might seem off-putting, but we'll go through it and how to use it. And hopefully that will make it seem much better than what this actually seems to look like. So the first thing to understand is when you have the binomial distribution, we say that x is distributed binomially. So doing this means that a random variable x is distributed binomially. This tells us what the distribution is. So you can see here it's a binomial distribution. And we say for the binomial distribution, we need to know 2 things. How many trials we did, so how many times we ran the experiment. So this would be how many times did I flip the coin? And what is the probability of a success? So let's say my coin is biased. The chance of a heads is like 0.6. So then, and I flipped it 100 times, then I would say x is binomially distributed for 100 flips with the probability of success of a heads of 0.6. So that's what I'd write for my binomial distribution. And then after that, you probably want to find the probability. So if I did it 100 times, what's the probability that my coin would give me a total number of, like, let's say 72 heads in 100 trials? To do that, what we need to do is use this equation here. Now, this one will look really off-putting, but let's actually talk about what this equation is. So P is a probability of success. 1 minus P is just a probability of failure. R over here is the number that we're looking for. So R would be how many heads we had. So let's say we wanted to find the probability that we rolled 72 heads. So following this formula, this part here is just n choose r, which you've probably studied before. This is a choose function, which you have in calculator. So n in our cases, we had 100 trials, and we want to know how many heads was there, how many times we got 72 heads, basically. So what's probably 72 heads? So we write 72 here. The probability of a success was 0.6. Then you raise that to the power of how many heads you wanted. And then the next part looks complicated, but it's simply going to be 1 minus p is 0.4. So this is the probability of a failure. And n minus r is just 100 minus 72, which is 28. So the way I like to think of this part over here, which is one way, is basically, I like to think of this as being the probability of a success times the, how many successes I have. And this is the probability of a failure, and just times how many of those happen. So if I had 72 successes, I had to have 22 failures, and the chance of success is 0.6, and so this should be 0.4. So that's all you have to do these kinds of questions. So I'll show you some examples of how to answer this. So let's say x is binomially distributed 20 and 1/5. So in order to do that, for probability of x being 3, all we need to do is follow the formula. So what I'll do is I'll copy this formula down, just so we always have it there. And let's actually try and use it. So that's our formula. So the probability that x is equal to 3 should be equal to, well, I've had 20 trials, that's my n. 3 of them are successes. The probability of success here is 1/5. So it's 1/5, like we said. And therefore, what is the probability of failure? If you want to write it in this way, you can do this. Before the powers, let's say probability of success is 1/5. Probability of failure is 4/5. And how many successes do I have? 3. And how many failures would I therefore have? Well, in 20 trials, if only 3 are successes, then I can only have 17 failures. So the answer would quite simply just be this. That's it. And whatever you get when you put that in a calculator would be the answer. Just in case you're stuck, this is known as the choose function, the NCR function on your calculator, which you should have. So the 20 is the n, the r is the 3. So you can just write that in, even in case you were stuck with that. Then we've also got the probability x is 10. This is the same thing. So again, we have 20 trials still, but now 10 of them are successes. So the probability of success and failure remains the same, but the only thing that changes, 10 of them are successes, therefore 10 of them are failures, and it's as easy as that. That's what you need to do. The next one is also just as easy, but you just need to break it down a bit. So the probability that x is less than or equal to 2 is the probability that x is either 0 plus the probability that x is 1 plus the probability that x is equal to 2. That's it. And if you just put all of those into your calculator, you will get your answer. Obviously, you have to write the binomial version of each. So the probability of 20, choose 0. The probability of success is 1/5, 1/4. So 0 for here, 20 for here. What you actually notice is this whole thing here. 20 choose 0 is just 1. 1/5 to the power 0 is just 1. So this ends up just becoming 4/5 to the power 20, actually. Then this one here would be 20 to the 1. Again, 1/5 and 4/5. 1 success, 19 failures, whatever that is. You add that up. And then 20 choose 2. 1/5, 4/5, 2 and 18. And that's it. That's how you answer that kind of question there. So let's take a look at another question now. So here we've got the probability that someone in the class likes the color blue is 0.25. And instead of asking everyone in the class, we take a sample of 15 students. So what's a good model for the number of people who like blue, which is x? So this one's actually quite easy. This is quite simply the binomial distribution for x, which is the number of people who like blue, is binomially distributed between 15 students, and the chance that each like blue is 0.25. And that's quite simply all you need to do for this question. And that would be the answer to the first part. And the reason you say this is correct is because, let's say the probability that they like blue, and actually to make the question right, I should say they either like blue or don't like blue, is that. Because if you can like more than blue, if you like the many other different colors, then there's only 2 outcomes, so it's not binomial. But the probability that I say you either like blue or you don't like blue, so it has to be one of the two, then this question will make sense. There's only 2 outcomes, either you're blue or you don't like blue. So they'll ask you, like, why can I, why is this a good model? Well, the first thing we said is there's only 2 outcomes, so either you can be blue or you don't like blue. And there's a fixed number of trials. There's 15 trials, so that's already fixed. And we have a fixed probability of success of all the trials. So that's a probability of each of them liking blue or not. So all of that is basically fixed. So assuming all the index samples are independent, so every time you ask a student, it doesn't affect it because that's a last condition, then we can say that you're allowed to do it. So that's why I said, remember those rules we said before, because when they ask you why is this a good model, then you just state those rules and you fit in all the things for the model. But basically you can get this as a result. Now we need to find the probability that exactly 6 people like blue. This one's quite simple. The probability that x is equal to 6 would just be equal to, again, we have 15 people, 6 are successes, so 6 like blue, so then 0.25 is a success, therefore 0.75 is not a success. 6 people like blue, therefore the other 9 cannot like it. 15 minus 6 would give us 9 there, and that's literally all you have to do to find exactly 6. So when it's exactly a certain number of people, it's quite easy. So the next question is asking fewer than 3 people like blue. So what is that saying? That's saying the probability that x is less than 3. Now the probability that x is less than 3 is equal to the probability that x is 0 plus the probability that x is 1 plus the probability that x is 2. But not the probability that x is 3 because it has to be less than 3. So again, if you do the same thing as we did before, this would be 15, 0, probability of success, 0, probability of failure, 15, that to the 15. Again, this just becomes 0.75 to the 15 plus 15 to the 0, 0.25 to the 1, 0.75 to the 14 plus, oops, sorry, my bad. This should have been 15 to the 1. You can just, it's quite common to make silly mistakes in these, so be really careful with stuff like this because it seems like it's quite quick and sometimes that will be a mistake. So 15 to 0.25, this should be a 2, 0.75, this should be 13. You just add that up and whatever you get, and that's pretty much it. That's how you answer questions about the binomial when it's this kind of thing. Now, there's one thing you might have noticed. This is great fun and all if you have to do like probability x is less than 3 is equal to this plus this plus this. But even writing that took quite a lot of time to do all of that. If I told you what's the probability that x is less than or equal to like 10, then I'm not going to expect you to have to write out the probability that x is equal to 0 plus the probability x is equal to 1 and so on. That takes way too long. There's going to be 9, 10 different things you have to write here. That's way too many. So that's not really a practical solution. So this works for small numbers, but what if I have a huge number? We'll take a look at how to deal with that in the next part. So to understand this last part, we just need to understand what are cumulative probabilities. And cumulative probabilities for a random variable x would tell us the sum of all the probabilities up to and including the value of x, where x is equal to or is less than or equal to 10. So if you're doing an example, if you want to find out the probability that x is less than or equal to 2, then that's all these 3 probabilities added up. And we'd actually have a table which would directly tell us what this answer actually is. So you don't actually need to do this. You can actually put it into a calculator. There is a cumulative button on your calculator, which basically helps you find cumulative probabilities. So you should find out how to use that, because that's usually the way you do it. Or if you go to the back of your book, you'll probably find some sort of binomial table, and that table will show you how to read the binomial tables which you've got. So basically all you need to do is, once you've gone to the back, you need to find the table which corresponds to your value of n and the value of p that you want to want. And literally it will be something like, if this is a table for n equals 10, you might have like 0, 1, 2, 3 all the way down, and then you have the probabilities like 0.1, 0.2, 0.3. And then let's say your binomial thing was distributed as 10, 0.2, and you want the probability that x is less than or equal to 2 as your question, then what you would do for that is you'd find the table for n is equal to 10. You'd find where you have 0.2, and you literally read 0.2 is this column here, so that's the one I want, and I want less than or equal to 2, which would be across here. So this is the value which I would want in my table. So you can just get used to reading that from the table and doing it. So, but to be honest, you have your calculators in these exams, so you could just put it into a calculator and read it off there, which is easier. So the next ones, I'll assume you have a calculator. And what will be worth trying is, if you do have a calculator, I would just try these questions. I've written some for you to try out and see what you get for your answers. And I'll post the answers down later in the description, just so you can double check your answers with it. But these are just for you to check. So the only thing, there's nothing really new here, which is why we don't need to go too much. But basically, to do this first question, for example, you would put n is equal to 10 into your thing. Again, you'd find where it's 0.3 for your probability. This would be 0, 1, 2, 3, 4, 5, 6. It would be easier if I drew till 6, since it goes till 6. But for this question, you use this column, this row, this number would give you the probability that x is less than or equal to 6. So you'll just get a straight number for that. Now, these other questions, you just want to be a bit careful, because probability, this table that you have, right, only gives you the probability that probability of x is less than or equal to x. So if you were to do this question here, this doesn't, if you just searched up 5 in the table and matched it up, that wouldn't work, because you notice this is missing. So you have to always convert these questions into the form of something like that. So if you convert this question to the form, what you actually need to search in your tables is a probability that x is less than or equal to 4, because these two are the same. Since the probability of every x being less than 5 is the probability of x being less than or equal to 4. And that's just something you'll need to get used to in cumulative probabilities and trying to understand that. And the final question we've got is, what's the probability that x is more than or equal to 15? I realized that question doesn't actually work there, so let's change that. Let's just make that 3. The probability x is more than or equal to 3. Well, how do we do a question like that? So you can see that here we've got the inequality sign flipped around. Well, if you're doing a question like this, quite simply, all you need to do is you can rewrite this as the probability, or as 1 minus the probability that x is going to be equal to less than or equal to 2. And why can I do that? Well, the probability that x is more than or equal to 3 is equal to the probability that x is either equal to 3 plus the probability that x is equal to 4 plus the probability that x is equal to 5, and so on, all the way to 10. So everything which is not included, which I'll put in red, is probability that x is equal to 0 is not included, x is equal to 1 is not included, and x is equal to 2 is not included. So these things, if you put together, that's the same as saying the probability is x is less than or equal to 2. So that's how you rewrite these. So whenever you get a question and you're looking at the tables, if it's not in this form, if you have something which is less than, this is how you would convert it. If you have something which is more than or equal to, then this is how you convert it. And just get used to converting things where it's like more than, less than. So different types you have to be careful are, which is less than equal to, which is fine because that's what your table tells you, or more than or equal to. Just need to be careful with that one as well. So that's pretty easy to understand. And a good thing I would say is, if just for a bit of help, if I got rid of this equal sign, then this will actually change my answer, because this says the probability of everything which is more than 3, which means that I can't include 3 in itself. So where I had 3 here, I can't include 3 anymore, because 3 is not more than 3. And actually that goes in the bad section here. So actually, if I was doing that question where it's more than without the equal sign, this would change and be x is less than or equal to 3. So just kind of play around with that, do some questions on it and get used to it. But this should hopefully help you understand that part. over there. So we can finally take a look at a last question, and this is probably the hardest kind of question which you can expect. So when you do this kind of question, we said we have a dice and there's a chance that it will land on a 6, and the chance it lands on 6 is 0.2, and we roll it 15 times. So what's the probability that we have no more than 3 6s and at least 7 6s? So these are like the word kind of problems that people don't tend to like. So this kind of question is, we know X is binomially distributed with 15 rolls and chance of success is 0.2. So the probability that X is no more than 3 times, now that's the key part, it says no more than 3 times. That means that I have to be less than or equal to 3, because I can't do that more than at least 3 times. So you just have to find that probability. And like we said, you know how to find that in a binomial table or using your calculator. And that's it. You just put in 15, 0.2 in your calculator for the cumulative binomial and you get that. For those of you who don't know how to do it, I'll make a video on just how to use your calculator to do that. But I think most of the people watching this video probably already know that. So then finally, part B. At least 7 6s means that the probability of X has to be at least 7, which means it has to be more than or equal to 7. That's what at least means. So again, to do this, we have to do 1 minus the probability that X is going to be equal to less than or equal to 6. So that's using what we said before. You can find this in your calculator or the tables again, and again, you'll get your answer straight away. So that's what you need to do for this kind of question. Now, the last part is the hardest part you can expect in the whole chapter in a question like this. So if we use the dice to win a raffle, then let's say I said, okay, now I know my dice has a 0.26% chance of getting a 6. So I say that, okay, I want to make a competition that people roll the dice to win a raffle, and we want the chance of them winning to be less than 0.05%. And because everyone can roll 15 times, how many 6s should I set them to roll so that the chance of winning a prize is less than 0.05? Because if I said, like, you know, in 15 rolls, you just have to roll 1 6, then you will win a prize, and the chances that you'll win the prize is quite high. So I don't want to do that. I want to limit it so I can make some money in the raffle. So in order to do a question like that, what we have to say is we say, let's say y equal to the smallest number of 6s needed to win a prize. So we say that y is the smallest number of 6s you need to win a prize. So, you know, if you needed 10, there's no point. We'll say what's the smallest number you need to win a prize. So what we're trying to say is we want the probability that X is going to be more than or equal to this random thing that we called here as Y to be less than 0.05. So we want the chances of, so let's just what was X again. X is the number of 6s and Y is the smallest number of 6s we need to win a prize. So we want our random variable X to be more than this value of Y that we have. So what we need to do quite simply is figure out what value does this Y have to be so that this is 0.05. Now again, from our tables, we can't do this so easily. And why is that? Well, that's because we have a more than sign. So remember, you have to do 1 minus the probability that X is less than or equal to Y is minus 1 should be less than 0.95. So then basically just look in your tables, find a value of the first value, which when you do 1 minus, that will give you something which is less than this value here. And whatever you get for that will be the smallest number you need to roll. So I'll leave this for you as an exercise to do. And then once I put up the videos on how to actually answer these kind of questions, I'll put like a fully worked solution. But it'll be a good idea to actually challenge yourself on this kind of question to see how you do it and to stretch your understanding on how to do this. So yeah, I hope the video was helpful overall. And there's one more video to go in the series, which will be the 3rd chapter on box plots and all of that stuff on representing data. So that should be quite a simple topic. So I've left that to the end. And as ever, if this was helpful to you, then please let me know in the comments below and I can continue making these videos for this subject and all the other ones too. So I'll see you in our next video. Welcome to another video in our statistics series. So today we'll be looking at hypothesis testing, and hypothesis testing is probably one of the most challenging topics for most students that I've seen in the last few years. Normally when I ask someone, in statistics, what's the most difficult thing that you've seen, often I'll find the answer is they'll say hypothesis testing is a chapter that I found quite difficult. And from my own experience, when I finished my high school, hypothesis testing is one of those concepts which, if it's not explained to you very well by your teacher, it can be quite a difficult thing to grasp. But once you kind of understand the basics, it's not as bad as it seems. It's actually quite a simple kind of process to do. So what I want to do today is, whether you've got teachers who've made it quite difficult for you to learn, or you just want to understand hypothesis testing better, then I'll try and take you through all of the different types of hypothesis questions you can get, and also I'll show you the standard way to write your answers. So today what we'll be looking at is, we'll try to understand exactly why do we need hypothesis testing. I think it's important to understand why you're learning this topic in the first place, so you can kind of appreciate and understand why you need to use it and how you can use it. Then apart from that, we'll be looking at how are we using samples and how do we use this to learn about a population. So in our previous videos, you've seen a lot about how we can conduct samples, how we can find samples, and now we're going to be putting these samples to use to learn about the population. Apart from that, when it comes to hypothesis testing, you need to understand what are critical values. So we'll be taking out critical values, which is something that, if you've seen this topic before, I know a lot of people have some difficulty looking at critical values. So apart from this, we'll be taking a look at two different types of tests. There will be one-tailed tests and two-tailed tests, and we'll take a look at a few exam questions for each. So once we finish this chapter, what I'd like you to understand is basically, what are hypothesis tests? Why do we need them? What are critical values? What are one-tailed tests? What are two-tailed tests? And most importantly, once you've understood the theory and how to do each of these, I want to show you how you can write out a standard exam answer for each type of question, because hypothesis testing literally follows the same kind of steps. Doesn't matter if it's one-tailed or two-tailed, you do the same steps and the answer is always in the same format. And for the exam, this is quite important. So I just like to kind of emphasize that quite a lot. So yeah, now that we've kind of gone through the introduction, let's just take a look at what exactly is hypothesis testing. So first, let's try to actually understand what is a hypothesis in the first place. So normally a hypothesis is something that you'll say where you're trying to learn something about the population. So a hypothesis might be something like, I think that in my school the most popular TV show is X, Y, or Z. So there might be a TV show and you might think, okay, this is the most popular one in my school. Or it might be something like, I think that this in this batch of eggs that I've got from the supermarket, I think that they're not very good quality or something like that. Basically, it's just something I'm trying to say about a population. So it might be me saying something like, I think if I flip this coin, it's not a fair coin, something like that. So a hypothesis is basically you saying something about the population parameter. So when we have a hypothesis, it's basically us trying to say something about a population parameter, like this. So that's the first thing to understand. I want to know something about my population, and a hypothesis is just a statement that I make about this. Is something that I say, I think that this, or I think that that. So I think that the most popular TV show in my school is this. So that is a statement I have made about the population, which is my school. So if I made a hypothesis, so I've made a statement now, I can actually test this hypothesis first. And then how do I do this? Well, the way that we always do it is we have to use some kind of experiment to figure this out. Now, as we've seen before, we've said that we could just ask every single person in the school what their favorite TV show is, and based on that we can come to a conclusion. Now, the whole point of statistics, like we discussed before, is often impractical to take this kind of solution. So often we need to take a sample from a population and understand something from this. So the idea about the hypothesis testing is that now that we've made a hypothesis, which is a statement about the population, we can now test this hypothesis by using an experiment of some kind. And to do this, we often need to take a sample from our population. So if I've got my school full of all the children there, maybe I'll say I can ask 5 people from every class across every year group. And there's lots of different ways that you can be fair in your sample, or different samples that might make more sense in different situations. So we've covered that before in the video about how do we take samples and what are the advantages and the disadvantages of each kind of sample. So basically, let's say we have now done the experiment, then what's going to end up happening is that we're going to get some sort of statistic from this kind of experiment that we've done. And this statistic is known as your test statistic. So let's just kind of summarize everything that we've said here. So let's say I'm sticking with the school example. So I've got my population here. My population are all the people in my school. Now, I can't ask every single person within this population. So what am I going to do? Well, instead I say, well, since I can't ask everyone, doesn't matter what sampling method we use, but let's just simplify it for now. And so we use some sampling method. And using the sampling method, we've conducted an experiment. So we did an experiment. And this experiment allowed us to get a sample of some kind. So now we have a sample. Now, by conducting the sample, what we want to find is some sort of test statistic. So in our population, there is some population parameter that we're trying to find. So there's a population parameter, which is something like, this is the most popular TV show. 60% of people in my school like this TV show. And what we're going to find from our sample is a sample parameter. So that's over here, a sample parameter. And what this would be used for is we're going to compare this with the population parameter, and then we're going to infer something. So that's kind of what hypothesis testing is about. So we have a hypothesis, which is just a statement about our population. So we've got a population here. Then obviously we can't ask everyone, so we take a sample. When we take a sample, we have to do it by some sort of experiment, and the result of the experiment will give us a sample parameter, which we're going to compare to the population parameter. And essentially, that's kind of what hypothesis testing is about. So when it comes to writing down stuff about hypothesis testing, the first technical stuff that we need to know is there's something known as the null hypothesis. So I'm sure you've heard of this a lot when you've done this topic. So what exactly is the null hypothesis? Well, we normally denote this as H0. That's what it's known as. And this is a hypothesis that we think is correct. So we think this one is correct, or we assume it to be correct. So this is a hypothesis that you think is correct at the beginning. So I might say something like, I think the most popular TV show in my school is, let's say, SpongeBob SquarePants or something like that. I don't know, let's say it's primary school. And then I'll say that I think that 60% of students in my primary school like this TV show. So my null hypothesis is what I assume is correct. And then we also have something known as the alternative hypothesis. So the alternative hypothesis. And this one is denoted H1. And this is the one that is going to be, this will tell you that basically something about our parameter if the assumption that we made in that null hypothesis is wrong. So basically what it means is that I thought my null hypothesis was correct, but if it turns out it's wrong, the alternative hypothesis will tell me that this is actually the case instead. So this is like if your assumption or if your null hypothesis is wrong, then this is the case. So what this means is I carry out my hypothesis test. So I've done that now. And I think that this one is correct. So I think that, okay, the null hypothesis is correct. Let's say I did all my experiments, found my sample parameter, found my population parameter, and then actually it turns out my null hypothesis is wrong. Well, if my null hypothesis is wrong, I need something else that I need to know is correct. Because I can say, okay, fine, this isn't the most popular TV show, or this isn't like 60% of people at my primary school don't like this. Then if that's not the statement which is true, then what is the statement which is true? Well, that's given by the alternate hypothesis. So basically, a hypothesis test goes something like this. My null hypothesis is either going to be correct or it's not going to be correct. So if it's correct, great. This is the statement, this one here, that you know is to be right. If that's not the case, then you know this is a statement, which is the one which is a correct statement. And in hypothesis testing, you're basically trying to find out, is this the one that's correct, or is it this one which is correct? And we'll talk a little bit more about how you can find these in the coming sections. So before we do that, let's just kind of give you an example of how we can conduct a hypothesis, at the beginning of a hypothesis test, where basically how do we set the null hypothesis and how do we set the alternate hypothesis. So let's come up with some sort of situation here. Let's say I have a 6-sided dice. There are 6-sided dice, or I should say die technically. So I have a 6-sided die, and what I think about this die over here is that maybe it's not actually a fair dice. Maybe I keep rolling it and I find out that I think that I'm always rolling a 6 for some reason, so I think it's not a fair dice. And I say, okay, I want to basically test this theory for myself, so I want to do my experiment. And to do this, I'm going to toss my dice. Let's say I roll the dice about 100 times, and I'm going to record the different numbers I get. So how many ones, twos, and so on do I roll? And basically, I want to see what the result is. So this actually lets you come up with a hypothesis. So I've got a 6-sided die. I think that the side 6 is biased. So let's say I think it comes up more than it should. It could be possible that it comes up less, but let's say I think it comes up more than it should. So, and I rolled it 100 times as well. I had 100 rolls. So from this situation, what you can say is, what is my test statistic? This is the first thing you need to realize. What is my test statistic? So my test statistic in this case, we're going to denote it as x. And what is x going to be? X is going to be the number of 6s rolled in 100 rolls. That's what x will tell me. Literally all x will tell me is how many 6s I rolled, basically. That's what it's going to tell me. And when I've done 100 of them. That's all the test statistic is. Now let's say, what should my null hypothesis be? Well, my null hypothesis is a thing that I assume is going to be true. So I'll say, let's assume that the dice is a fair dice. So if it's a fair dice, then my null hypothesis, which is H0, what it should be is it should be that the probability of my 6 coming up should be equal to 1/6. That's what should be the case with a normal dice. If I roll it, I should get a 6 of the time. Now, if I think that the dice I've got, that this actually biased, then in that case, what I'm trying to say is my alternate hypothesis. What I'm trying to say is actually, you know what, the probability isn't 1/6. I think it's not a fair dice. So therefore, the probability of rolling a 6 is actually going to be more than a 6. And so therefore, I've written my H1 as being P, being more than 1/6. So this is basically what's going to be your alternate hypothesis. Now, that's kind of a basic beginning to it. Don't worry too much about the technical details of this. Just kind of try to understand why is my null hypothesis as 1/6 and why is my alternate hypothesis as more than 1/6, because when we get to solve an actual question with all the test statistics and the numbers and stuff like that, it'll be a lot more obvious what these are. So basically what we need to understand is that basically you can see here that we said that our alternate hypothesis was probability is more than 6, and we said it could have been less than 6, so the question was different. There are cases where actually sometimes we're going to find that the alternate hypothesis will be the case where it's not equal to. So we're not saying it's more than a 6 or less than a 6, we're just saying it's not equal to a 6. So for this, sorry, what we need to do is basically kind of see how do we use this. So basically what we're trying to say is if your alternate hypothesis is in the case of H1 is more than something, so sorry, H1 is your probability P is more than something, or your H1 is the probability P is less than something. In these two cases, these two are considered one-tailed tests because they're more than or less than. In the case that your alternate hypothesis is P does not equal to some value, then in this case, it's a two-tailed test. And basically, we'll be covering what each of these are. But just so you know, these are the 3 different situations that you can get. So if your alternate hypothesis looks like this with a more than or less than sign, then it's one-tailed, and if it's not equal to, then it's a two-tailed test. And we'll help you figure out, how can you figure out, is it a one-tailed or is it two-tailed? We'll kind of cover how you can figure that out in the coming examples, but this is just so you kind of have a heads up. So one other thing you need to do is you need to know when you're carrying out the hypothesis test, you always assume that the null hypothesis which you have is going to be true. And basically then we're going to do an experiment, find the test statistic, and basically after all of that, we need to decide, how rigorous are we with our test. So basically we say something like, okay, I assume my null hypothesis is true. I start with that. I think that H0 is true. And then I'm going to do my experiment, and that's going to give me a test statistic. As so. And basically what I need to do is consider how likely is it that this test statistic will occur. And is this likelihood, you have to compare it to like a threshold, and this threshold is known as significance level. So the significance level. And this is basically saying how stringent am I, how likely am I to reject the null hypothesis. So, how strict am I being? Is that the 1% level? Is that the 5% level? Is that the 10% level? The level will always be given to you in the actual question itself. Normally you can expect 10%, 5%, or 1%. And often the bigger the significance level, the more stringent you're trying to be. So, if I have a 10% significance level, then I'm being very, very, I might be more likely to reject my null hypothesis, where if it's 1, then I'm less likely to reject it, but more on that later. Basically, for now, just think of the significance level as how strict are you being when you're conducting a hypothesis test. Okay, so let's actually try to understand what are critical values and what are critical regions. So normally, just so you know, as a starting point, the critical region it's basically the part of a probability distribution. It's the part of it where if your test statistic is within that, then you reject the null hypothesis. And just to help make more sense of that, the critical region is basically saying that, let's say we have some distribution. Since we know in this chapter we're working purely with the binomial distribution, the binomial distribution often looks something like this. And what often happens is that your test statistic can fall in different parts of this. So my test statistic could be here, it could be over here, it could be here, it could be anywhere. It depends on what you find it to be. And basically what we want to say is, if there's a region of this graph within which that test statistic falls, then anything in that region means we reject the null hypothesis. So let's say we found the region to be somewhere here. So let's say the critical region, we found that to be over here. Then let's say I found my test statistic. And my test statistic fell over here. Now, if my test statistic falls here, then I will accept H0. But if my test statistic falls anywhere within this red area, then I'm going to basically reject my null hypothesis. So these are the two different outcomes you can have. And the critical region is basically this whole shaded red area. So all of this part here, this is critical region, because that is a part where if my test statistic falls within that, then I reject the null hypothesis. And anything that falls within this green area, this is all fine. So the critical region is basically that. And the critical value is actually the first value of my critical region. So in this case, my critical value would be this one here. That's critical value. And it's useful to know because you know that if you fall on, let's say you fell on the right side of that critical value, you reject H0. Whereas if you fell on this side of the critical value, then you were to accept H0. So that's kind of the idea of what the critical region is. So yeah, basically that's the gist of the critical region. So I think it might be a good idea to kind of get a better understanding of it. And don't worry if it seems quite difficult at the moment, because when it actually comes to the questions themselves, we're going to be using a lot of these concepts and it will make a lot more sense when we actually do an example. But for now, I just want you to follow these kind of things separately. So I'll give an easier example to understand the critical region, how it kind of comes about. So let's say my test statistic was modeled binomially with n being 10 and p being some value. My significance level is 5%. And let's say my H0 is p equals 0.4. And my alternate hypothesis H1 is p is less than 0.4. But I think for this example, actually what I wanted this to be was I wanted p to be more than 0.4. Okay, so let's say that this is our situation. So what this means is that we assume, for the sake of the question, this is what you always do, that x is binomially distributed 10, and since the probability which was p here, we're going to assume that this probability is 0.4 from there. So we'll say p is 0.4. That's what we've got. Now, if you were to graph this binomial distribution over here, you would find it gave you something like this graph over here. Now, what we want to do is, we know that we're at the 5% level, and what we want to basically figure out is the same way we broke this diagram down here into the accept region and the reject region, we kind of also want to break down this diagram here into some kind of region where we accept it and some region where we reject it. So we need to figure that out. So how can we do that? So let's take a look at the probability that x is equal to 10. Now, if on this graph I know the probability x is 10, if I find that on the binomial tables, or you can use a calculator to figure it out, whatever you prefer, then you're going to find that this is equal to 0.0001, which is, that's fine. Let's carry on. Let's say what's probability x equals to 9. Probability x equals to 9, if you do the same thing in calculator, is 0.0016. And let's say the probability x is equal to 8. What is that probability going to be equal to? Well, that's 0.0106. So what do we find if we add up all these probabilities together? Well, if you add them all up, what this is going to give you, the probability that x is more than or equal to 8. So what happens if you add up all these numbers together as well? So if you add them all up, you get 0.0123. And 0.0123 is actually the same as 1.23%. Now, this value is less than our significance level of 5%. So because our 0.0123 or 1.23% is less than the significance level, then what we say for that is that any of these values would be rejected because all of them are less than 5%. So how does that look like on our graph? So over here, we found that its value for 10 was 0.0001. Its value for 9 was 0.0016. Its value for 8 was 0.0106. So when we put all of these together, what we found was it was less than 5%. And if it's less than 5%, then we're going to reject it. And why is it that we reject it on this side? Well, the key thing is that here we found that this is a more than sign. And because of the more than sign, we know the reject region will be on the right-hand side of the graph. If this was a less than sign, then our reject region would have been on the left-hand side of the graph. But don't worry about that too much now because we're going to cover both left and right-hand sides later. For now, let's just concentrate on the fact that we're doing the more than sign, so that's on the right-hand side. So anyway, what have we done so far? We found the probability x is 10, x is 9, x is 8, and when we put that together, we got the probability x is more than or equal to 8, which gave us 1.23%. And 1.23% is less than 5%. And since this is the case, we so far know that any of these values, if you get it, you'd reject it. So what happens if we then move on to the probability that x is actually equal to 7? Well, if you try to figure out the probability that x is equal to 7, you get 0.0425. And then if I add up all of these values, so I add up the one for this, 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 and this, what I'm going to end up getting is the probability of x being more than or equal to 7. And what this is equal to is going to be equal to, let's just add all of this up, well, actually, I don't need to worry about that, but let's do it anyway. 0.425 plus, I got 0.0123. So what does that equal to? 0.0548. Okay, now I've got that. And what does that equal to? That's 5.48%. Now, 5.48% is actually more than my significance level. And that means that this value here, which I just added on, 0.0425, this value took me over my threshold of 5%. Now, since it took me over my threshold of 5%, that means that if I get any value of x which is equal to 7, then I'm going to accept it. Same for x is 6, x is 5, x is 4, and so on. The only ones that I actually found that you're going to reject are the values 8, 9, and 10. Any of these values would give me a number which, when you added them all up, would be less than 5%. So any of these values would not work, so they would all be rejected. Any of these values here, as you can see, since when I added 7 is already more than 5%, then it doesn't matter which of these other values I take, all of these values will add up to something which is more than 5%. Now, since this adds up to more than 5%, then I can clearly say that this area here is the acceptance region, and this area here is the critical region over here. And what is my critical value? The critical value will be 8, since that's the first value in my critical region. So that's kind of the idea behind how that part works. So one other thing I'd like to help you out with is kind of try to understand, which side you reject, which side you accept, because this can get a little bit confusing for some people at some times if you've seen it. So I just want to kind of clarify that part for you. So normally what you're going to be given is you're always given a binomial distribution of some kind, a significance level of some kind, and the null hypothesis and the alternate hypothesis. Now, using these parts of the question, the only thing you really need to worry about at this point is that is it a less than sign, is it a more than sign, or is it a not equals to sign? And like we said before, this kind of tells you about the fact whether it's a one-tailed or a two-tailed test. So now let's say it's a less than sign. When it's a less than sign, you know that your reject region is always going to be here on the left-hand side of the graph. So the same way we were trying to figure out before that, did stuff fall into the right-hand side? And we were trying to figure out those numbers. When you're doing questions for less than, you're actually going to be trying to figure out at which point does, let's say, this part exceed 5% here. And here you're trying to figure out which part does this exceed 5%. So if it's a less than sign, you always know your reject region is over here and your accept region is over here. If it's a more than sign that you've got to work with, then always your reject region is going to be on this side over here, and then your accept region is over here. So it's pretty simple to know. If it's less than, that's a reject region. More than, that's a reject region. And if you're doing a two-tailed test, where you have a not equals to sign, then what ends up happening is only one case. You have either this side or this side, you have two reject regions, and anything which falls in the middle is your accept region. And this will make a lot more sense when we do questions, but keeping this kind of thing in mind, it'll be quite useful to draw diagrams. And when we actually do a proper one-tailed test and a two-tailed test, I'll try and show you how you can kind of use these diagrams to help you, because they're not always taught in schools, or they're not really explained how you can use them. So I just wanted to kind of introduce that here so that when we do some questions, you're a little bit familiar with it to try. And like I said before, don't worry if all of this seems a little bit overwhelming or a bit difficult, because when we use all of this together in one question and give you a model kind of solution, it should be a lot more clear on how to use it. So for now, what we're going to do is we are going to go back. So what I also wanted to show you is how can you actually use the binomial tables to actually figure out what the critical region actually was, because you don't always want to keep adding up all the numbers like p is equal to, or x is equal to 10, x is equal to 9, x is equal to 8. That can take quite a while, and that's actually not how you do it when you're doing this in real life. That was just the theory. So what is a slightly easier method that we could use? So let's do the same question we did before. We had the fact that we had a binomial distribution of 10 and 0.4, and we want to figure out what is the critical region if you're given that kind of binomial kind of thing. So first thing you need to do is, since we can see n is 10, we need to look at the binomial tables where we have n is 10. And since we're dealing with the probability of 0.4, the only area or only column we care about would be this one over here. So that's what we've got now. So we know that our significance level that we were working with before, the sig level, that was 5%. So we know that. And we also knew that the alternate hypothesis we're working with, we had a more than sign in that. So since we had the more than sign, we know that we'll be working in this area of the binomial tables. If we had a less than sign, we'd actually be working in this area of it to see when it exceeded 5%. So at which point here does it exceed 5%? So here we can see there's no real cause for any concern, it's just a 1. Here this still hasn't exceeded 5% because this is 0.998. Here we haven't exceeded 5% either because that's 0.988. But this number here is where we first, oops, that kind of disappears. But this number here, which is 0.945, is where we first exceed that 5% value. So now that we know this, how can we actually use that to figure out what the critical region is? So the way you do this normally is, the first thing you want to do is keep going through the numbers until you find the first one, which has exceeded 5%. So we clarified that the first 3 down here haven't exceeded 5%, and this one over here has. So I would like to kind of show you like the boundary at which point it flips. So I'm going to take I'm going to take this one here, which is 0.945, and I'm also going to show you how to calculate something for 0.988. So this value of 0.988, let's actually figure out, and we're looking at this one here, where exactly does this number, what value of a does this fall for? That's this one here, and this one over here is this one here. So I kind of want to talk about these two numbers over here. So what does the binomial table actually tell us? Well, the thing is, the number in the binomial tables are actually telling you the probability that x is less than or equal to a value of a, and a is basically given over here. So since I said that 7 here, then you could put that 7 here and get the probability that x is less than 7 is equal to 0.988. So that's kind of how this table is working. So this is what the table is telling you, the probability that x is less than or equal to a. So I'll put that up here. So how can we use that? So let's take a look first at this second highlighted line. So this tells us the probability that x is less than or equal to 7, and that means the probability of that is equal to 0.988. So we want to figure out a probability, because it's a more than sign, where the probability of x being more than a value of a is basically going to be less than 0.05. So that's where anything which is the case over there will tell us a critical region. That is basically what the critical region is. So to figure out this, you'll notice the difference is that here we have a more than sign, here we have a less than sign. So we need to kind of use the probability rules to flip that. So this is the same as doing 1 minus the probability of x minus 7. What will that give us? That will give us a probability that x is more than or equal to 8. And if we do that, we get 1 minus 0.988, which is equal to 0.0132. And as you can see, this value here is less than 0.05. So this part here is within the critical region. Now, if we did that for this one, or this one, we'd find that's the case for all of them. I want to show you what happens if you did it for the second one. So the first one, so if you did it for this line here, what actually happens? The probability that x is less than or equal to 6 is equal to 0.945. So 1 minus the probability of that will give you the probability of x being more than or equal to 7, which is equal to 1 minus 0.945, which is equal to 0.54. Let's take a look at that. 5, actually 0.55, my bad. So, my mental maths just kind of went out the window there, but this one here should be 0.055. And as you can see, this is equal to a probability which is more than 0.05. So this is the case where this is the acceptance region, this is okay. Whereas this one here, it was less than 0.05. So therefore, it's not actually going to be accepted and it's in the reject region. So based on this, we can say anything which is more than 7, this is okay. So where was the first time it was not okay? Well, it was not okay over here, which was P is, or probability of x being more than or equal to 8. So that means anything which is 8, 9, or 10, 8, 9, well, we don't have 10 here, but 9, 10, those values would not be accepted, whereas everything else would be accepted. So the key in this one here, this is just more for people who want like a deeper understanding of how it works, is essentially we wanted to find where is the value where it flipped. We found the value where it flipped was this one here between these two. So we know that based on that, the probability of this one here, of P being x less than or equal to 6, is equal to this value here. So when we flipped it, because it's more than sign, we found out, okay, this value works, so this is fine. So every other value which is here, when we did it, we found that didn't work. So that one there isn't fine. And basically what this tells us is, this tells us the critical region is anything which is probability x is more than or equal to 8. Don't worry, that was quite difficult and hard to kind of understand, but if you kind of follow it, it should hopefully make a bit of sense. But the key reason we're kind of trying to explain this is we want to learn of something known as the actual significance level. And the actual significance level, by its definition, is a probability that you'll incorrectly reject the null hypothesis. So what is the chance that you incorrectly reject the null hypothesis? That's the actual significance level. And how do we actually find that? Well, finding that is pretty easy. All you need to do is go to critical value. That's critical value there. And in this case, it's just going to be whatever number we got when we used the calculation for it, which is 0.0132. So this one here is the actual significance level. So you'll be working with 1%, 5%, 10% that give you the significance level. And if you want to find the exact significance level for a distribution, which is this one here, when you find out the first value, or the last value, the first value which did not work, when you find out whatever this number gives you, that's the actual significance level. So in this case, this tells us it's 1.32%. So that's kind of how to go through something like that. And yeah, I know this can seem quite difficult, but a lot of the time, once you start doing one-tail, two-tail test, you'll kind of start getting used to how to kind of make this kind of thing work. And what I'll try and do is I'll give you examples of a less than, a more than, and a two-tail test to make more sense of this. So let's take a look at that now. Also, I'd like to point out the value I'd used here. If some of you followed, that might not seem correct. That's because the value I'd used for this in my notes was actually 0.9877. So that's the value I'd used. And that's the value that basically got me to that number there after all the roundings. So don't worry, this is just because of that kind of reason. If I actually did this normally, this shouldn't have been that. It should have been 0.012, but it's the same idea. So that's all okay. But yeah, what I want to do now is kind of put everything into context and now start looking at a few exam examples. So some questions that you'll get in your exams and how you can solve them. So how can we use everything that we've learned? Don't worry if it's difficult. What I'll do now is actually get on to the example where I'll go step by step as to how you solve it, and you can try and follow this for some of the questions you have in your book and see if it makes sense. So I'm going over to the next part over here. We can see that we have a question where we have a binomial distribution where it's 6 in P. Our null hypothesis is 0.35, and our alternate hypothesis is more than 0.35. And our significance level is 5%. Now, since we have a alternate hypothesis of more than 0.35, that means the diagram in our head should be something like this one over here that we looked at before. We know there's some value where this is a region where we're going to reject, and this is a region on this side where we accept. So let me just use some colors for that one. This side here is a reject region, and this side here is the accept region. So that's the first thing that we do. We look at the question, see a more than sign, and we immediately draw this to kind of figure out what we need to do. And we also know the significance level that we have is 5%. Okay, great. So how are we going to start this question? Well, since we know that this question is given this way, we can write x is binomially distributed like this, 6. And we take this 0.35 and we put it in here. So what does that do? That gives us 0.35. Okay, this is the first thing we write down. Now I want to know what part of the graph should I actually be looking at? Well, I'll find the part where it's n is equal to 6, and I only care about actually this section over here where I have these numbers over here in the 0.35 column. So these are the only numbers that I should be using. So how are we going to do the question from here? Well, I want to take a look at where is the first point where my numbers are more than 0.05. And what I mean by that is this one here, and this one here. You can see none of these numbers, if you do 1 minus them, you'll get numbers which are less than 0.05, which means that these are the ones which you'll reject. But this one here, when you do 1 minus 0.05, and so 1 minus this thing, you get a number which is more than 0.05. So it's easy enough for me to say that, but I wanted to kind of go extremely step by step in this, so I'll actually show you what I mean by that. So if I find the probability of x being less than or equal to 6, that is apparently equivalent to this one equal to 1. So if I do 1 minus the probability that x is less than or equal to 6, that gives me the probability that x is more than or equal to 7, which is equal to 1 minus 1, which is 0, which makes sense because for n is 6, this table shouldn't actually have gone that far. So then let's take a look at the probability that x is less than or equal to 5. That is equal to 0.998. So 1 minus the probability of x is less than or equal to 5 is the probability that x is more than or equal to 6, which is equal to 1 minus 0.998, which is equal to 0.002. And this here is less than 5%, so we know this is rejected. Then if I do probability x is less than or equal to 4, I get this is equal to 0.978, where, so if I do the same thing again, that's equal to 4, the probability that x is more than or equal to 5 is equal to 1 minus 0.978, which is equal to 0.022, which again is less than or equal to 5%. And you can kind of see the gist of what I'm trying to get at here. But basically, just by looking at all these numbers, you want to basically figure out which point where is it more than 0.55. And if you look at it, it should be fairly obvious that the number we're trying to look for is this one over here, where this is the first point at which it's more than 0.55. So based on that, how are we going to figure out what our critical region? So this is the first one where it works, and we want to figure out what the critical region is. So to do that, we need to find out the first value which didn't work. And what was that? The first value which actually didn't work was this one here. So what just happened? We tried to do 1 minus everything. We found that, okay, these values, that one is reject, that's reject, that's reject. And then we found, oh, at this point here, this is the one where we just suddenly accepted it. So what we want to do is go one back and take a look at what's the first point at which we rejected, which was this one here. And that's the only one we actually need to write any of this stuff out for. So this gives us a probability that x is less than or equal to 4, which is equal to 0.978. So this means if I do 1 minus the probability of x is less than or equal to 4, then that gives me the probability that x is more than or equal to 5. So let's do that. 1 minus the probability x is equal to 4, we found that's 0.78. So that's equal to 0.022. Now that we've seen that, this is the value at which it's less than 5%, and therefore anything which is over here, anything which is more than 5 is going to be rejected. So which values are more than or equal to 5? Well, only 5 and 6. Therefore, my critical region is going to be values where x is 5 or 6. So if x is 5 or 6, then we found that this is our critical region. So that's kind of how that works. So just to step over that again. They gave us the details in the question. We can therefore make this part here. The x is binomially distributed, 6 and 0.35, and the 0.35 we got from, well, not from this one over here, but we got that from over here, the null hypothesis. We assume that's true. Now, once we knew that's true, we took a look at this section of the graph, and we said, okay, if you do 1 minus that, it's not more than 0.05, this is fine, this is fine, this is fine, and then, oh wait, this one here, we've got a value which is more than 0.05 when we do the subtraction. So we said, okay, what is the point at which it flipped from being rejected to accepted? Well, it was between these 2 points. So once we found the points where it flipped, then we say, okay, we're only going to take the first one, which is rejected, which is this one here. Now, since we know this is the one that's rejected, we are going to take this value over here and then do this line here. How did we get the probability of x being less than 4 is this? This one came from here, and that 0.78 came from over here, 0.978. We put that there. Once we knew that, we know that if we do 1 minus that this thing is true. 1 minus the probability x is less than or equal to 4 is the probability that x is more than or equal to 5. We then put that in here to get this, and then we solve that to find that. And once you found this one here, you can clearly see that that's obviously the first one we rejected, which you can tell. And therefore, the answer to critical region is the probability as x is more than or equal to 5, because it was that gave you this value over here. So it's 5 or 6 critical region. Notice that 4 is not in the critical region, even though it looks like it was accepted here. But the way you got your critical region was by doing this calculation, which actually only gave you 5 or 6 because of this over here. So that's kind of important to understand. And then someone might ask you, what is the actual significance level of this test? Well, the significance level of this test, the actual one, is just going to be that, which is going to be 2.2%. And that's all there is to it in the one-tail test when it's the upper tail on that hand side. Now, what you can do if it was, let's say it was a less than, so let's actually get rid of all of this stuff that we've done here for a second, and let's actually change this around to being a less than sign. Then this graph no longer is the case, and what we actually end up having is we have something where, let's say, it's a less than sign, so we know that this side is now all going to be accepted, and this side is all rejected now. So what you end up doing here, so if I'll just erase all my highlighting and start all over again, then what we're going to find is that, well, it's 5%. So looking at these numbers here, where does it first cross 5%? Well, this is fine. This is less than 0.05. And actually, wait, sorry, my bad. This is not less than 0.05. So actually what we found is in this example, it's not probably the best example to use, but there's actually no value at which at the 5% significance level, which we're going to reject, because this number here is actually not even less than 0.05. So what this kind of tells us in this question is, in this case, if that was a diagram, pretty much everything would be accepted at the 5% significance level. So in this case, it would be completely okay. So yeah, don't worry about that too much for now. Let's take a look at some other examples. So yeah. Okay, so everything we've learned so far, all of the different examples you've seen, all of the different theories you've seen, I'd say all of that has probably built up to this kind of this part of the video, because here I'll basically show you how you lay out a one-tail test, and if there have been parts which are confusing throughout the video, hopefully this part will help you bring it all together. So how do you actually solve an exam style question? Well, the first thing I just like to say is that to do these kinds of questions, there are a few things we have to follow. The first thing we have to do is we have to have a test statistic model. That's the first thing we need, a model for our test statistic. After that, we need a null hypothesis and an alternate hypothesis. Then we need to basically figure out what the test statistic actually is. Once we know that, we need to look at the significance level. So we compare it. And once we've done that, we need to write up a conclusion. And this conclusion has to be based on the question that we've just tried to do. So when you're doing these kind of questions, keep this in mind. You have to have a model. So like X is binomially distributed in a certain way. You need to figure out alternate and null hypotheses. You need to figure out a test statistic. Then you have to compare this test statistic to your significance level. And then based on that, you either reject it or you don't. And based on that, you'll write a conclusion based on the original kind of question. Okay, so let's take a look at an example question here. So let's say I have a standard medicine, like the normal medicine I use to treat a disease. And that medicine, I have an old medicine, and the original medicine has a 0.4 chance of success. So there's a 40% chance that it works. And then someone comes along and says, you know what, I have this new medicine, and I've tried it with 20 people. And from these 20 people, 11 were successes. And I'm saying that, okay, based on that, I think that my new drug or the new medicine that I've got is better than the old one that you had, because the old one worked with a 0.4% chance of success or 0.4 chance of success. And my new one, when I had 20 people, I had 11 successes, which I would say is more than 40%. So I'm saying, I think that this is better. So then we're saying, okay, let's test this doctor's claim and see, is he correct? So we're going to set up a test at the 5% significance level. And that's what the question will be. So the way we do this is, the answer to this kind of question would be something like this. First, we have to have our test statistic, like we said. So we'll say X is the number of people for whom the medicine was successful. That's what X is. It's the number of people for whom the medicine was a success. And P is the probability of success. That's how I set it up. So it's X is the number of people for whom the medicine was a success, and P is the probability that I actually have a success. So X is binomially distributed, where I had 20 people, and with the probability of success of P for each of those 20 people. That's how you know it's binomial, either a success or it wasn't. Then I'll set up H0. So H0 is basically my probability is 0.4, which is what my success normally was. But because this guy is saying his drug is an improvement, well then what we're saying is the alternative hypothesis is probability is more than 0.4. So that's what's happening at the moment. Before, the guy said that my drug is better. So we're saying, okay, this is what I'm assuming is to be true, but you're saying that this is the truth if that's not the case. So how can I see which one is true? So now I need to actually figure out what is the test statistic going to be. So first thing that we know is that this is a one-tailed test. So let's just bring our table down here. Okay, so I've got n is 20 over here. And so what's our significance level? Our significance level was 5%. And what is our P? Our P is 40. So let's take a look at where is 40 on this graph. That would be over here. So the only column we're actually interested in would be this one here, for n is equal to 20. Okay, so first things first, just because of good practice, we'd say if we draw this graph, we know it's a more than, so we know basically our reject region is on this side. So we're looking for something over here from which to, on this side, from which to start doing our rejects. So as you can see, that's rejected, that's rejected. All of these values are all rejected because a 1 minus them would give you something which is less than 0.05. So all of those are rejected. So let's take a look at this one here. This one here is 0.998, which again would not work. But then let's take a look at the first one. So this would not work either. This would not work. Okay, here we found the boundary. So this part here, this is where our boundary is. Let's just draw that a bit more clearly. Okay, so why is this a boundary? Well, as you can see, if I did the one for 11, which is here, then I'd have 0.943, which 1 minus that would be okay. Whereas if I had 1 minus this one here, that would give me something which is less than 0.05, which would not work. So the value I want to take a look at is going to be this one over here. So when we do this one over here, let's write that down. So the way to work out would be the probability that x is less than or equal to 12 was 0.979. And why do we use this? Because it's the first value which doesn't work. We found the boundary was these two. This one worked, this one doesn't work because 1 minus that is less than 0.05. So we're going to do that here. So if you got that, then how do we find the greater than version? Well, 1 minus the probability of x being less than or equal to 12 is the same as the probability that x is more than or equal to 13. So 1 minus 0.979 is equal to 0.021, which indeed doesn't work. So therefore, our critical region is where x is more than or equal to 13. So that's anything which is more than or equal to 13. Now, the thing is, our test statistic is 11 because we found that when we did our test, our experiment, we had 20 people and we had 11 successes. So that is our test statistic, which is given to us. So we will compare that 11 to our critical region of 13. Now, if I just draw this graph that we had here again, so if I just, actually I'll just draw it from scratch, just draw a big version of it. So what I said that was we found this thing here. we knew that anything on this side would be rejected. And then we actually found what this number here was. We found that this number was 13. So anything which is more than 13 is going to be rejected, and anything which is less than 13 will be accepted. And then we have a test statistic. So where does this test statistic fall? Well, the test statistic 11 would fall somewhere here. This would be 11 because that's 13. So that falls in the accept region. So what we found here is our test statistic does not give us enough evidence to reject, but instead we've accepted it. So what's important here is actually how you write the answer. So we say since 11 is not in the critical region, we will accept H0. But in terms of your exam answer, we never talk about the alternate hypothesis. So we never talk about rejecting or accepting the alternate. We only talk about the null hypothesis. So in this case, we'll say no evidence, or there is insufficient evidence to reject the null hypothesis. That's what we must say. So I'll just go back a bit. I'll write the answer. Insufficient evidence to reject the null hypothesis. And the claims of the doctor are wrong. And you'd say that the new drug is not actually better than the old drug. There's not enough evidence for him to say that the new drug is any better than the old one. So that's the important thing. The key thing I wanted to say to you is that you have to write there's insufficient evidence to reject the null hypothesis. If indeed we did find a test statistic was in this reject region, then we'd say there is sufficient evidence to reject the null hypothesis, and then we'd explain it in context that the doctor's new medicine is actually okay. It is better than the old one. But that's the kind of method we use. So you can see it's not too bad. This was all given to us. We used the significance level. We found, okay, which is the number at which it doesn't work first. It was this one here. Using that, we can find the critical region, which we found is x is more than 13. And we said, okay, this is 13. Our statistic is less than that, so we accept it. So everything is okay. So since we've done that, now let's actually take a look at a two-tailed example. Okay, so for our final example, we're going to take a look at how to write out the answer for a two-tailed test and the working that you'll need. So for this one, let's say that there's two restaurants. There's person A's restaurant and person B's restaurant. And what we found that was in person A's restaurant, 1/3 of people order vegetarian meals. And person B wants to basically figure out that are the number of people eating vegetarian meals in his one any different to that of those eating it in the other one. So he basically looked at 10 people and he found that only one person ordered a vegetarian meal, and he's trying to basically figure out, is there a connection that does the number of people eating veg in his restaurant is the same as the number of people eating vegetarian person A's restaurant. So there's two restaurants. This one has 1/3 of people eating veg, and this person wants to figure out if he also has 1/3 of people eating veg, and he's only been able to sample 10 people and found one person eats veg. So is that enough for him to decide that they have the same number of people eating vegetarian meals in both restaurants? So as usual, we'll have to say, what is x? So we'll say x is a number of people. X is the number of people eating veg at restaurant number B. That's what x is going to be. And P is the probability of ordering veg. So x is the number of people who eat veg at B, and P is the probability of people who order veg. So therefore my distributions, if I do it, is going to be x is going to be binomially distributed with, or actually let's not even start with that. Let's say first that, what's my null hypothesis? Well, my null hypothesis is that the probability of people ordering veg is 1/3. That's what I think. That is 1/3 of people who are indeed doing it. And my alternate hypothesis is that it's not 1/3. The question never said, is it more or less than 1/3? The question just basically states that, is it is it a third or is it not? So a trick in these questions is if it says, is it less than or more than, you know it's a one-tailed test. And if it says, is it not equal to or is it this, then you know it's a two-tailed test. So here I'm saying that my null hypothesis, I think it was a third. But if it's not a third, then this is the case. So that's what it's going to be. My significance level is 5. So you write down sig level at 5%. And also we're saying that if H is true, then X is binomially distributed with 10 people at 1/3, because there are 10 people in a sample, and we're assuming H0 is true, so that's a third. So basically, what we need to do first is, let's bring this down again, this table, since we'll be using that quite a lot. So normally you won't have this kind of table in your exam booklet all the time. Like you have a booklet given at the end and it has like some binomial tables. Sometimes the values which you have to look at won't be in your binomial tables, so hopefully at school they'll teach you how to use a calculator to put in the values of n and put in the values of p, which actually gives you a calculator on your, the same table basically just on your calculator. So that's just something to keep in mind to figure out if you haven't already seen that already. Just you can ask someone at school, ask the teacher, look it up online, but it will be pretty useful. But anyways, what have we got so far? We have our null hypothesis, our alternate hypothesis, we have our significance level. So as we've always done, the first thing we need to do is draw the two-tailed graph. We know everything here is rejected and everything here is accepted. So what we need to figure out first is what are these two values in between which we accept. So for the lower tail, just make sure that you have this table actually first. I just want to make that point because you won't always get this table in your booklet that you have in the exam, because some values for p won't always be in the booklet and you have to learn how to do it on a calculator. Now for that I would ask your teacher how you do it, or just ask your friends, but basically just be comfortable coming up with the same table on calculator. The calculator method is basically the same thing that you find in your booklet. They both give you the same table. So in this case we had like p is a third, so you won't get that in your booklet, but in your calculator you should be able to have it. But anyways, taking a look at this, we want to figure out what's the lower tail. So based on what the lower tail is, what we want to see is which values do we reject and which ones do we accept. So first thing you have to remember is the significance levels. These are both 2.5% because we half it on a two-tailed test. So apart from that, let's take a look at our graph. We can see 0 has a value of 0.0173. Now that's less than 2.5%, so that one unfortunately is going to be rejected. Then over here, we can see that the value 1 is 10.4%, and that's more than 2.5%. So that one is in the accept region. So all we can see here is that this is rejected and these are all okay, these values here. So we know that our lower critical value will be 0. That's a critical value there. Now there's nothing actually less than 0. So if you're bang on 0, then we're going to reject you. But obviously there's nothing less than 0 in this case, so we don't need to worry about that. So we know that, and now the only thing left is, what is the upper tail? Well, let's do the usual stuff we always did. So we have to do 1 minus each of these numbers and see at which point is that going to be more than 2.5%. So as you can see, this one would be rejected, 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 rejected. Oh, but this one for 5 would be accepted because it's 0.92 and we're trying to get the 2.5%. So as usual, we found the boundary, and then we look at the first one, which we would have rejected, which is this value for 6, where it's 0.9803. So we write the probability that x is less than or equal to 6 is equal to 0.903. So 1 minus the probability of x minus is less than 6 is the probability that x is more than or equal to 7. Therefore, 1 minus 0.9803 is equal to 0.0197, which is indeed less than 2.5%. So we know therefore the critical region is anything where x is more than 7, so any of these values here. So we can fill that in, 7. Now as we saw before, our test statistic is 1. Why is that? Because we did our experiment, only one person had veg, and 1 falls right here. And therefore there is not enough evidence for us to do a rejection, because you can see it falls in the accept region. So we'll say there again, there is insufficient evidence to reject the null hypothesis. Remember, we always talk about the null hypothesis, and we'll say something in context like there is not enough evidence to say that the proportion of people in A's restaurant is different to the proportion in B's restaurant. So always remember to add that on after that for the context part. And yeah, that's pretty much it. So normally in these two-tailed things, all you have to really do is figure out what this value is, figure out what this value is. So you see, okay, reject, or so on. So here we said reject. This is fine, 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 and then these are not accepted. That's basically what we found. So we found that these are all the regions in which we reject. Where does that statistic falls in that one, so it's okay. And two-tailed is basically just kind of doing that. So try a few more questions, you should feel fairly comfortable. And it does take a while, but after you've done it a few times, it should help you. If there are any questions you don't understand, then please let me know what those are and I'll try and explain that to you best I can. And with enough practice, there's only 3 things you need to know: how to do a lower-tailed one-tailed test, an upper-tailed one-tailed test, and a two-tailed test. So once you've kind of got used to doing that, finding what the critical regions are, the critical values, and the test statistic, you'll actually realize it's not so bad. And just get used to laying out your questions like this. So just to recap it, say H0, say H1, say a significance level, write down the distribution, make sure you've said what X and P are, do your calculations, figure out the test statistic, figure out these values, see if it falls in there, and then you can just take it from there. Always remember to end with if there's either always going to be insufficient evidence or sufficient evidence, depending on whether you reject or accept, and then put the thing in context, and that should be good enough for this. If this is very difficult, let me know in the comments below if you'd like me to go through some more examples. So this video has covered a lot of the theory, so it might seem quite heavy, but in another video I can just do maybe 3 or 4 examples of a one-tailed and a two-tailed test just to give you a better idea, and I can write down exactly what I would in the exam as well in a slightly neater form, just if that helps some students, which I've seen before. But as ever, I hope this video was helpful, and just let me know in the comments below if you would like to see more of these videos. Until then, I'll see you in the next videos.